2, test. 1, 2, 3, 4, 1, 2. Test, test. 1, 2, 3, 4.
everyone. We're going to start the first session of today, groups of unknown order. Let me tell you a few words about groups of unknown order. So there are these pretty interesting cryptographic primitive. Basically, what you can do is that you can commit to integers, and a few interesting properties are, one, that if you commit to a very large integer, you have to do a lot of work to do the commitment, and so you have this sequentiality assumption, which is useful for VDFs. And then you have this compression property, where if you take a very large integer with a lot of information in it, you can compress it down to something very small. And it also has this very nice additively homomorphic property where basically the commitment of the sum is the sum of the commitments, and that allows you to do like nice algebraic tricks to get all the proofs in things like accumulators and snarks. So we're having this little mini revolution in cryptography with this a blossoming of research around groups of unknown order. There's this key idea called proofs of exponentiation, which started with VDFs, but they're now being used all over the place in accumulators, vector commitments, polynomial commitments, snarks, etc., etc. So our first speaker here is Megan Chen. She has a math background, and she is part of the Ligero team. Ligero has a bunch of MPC experts in the team, including Mutu, Karmit, Abby, and they're taking their expertise in MPC to generate an RSA Modulus, which is kind of the basis for constructing one of these groups of unknown order. It's kind of a trusted setup. And in many ways, this MPC is super exciting for the space because it's breaking a number of records. So with that, please help me give a round of applause to Megan.
All right, thanks for the introduction, Justin. Also, thanks everyone for waking up early to be with me here today. So as a reminder, my name is Megan, and I'm a researcher at Ligero. Today I'll be talking about Diogenes, our protocol for scalable RSA modulus generation. And this is a joint work with Karmit, Yuval, Yuri, Daniele, Tarek, who is here, Abi, Muthu, and Ruhan. Great. So just as a warm-up, we're going to start with what is an RSA modulus. It's a product of two large primes, P and Q, where P and Q are kept secret. And just as terminology, we call a biprime the product of exactly two primes, and we want n to be a biprime. So there's been a long history of using RSA. It was used starting in the 70s for encryption. We've used it for other things since then, but more applicable to this conference. They're useful for verifiable delay functions, and also a lot of blockchain networks these days want to use verifiable delay functions because they're a good strategy for generating randomness. Okay, so here is a popular construction of a VDF. It starts with the Reves Shamir Wagner time lock puzzle, which is essentially doing T sequential squarings in a group mod n. So here, the circled n is our RSA modulus. And security here relies on the fact that the factorization is kept secret. Thus, it sort of makes sense to generate n with untrusted setup, which is the goal of our project. So to review, what are the goals? We want parties to interact and jointly sample a biprime modulus n. And how we do this is that everyone has a secret share, specifically an additive share, of n's factors, p and q. Also, we want 1,024 parties to participate and achieve scalability in this project. Additionally, we want a dishonest majority, or n-1 active security. This means we only require a single honest participant, even though we allow malicious parties to deviate arbitrarily from the protocol. Great. So the problem was introduced by the seminal work of Boneh and Franklin in 1997. So this isn't a new problem that we've considered. They introduced the problem and were the first to offer a solution. And Notably, to date, their framework still remains the basis for most of the follow-up works in this space. I'll highlight a few quickly. So in our specific setting of having active security across n parties and a dishonest majority, there were only 2 previous works that gave protocols that satisfied this. However, our analysis at Ligero found that they're not efficiently scalable to 1,024 parties. Additionally, only 2 of these works actually implemented their protocol. However, even though they give active protocols in their paper, their implementations remain passive. So we'll look at one of the, or specifically, let's look at the state-of-the-art implementation by Frederickson et al. They want to generate an RSA Modulus size of 2048 bits. Again, their implementation was in the passive setting. Their protocol is for 2 parties, and each party has 8 gigabytes of RAM and 8 cores of CPU. And further, they have a bandwidth of 40 gigabits per second. My back-of-the-envelope calculation for the most expensive part of their protocol says that they need at least 1.9 gigabytes of online communication per party. And additionally, their timing, or they timed their protocol, and it lasted 35 seconds for an 8-thread implementation. So at Ligero, we're pretty ambitious. Also, we want our project to be scalable, so let me show you what our goals are. So we want to generate the same modulus size and give an active implementation, specifically with identifiable abort. Nothing big, but I'll explain it later. We want 1,024 parties to participate in the computation. This avoids having a few parties so that it reduces the trust in any single party. Let's see, each party has only 2 gigabytes of RAM and a single core of CPU. We limit the bandwidth to be 1 megabits per second. Everyone has less than 100 megabytes of online communication. And also, we want our protocol to terminate in less than 20 minutes. This is pretty crazy, right? Okay, cool. So how do we go about trying to achieve this? So here's a quick roadmap of the steps we took to do this. First, we design a protocol secure against passive adversaries, and then we compile it to something secure against active adversaries. I just want to note here that this is a common paradigm when constructing crypto protocols. So what's the best scalable passive protocol? So we also use the Boneh-Franklin Framework given in the 1997 paper. And here's a quick overview of how it works. First, parties randomly sample shares, P and Q. These are secrets. Sorry. Oh yeah, each of these values are random, so there's no guarantee that their sum is prime. Since the next steps of the protocol are more expensive in comparison, the steps also includes distributed division checks to filter out values that are divisible by the small primes. And lots of these works call it trial division. Next, each party inputs their shares of P and Q into a secure distributed multiplication to get a candidate RSA modulus n. Now at this stage, we still have no idea whether the sum of Pi and the sum of Qi are actually prime. So we've done some initial filtering, but this isn't enough. So next, one way to check is to use a distributed biprimality test. Now recall that we can't really reveal the primes P and Q. However, we can use the fact that n is now public. In conjunction with the parties using their Pi Qi shares, we can actually test whether n is a product of 2 primes. Now I want to explore how we do each of these steps in detail. So first, we're going to focus on prime candidate sampling and trial division. So what do previous works do? Again, they pick their P and Q shares. They jointly trial divide. And if both of these pass, we multiply them and get a candidate RSA modulus n. But quickly, let's do some probability to see how likely we are to actually get a prime here. So let's say we're sampling 1,024-bit primes, and the only stipulation we add is that they're odd. The probability here is 1 in 500. assuming we're sampling randomly. So if we're trying to generate a biprime, we need 2. So this makes the probability 1 in 500 squared. A simple expectation says we need 250,000 samples to do this. And also, further down the line, we need to do large multiplications to construct n. And by large multiplication, I just mean 1024-bit inputs. So is there a more sophisticated way to do this? Turns out there is. So this is an idea based on the Chinese remainder theorem. So let's quickly review how that works. Suppose we have a set of remainders, taken mod 3, 5, 7, etc., all the way up to mod t. I've illustrated this with the piggy banks on the left. CRT essentially says we can map this set of remainders to a unique value in the larger modulus, which is specifically the product of all of the smaller moduli on the left. And this value is unique. So the mapping algorithm here is called CRT reconstruction. And what's special is that this mapped value will have the same remainders mod the moduli on the left. And as a quick note, this only works if the small moduli on the left don't share any factors. So our improvement is that based on the Chen et al. Manuscript that will be published very soon, we observe that if we sample non-zero values, mod the smaller moduli, mapping the remainders up to a product modulus will yield a value that's not divisible by the t smaller moduli. So if we set the moduli on the left to be exactly the first t small primes, this works exactly like trial division, but instead we're essentially picking pre-approved values, and we call this process sieving. So if we go back to our probabilities, now we're still sampling the same size of prime, but we're sieving up to the 150th prime. So the probability of actually sampling a 1024-bit prime increases to 1 over 60, which is pretty good. And then since we need 2 primes, the probability of getting a biprime is 1 over 60 squared. This means we need 3,600 samples in expectation, which is a huge reduction from 250,000. And further, we can construct n using a series of small multiplications. So quickly how that works is we sample 2 values, mod each of the small primes. We multiply them using a distributed multiplication to get these product residues. Then we can use a local reconstruction to generate our candidate n, which is pretty cool. So next, after we have our sieving trick, we need to do some multiplication. So let's review how we build our multiplier. So quickly as a review, what is secure multiplication? Here I have a 2-party functionality where parties supply their inputs AI, BI. These are additive shares of A and B. Then they input it into the functionality and receive additive shares of the product, and great. Essentially, we want to achieve the same functionality, but we want to do it with 1024 parties. So our approach is to use something called threshold additively homomorphic encryption. It comes with the typical algorithms for encryption, key generation, encryption, and distributed decryption. One thing to note is that it's threshold, meaning parties each get a share of the secret key, and everyone needs to participate in order to decrypt a ciphertext. Additionally, I said this scheme is additively homomorphic. Essentially, this says if we add 2 encryptions, the decrypted value will be the sum of the original plaintexts. Also, if we do scalar multiplication by multiplying an encryption of A here, encryption of M here by a plaintext A, we get an encryption of A times M. Cool. Another piece of our multiplication is introducing something called a central coordinator. This allows us to take advantage of a star topology. So is this coordinator trusted? No. And we can review why we don't have to trust him later. They're also not a part of the party count, meaning this is external from our 1024 party count. Also, it just does public operations. Specifically, we only want it to add AHE ciphertexts. Great, so quickly for our implementation, this is the spec we set for our coordinator. It has 1 terabytes of RAM, 128 core CPU, and 10 gigabits per second bandwidth. And we do this so we can move a lot of the heavier computation away from the parties and speed up the protocol. Remember, we want our protocol to be accessible to a wide range of parties, so we don't want to increase their computational power here. Great, so now that we have these pieces, how do we actually multiply? So parties all have their PI-QI additive shares. Then they work together to do a distributed key generation, so everyone gets the public key of the scheme, as well as their share of the secret key. Then everyone encrypts their PI and sends this to the coordinator. Now the coordinator just adds all of these up and sends it back to the parties. All the parties receive now an encryption of P, since this is additively homomorphic. Then we multiply by QI and send that to the coordinator. The coordinator, again, adds all this up, and the parties receive now an encryption of P times Q. Then if we do our distributed decryption, the parties now have a product P times Q. Great, so next, the question is, how do we actually instantiate threshold additively homomorphic encryption? This is a great idea, but we actually need to examine some existing constructions to see if they're efficient. Essentially, we reviewed all of these methods, and we settled on ring LWE, mostly because it supports AHE with better parameters. Also, we can pack multiple ciphertexts we can pack multiple plaintexts and into a single ciphertext, which is good for efficiency. Cool. So using our multiplication, we get our candidate modulus n. So the next step is to do a biprimality test to check if it's actually the product of 2 primes. Remember, we only filtered up to 150 at this point. Here we simply use Boneh-Franklin's protocol from the original paper. I will say it's probabilistic, and it's loosely based on the Miller-Robin primality test. Essentially, you take advantage of the fact that n is public right now, and you can do this test. Great. So now we have our passive protocol, and we want to compile it to security against active adversaries. How do we do this? We use a generic method called GMW, which I'll illustrate in the following slides. So here's a picture of some generic passive protocol. I give it in 2 parties, but it really can be n parties. Each party has a secret input xi, and also their own internal randomness ri. Then using these, they send messages to each other and then do a protocol. Great. Then what GMW says is, okay, this is passively secure. We can compile it up to something actively secure as follows. Parties simply commit to their inputs and randomness at the beginning. Each party then, in subsequent steps, each party validates all of their messages by sending a zero-knowledge proof along with their messages. So we don't exactly follow this technique. Our compiler sort of simplifies it. In our protocol, parties don't actually have secret inputs into the protocol. They simply use their internal randomness. So we commit to that at the beginning. This allows us to move the zero-knowledge proofs to after the messages are finished. Great. So next, the question is, okay, well, what zero-knowledge proof system should we use? So here is one of our main considerations. Our protocol requires operations in a lot of mathematical structures. So in lattices, we're doing operations for ring LWE in the ring listed above. Additionally, to generate our candidates, we're doing operations in Z mod P, where P is prime. And lastly, we have this Jacobi test as part of biprimality, which requires operations in Z mod N star. So again, our application needs to prove statements over several different types of domains. Also, our schema works as follows. We want to commit to randomness for the additively homomorphic encryption scheme, as well as the parties' PI/QI shares at the beginning. We want to run the entire passive protocol, and then afterwards, we want to commit to randomness for the sigma protocol, which we use to prove the Jacobi test, and then send the proofs at the very end. Now, this is all things that every party has to send to the coordinator. Lastly, we want the proof system to be memory efficient. This is really important because our parties have memory constraints. Again, it needs to support commit and prove, just because we're doing GMW, which I illustrated before. And lastly, we want this to be versatile. So actually, we chose to use a combination of Ligero proofs and a Sigma protocol as well. Again, so Ligero is used to do range proofs to put bounds on the noise for ring LWE. Essentially, correctness won't hold if the noise is too big. Say if a malicious adversary adds something that's out of the bound. Also, we're proving the correctness of each of the parties' action afterward. And like I said before, sigma is used for the correctness of the Jacobi test for biprimality. And this is a very specific proof that's good for when you need to prove exponentiations. Great. So now that we can be sure that the parties are behaving honestly, what about the coordinator? Well, recall that the coordinator only adds things that it receives, and it also has no inputs or any randomness. This means we can simply make it publish its transcript online, say like on an AWS server, and thus it becomes publicly verifiable. Essentially, we just check that the messages it receives is consistent with the outputs it gets. Great. So in summary, this is how we construct our protocol. So I'm going to breeze over this quickly because I want to talk to you about some performance metrics we got. So up until now, I keep harping about how our protocol is scalable, and I think these numbers really back it up. So great. We implemented our passive protocol and ran it across the number of parties listed on the left. Notably, we got up to a 10,000 party we ran the 10,000 party implementation, and this took only 35 minutes, which is pretty good. This also gives hope that we can actually do multi-party computation across all nodes in a blockchain. So notably for Ethereum, there's roughly 10K nodes online at a given time. So what about our active protocol? So we actually ran this for 1,024 parties last night, our desired target number of parties. And we got this timing. So just to generate an RSA modulus, this took about 5 minutes and 20 seconds. To generate all of the proofs for the parties to send for verification, this took less than 7 minutes. And then lastly, verification technically took longer than 8 seconds, and I'll explain why. Essentially, what happens is the parties are generating lots of proofs that they're sending for verification, and after they generate each one, they send it immediately. So then the verification becomes parallelizable. Great. So how did I achieve these performance metrics? Essentially, we opened nodes across AWS servers and also had some local participants that were employees of the company. So what about in the real world? Well, we had a trial run on Tuesday at VDF Day. Thanks to the VDF Alliance for giving us the opportunity to let us test the protocol in the real world. We had about 25 parties participating with all different types of systems, or computers, sorry. We set our coordinator on AWS, and we were able to run it 2 times. Our passive protocol succeeded, meaning we successfully generated RSA moduli, but our active protocol didn't complete. One thing I forgot to mention is that we essentially distributed binaries to all of the participants via Docker. So, okay, active didn't complete. We got security with abort, which is pretty cool, but we didn't get identifiable abort, which is what we wanted. So why do we want this? Well, we want to be able to kick out parties that are behaving maliciously and restart the protocol computation. So here's what we learned. Essentially, identifiable abort requires more rigorous testing. And up until now, no implemented MPC offers this. So this is sort of like new territory for us. And lastly, I want to thank all of the participants who came and to stay tuned. We hope to have a demo, we hope to have another demo in the future, so it'd be great if you can come join us. Great, in conclusion, we're on track to meet all of our prior goals, and there is just one exception. We had to increase our online communication per party up to 200 megabytes, but otherwise, this has been a really exciting project. Thanks, everyone.
Thank you, Megan. We have time for a few questions. We have a mic here if you want to line up, or if you raise your hand, I'll come give you the microphone.
So after you generate your modulus n and now it's public, do you do additional trial division on n, or do you just rely on the trial division in the first phase?
We only rely on trial division in the first phase.
So was that not helpful to do additional trial divisions?
Honestly, we didn't really look into it very carefully, but we sort of chose our trial divisions up to the first 150 primes, which essentially like makes, if you do CRT reconstruction, it goes up to a domain that's 1024 bits. Oh.
I mean, one question I have is that this untrusted coordinator seems very powerful for scalability. Mm-hmm. Do you think this model can be reused for other MPCs other than the RSA one?
Oh, definitely. I will say this is the first time any RSA Modulus generation application has used an untrusted coordinator. And this is particularly useful for this application because the parties have to send so much information. We're sampling primes, we're trying to sample primes, but the chance of actually hitting a prime is pretty low. So it's helpful in the course of the computation to have a central coordinator in order to avoid having parties send information to each other party, essentially instantiating pairwise connections.
Okay, thank you, Megan.
Thanks.
Okay, so our next speaker is Simon from Supranational. Simon is a hardware expert who was with Intel for 18 years, and he co-founded Supranational with two other Intel people. And quite amazingly to me, the three co-founders of left Intel basically to work in the blockchain space, and their very first project is the VDF project. I get to work with these guys on a very regular basis, and I'm just amazed at the quality of the output, very consistent. So with that, let's give a round of applause to Simon.
Okay, so I'm going to talk today about accelerating RSA operations on hardware. So let's just get into it. So we'll talk a little bit about why acceleration is important and why we care about it. Get into sort of the primitives that we're interested in for RSA. We'll talk a little bit about algorithms, although we're not going to focus much on it in this talk. And then look at the various platforms. So when we talk about hardware, from our perspective, hardware is anything you're going to run the software on, right? So we'll look at all four of these platforms and look at what some of the trade-offs are. And then get into some performance numbers, some measurements we've taken, and some proof points in the end. So why is it important to accelerate RSA? I mean, if you come here if you've watched the last couple of years here, there's been all these amazing new cryptographic primitives being introduced. You've seen VDFs, proof of exponentiation, snarks, zero knowledge, goose eggs, right? It goes on and on. And they're enabling all kinds of new use cases: privacy, unbiasable randomness, scalability, compression of proofs and storage. But they're all computationally very intensive, right? So they require a lot of computes, and that means either time or money, et cetera. So if we can accelerate this stuff, make it more efficient to run, there's a number of really big benefits. We can use higher security. We don't have to compromise on the size of keys, for example. You can get greater scale. You can do more larger circuits in your snark, maybe, whatever it is. You can improve the user experience. So sometimes if you're latency bound, right, you get results back faster, and that's important. And then you can lower costs, and that's always important. So the other interesting thing about, while this is RSA, it turns out these underlying computational primitives are pretty common across most of cryptography, so it's actually more broadly applicable. So part of what I want to accomplish today is to give you guys some actual, information you can go use to optimize your own software and whatnot. So we'll talk about sort of what is the recipe for optimizing something that we follow. So you need to define the use case. You need to know what it is you're accelerating. Typically, you'll go benchmark some software, understand the pain points today and what it's doing, right? So you know what you have to go solve. You have to identify the sort of key operations underneath it, and we'll talk about what those are for RSA. Then there's selecting a target platform. They all have different characteristics, so CPU, GPU, FPGA. You want to pick the right one depending on the characteristics of the function. And then it's sort of mapping carefully those operations onto the hardware. This becomes very important if you want to get the best performance. You have to really map it to the specifics of that hardware, and it may mean that you have to pick multiple platforms and have multiple optimization points. So this chart there's a lot on here, right? But one thing we've been looking at is sort of mapping out the space, the ecosystem. And so if this kind of a map can help you navigate. So what is your use case? What is the platform you need to go through, and the underlying, sort of cryptographic functions and operations. I think it's helpful just to sort of think broadly about the whole space, so you get that big picture as you go through the process. So for RSA, what are the primitives? So when we look at it, right, it all seems to boil down to these 4 functions: square, multiply, add, subtract, right? And if you do those, and you do those really well, you're going to accelerate most of what we see coming through here for cryptography. And again, these things apply too to ECC and BLS and other things. So just to give you 2 examples of how this can boil down, if you look at VDF evaluation, right, it's x to the 2 to the t, where 2 to the t is really, really big. And what that ends up being is iterated squaring. So what you really need to do is just make square really fast. And then exponentiation is another one, right? So break down exponentiation, and it's a square and multiply operation. So you get square and multiply to work well, and again, you're going to do pretty well. There's other things you can put on top of it, windowing and things like that. So you might have lookup tables, but in the end, you're going to go through these sort of fundamental operations. And then, so how do you measure performance, right? And there's sort of 2 main metrics. There's latency and throughput. So latency is the desire if you have one problem that you want to get it done as fast as possible. And you can see sort of in the chart here, the blue squares, you want to shrink those in the horizontal, right, so that you get that one thing done quickly. And then some algorithms are sort of throughput oriented, so you have a lot of things, and it doesn't matter really how fast one particular thing gets done, you just want to get the batch done as fast as you can. And so the green shows that difference where the individual boxes are longer, but we're getting 4 of them done at the same time, and so the amount of work you get done in a period of time is much bigger. And so understanding if you're optimizing for latency or throughput is going to affect the platform that you choose, is going to affect how you optimize. And different algorithms can vary if they're latency or throughput oriented as they run. So part of profiling is understanding, how that's going to work. So algorithms, as I said, we're not going to spend a lot of time on it here, but algorithms are huge, right? So if you look at some of the things going on, the VDF proof, for example, if you take the straightforward approach, it's very expensive and a long latency operation. You can change the algorithm. And you can really change the fundamental way the algorithm works so it becomes throughput-oriented instead. So getting the algorithm right can make orders of magnitude difference in performance. Even something as simple as looking at Montgomery space and staying in Montgomery form as you do these operations can make several times a difference in performance. So it's really worth spending time here and getting this right before you move on to the lower level optimization. So we'll go into a little bit about how large integer arithmetic works on these platforms, and it's generally all the same. So in the RSA space, you have integers that are 1K or bigger, typically, right? And those don't fit into a word size on a computer, which might be 64 bits. And so what happens is those get divided into what are called limbs, which is how you represent these numbers. And then you have to perform these basic operations on those limbs. So this gives an example of some x86 operations. So for add subtract on the left, it's pretty simple, right? So you kind of walk through the limbs, you can do add, and then there's a couple of instructions that are really dedicated to this large integer arithmetic called add with carry and subtract with borrow, right? And those perform just like you did in school, right? You sort of walk from right to left and you borrow and carry as needed to get to an answer. Multiply is a little bit trickier, right? Because you now have to do this whole cross product. And what this shows is a school book multiply operation. And you can see how you generate the partial products by multiplying all the smaller limbs. And in the end, then you sum down the columns. So there's oddly enough, specialized instructions for this too. So mulx is an instruction that lets you do it without affecting carry flag, or the flags on the processor. And that alleviates some dependencies in the superscalar pipeline. And addtx and addox let you maintain 2 carry chains, which also gives you more parallelism out of the system. One interesting thing is we mentioned squaring and multiply. Those, of course, you can do a square with a multiply operation, but there's a nice optimization you get if you optimize just for squaring. So you can see if you look at the very bottom of the multiply triangle, you have, if x and y are the same, you have the same thing. You've computed the same partial product twice. So why do that? Instead, you can just compute it once and double it, which on a binary system is a shift left, which is very cheap. So in the end, you can save a lot of computation by doing this. And if you look, this is fairly small, so it's not obvious, but if you look at a larger, a 2K operation, right, you can see it's a pretty stark difference, both in terms of the number of operations and also the depth, right, of the tree, which is the latency, effectively. So let's look at the platforms that are available and what are the underlying primitives that we need to use in order to perform these calculations. This shows the pipeline for an Intel Sunny Cove x86 processor. It's one of the newer architectures. And if you look under port 5, you'll see there's a mul operation. That's a 64-bit mul. So the data path in these processors is 64 bits. You get 1 per cycle. So on the right, in the table on the right, you see there's a table that gives some numbers. And what we've done is just sort of, for each of these platforms, calculate a theoretical upper bound on how many multiplies you can do in a given amount of time. So what's the throughput on multiply operations for 2K-bit numbers? And we do that just by sort of taking the word size and the number of operations you need to do, multiplying it out. And in this case, if we look at a 5 gigahertz core, we need 1,024 operations for 2K, and that gives us 39 million operations per second. And obviously, you can scale with the number of cores. It's a linear scaling. The other interesting thing to note about this is below the integer unit, there's a vector unit. That's a 512-bit vector unit that does operations in 8 64-bit lanes. And historically, you couldn't do multiplies in there, but there's a new sort of operation coming out called this FMA, fuse multiply add, which lets you do 8 multiplies at the same time. And so that has the potential in these upcoming systems to provide a really nice speed up. This is a GPU. This is an NVIDIA 2080 sort of TI pipeline, the Tesla core. And these are 32-bit pipelines. So you see there's an int there. That's an int 32. You get 1 per cycle there. The interesting thing about the GPU is that while you can see the frequency is lower, there are 4,600 of these things. So it's sort of massively parallel. That's the beauty of the GPU. And you need, because it's a smaller word size, you need more operations, but the total throughput is 1.7 billion operations per second, so much more. The latency is going to be higher because it's running slower and they're smaller, but typically you wouldn't send latency-oriented jobs to a GPU. So the throughput here, if you can take advantage of it, is great. It doesn't take into account memory operations and all that, but which typically will pull that down some. This is an FPGA. So in the FPGA, you're generally targeting these DSPs. This is a Xilinx VU9P DSP. It's a 27 by 18-bit multiplier. Same kind of calculation here. This runs at about 500 megahertz. Because of the funny size, you need about 10,000 operations for 2K, giving you a 327 million operations per second. So if you think about the FPGA compared to the GPU, for throughput, there's a pretty stark difference. And when we look at the data later, you'll see that for latency, FPGA can actually do pretty well relative to the other platforms, because you can sort of target your whole pipeline in an FPGA for the specific function. So this comes into the trade-offs you have to make when choosing a platform. Finally, so if you're going to build custom silicon, it's kind of neat because you get to go make up the functional units you want, right? They're going to be, you can really target them to the operation you want to do. So this is sort of a picture of an architecture we've been looking at for about a year, targeted at these RSA operations. And there's sort of two configurations I'm showing you here. One is if you wanted to do a latency-oriented operation, you could build a massive 2K or squaring unit, really. So if you think about VDF evaluators, right, you want a massive squaring unit. So you can build this whole squaring unit that you shrink it down and make it as low latency as possible. And we think you can get into sort of single-digit nanoseconds, right, for one square. If, on the other hand, you want a throughput-oriented ASIC, you can do that too. You might build a smaller one, maybe 256, 512 bits, and you tile that out a bunch of times. But because you get this larger word size, right, you're getting much higher throughput per clock cycle. So if you look at a sort of a theoretical estimated configuration here running at 1 gigahertz with 1,000 cores, we can estimate sort of with that word size you need 64 operations, so 15,000 million operations per second, so 15 billion operations per second, 10 times over the GPU. And you can sort of choose with an ASIC too, because you can make it as large or small as you want, right? You can choose what performance you target there. So one interesting thing to note about the GPU, we talked about these instructions a little bit, the mulx and the addcx, addOx. And this shows the code sequences on the right on the left for what those instructions look like. You can get about a 50% improvement by using addcx, addOx, and mulx over if you sort of write it naively, right? And I know a lot of people use compiled code here. One thing is that the compilers actually don't generate addcx and addOx because they don't like changing the definition of these carry chains. So if you're looking at your code, one thing you want to look at is to make sure you're linking in or using assembly code somewhere in your compiled stream so you can get the advantage of these operations. That's an easy way to maybe get 50% improvement. The instruction sequence on the right is for this fuse, multiply, add, the vector unit. And you can see in two instructions here to do an 8-way multiply. So the first instruction does the multiply and saves the low order bits in ACK 0. The second instruction does the multiply and saves the high order bits and accumulates them in ACK 1. So with these two instructions, you're getting those full 8 lanes. We've done some measurements on some of the early systems and seen a few X kind of speed up just from switching to this operation. So let's go into some numbers here. So we went and found some platforms, right, and benchmarked some of these. This is looking at, we're changing a little bit because it's a 2K Montgomery multiplication with a reduction. And we just iterate on that, as fast as possible. So this shows you the throughput for the variety of platforms. You can see the CPU, while the CPU runs fast and is great for general purpose and can do a lot of things really well, is fairly low at 9. However, with CPU, it's pretty easy to scale it out. It's easy to buy more cores and make everything run faster, and the programming model is about as easy as it gets. The GPU, so we measured at 350. That's a huge throughput. The trick with the GPU then is you have to manage the programming model. It's asynchronous. You have to get the data to it and from it. So, while in theory you could get 350, often you don't see that in a real application. But part of why we sort of want to show you this is as you go through optimizing, you want to know sort of what is the theoretical limit of the system, and how do you know when you're done optimizing, right? So if you're looking at this kind of operation and you find that you're, a tenth of this performance is what you're seeing, there's a lot of room to improve still. And you should at least understand sort of what's taking that another 90%, and maybe you can tackle it, maybe you can't. But part of I think is really getting the best performance out of the systems is understanding these fundamentals. And then for the FPGA, we did the same measurement, right, and got about 40. So if we look at the ASIC and how that compares, right, you can see with the ASIC you can really make a huge difference. What happens with the ASIC is you get rid of all this extra logic that you would have on a GPU or a CPU, which are solving any problem in the world. And the ASIC is really solving that one specific thing, and it does it really well. So you get this nice performance benefit. Similarly, on latency, the interesting thing here is that the GPU and the FPGA switch places. So the CPU has a reasonably low latency, and it's gotten really good, over the years. GPU is not a great latency, right? You can do things, but it takes a while. But for the FPGA, you can see it, whereas in the previous one, the GPU had, 10x performance on throughput. We see another 10x, swap on latency here. So if you have a latency-oriented, problem, an FPGA is a good place to think. And then for the ASIC, similarly, if that's what you're targeting on latency, you can really, do a great job there. Another 10x difference, essentially. So let me talk about a couple of proof points for where we've applied some of this. So about a year ago, actually almost to the day, we were starting to look at VDF evaluators and learned about this, this 35-year time lock puzzle that Ron Rivesta set up at MIT. And it was 20 years old at the time, and we thought, well, we're building this sort of low latency squaring circuit. Can we go use it to tackle this problem? And when we looked at it, it seemed like we could solve it in about 2 months of runtime if we really optimized it for an FPGA. So we set out to do that, and about 3 months later, we actually did solve it. And so we really did this, it was 20 years into the time. It took about 2 months of runtime. And here you can see we're at MIT, and that's Ron Rivest on the right. There's a whole time lock that got opened up. The unfortunate thing is that there was a fellow, Bernard, who 3 years earlier had started running the same problem on his desktop machine. And while he moved around, he always restarted it. And so 2 weeks before we solved it, he actually solved it. So, but it was great. I mean, it was a well-earned win for him. The diligence and perseverance is remarkable. And I think actually it really is interesting to see the stark difference. So one thing is that Ron Rivest had estimated that it would take 35 years to solve it. And Bernard was able to do it in 3 years, right? And why is that? It's some of these instructions that went into the CPUs, the ATCX, the MULX, it's the number of cores. Well, not in this case because it's a serial operation, but CPUs have really come a long way, right? And in spite of Moore's law and the slowing down of the frequency game, performance has continued to increase. And then, of course, if you look at the FPGA and a really targeted thing, you can really make a big difference there. The other thing I want to mention is we've been, continuing to look at VDF. So we worked on the evaluator for a while. We started looking at Wesolowski proofs, and we actually built an implementation of those using GPUs. Right, it's a very performance-oriented algorithm, and decided that why not put this stuff into the world. So what you see here is a VDF as a service that we have stood up, and you can navigate to it and look at it today. About every 30 minutes, it takes an Ethereum block hash. We put it onto an FPGA in AWS F1, which runs at about 26 nanoseconds per square to compute a VDF. We send the intermediates into a GPU in AWS, which then computes a 2-iterative Wesolowski. That gets published online. You can pull it down, you can look at it, you can verify the proof. Do let me know if you see one that doesn't verify. And all that is with about a 1% overhead on the proof generation. And you can take a look at it here if you navigate to the site. And this is an example of the output, right? So you can see the modulus, which is one of the RSA challenge moduluses. And who wouldn't trust Ron Rivest? And then you can see the proof there, and you can take a look at that. So that's all I have. Any questions, I guess? And then my email's here. If you have further questions, please feel free to reach out.
Thank you, Simon.
So, quick question. On the GPU code, that must be CUDA code.
That is CUDA code.
So
yeah.
is that CUDA code that you hand write, or it's compiled from C++ into CUDA?
So the code we use actually uses a library from NVIDIA called CGBN, which is an implementation of a libGMP type API for their CUDA, for their cores. So we just call that directly.
Right, but you have, let's say, routines that calculate the VDF in CUDA code, correct? I was just wondering if that's open source to learn from
yeah,
how to
so
do that.
Right, so we wrote code for CUDA cores that does the Wesolowski. Is that what you're talking about, the Wesolowski proof?
Right.
Yeah. It's not open source yet. We'll probably open source it at some point. but
Point this here.
Yeah, thank you.
Any other question?
Yeah, just a quick question. I was wondering if you could talk about the availability of the IFMA 512 instruction. Is that?
Sure, a little bit. I mean, I don't know, you know, anything more than you can find online, but it's in some of the Cannon Lake processors now that you can buy. I know it's in a Nook, and I think it's going to become more available, you know, through future releases of processors. I think, yeah, I don't know other than that. It's pretty limited right now, but I would expect to see more of it in the coming years.
Is the VDF as service right now available to general public?
To the general public?
Yeah, the VDF.
Yeah, I mean it's publicly online here. I mean this only takes, we only have a service right now that takes the Ethereum block hashes and feeds it through. But if you wanted another source of randomness, you know, to feed through it, for example, we could look at that. You know, it's easy to make more copies of it, right?
I don't think this matters for VDFs, but more generally, if you try to make these implementations side channel resistant, can you estimate what kind of overhead you'd be looking at?
A lot of the, so if you look at the, we have, first of all, we haven't tried to make them side channel resistant for the most part, but if you look at these fundamental operations that, you know, the add, subtract, square, and multiply, I think they're deterministic in runtime. If you look at some of the higher level things like exponentiation, you'd have to take care, I guess, to make sure that they are side channel resistant. I mean, for VDF that we looked at here, it doesn't really matter, right? So, and as far as the overhead, I mean, we have looked a little bit at like BLS. We started looking at that, and sometimes you can add constant time, right? I'm talking about constant time, runtime, and with very little overhead. So it really depends, I think, on the algorithm.
Okay, thank you, Simon.
Thank you.
Our next speaker is Ben Fish, part of the Stanford Applied Crypto team. And he's done a lot of work that's very relevant to the blockchain space. So proofs of replication, proofs of space. He's also one of the co-authors on the paper that defined the notion of VDFs. He's also worked on accumulators and batching techniques and vector commitments. And one of his latest works, which is really, really exciting, is Darks, which he's going to talk about today.
Thank you, Justin. Okay, so today I'll be talking about our latest work on transparent snarks. This is work that we put out around in the fall, and we've also made some improvements that I'll mention throughout the talk, but the bulk of the talk will focus on what we published in the fall. So the concrete result is a new snark with no trusted setup, and the snark is notable for having relatively practical proof sizes, or under 10 kilobytes for 1 million gates, which is what is novel about a snark with no trusted setup. We have other types of snarks that are based on FRI, and so previously you were seeing snarks with no trusted setup in the range of over 100 kilobytes. So the most significant thing about this new snark is its relatively small proof size. And the verification still performs well under, say, 100 milliseconds. And asymptotically, we can say that the size of the proof and the verification time is logarithmic in the degree of the size of the circuit that is being proved, with some other constant factors that also depend on the security parameter, which is why we write O lambda. And the main new tool that we're using here is a polynomial commitment scheme using groups of unknown order. So this new tool is then plugged into other machinery that was developed by many other people over the course of years. And so we apply this key new tool in order to get this new type of snark. So let me tell you what a polynomial commitment is, as the bulk of my talk is going to focus on not the other machinery that we plug this polynomial commitment into, but the new polynomial commitment scheme itself. So informally, a polynomial commitment scheme allows one party to commit to a polynomial, say over the field fp, of degree d, or at most d, with a small value, c. So c is going to be ideally constant size, and then later be able to prove that the evaluation of this committed polynomial on some point z is equal to some target point y. And again, the idea would be to be able to give a small proof, ideally constant size, although if we could give something which is polylogarithmic in D, that would also be pretty good. So a bit more formally, a polynomial commitment starts with the syntax of a normal commitment scheme, where you have perhaps a setup procedure that generates some public parameters, a commitment to the polynomial, which will produce this small value, as well as an opening protocol which could open the entire polynomial. And then the additional thing that it has is this eval protocol. And we like to describe the eval protocol first as an interactive protocol that is something called a public coin interactive protocol. And once you describe a public coin interactive protocol, then as a heuristic, you can make it non-interactive by applying something called the Fiat-Shamir heuristic. So as for performance, we want the normal part of the commitment scheme to be succinct in the sense that the commitments are much smaller than the size of the original polynomial. So ideally proportional to the security parameter and not to the size of the polynomial. And the communication in the interactive eval protocol, we would also like to be sublinear in the size of the polynomial. And then if you compile that to a non-interactive proof, that turns into a proof size which would be sublinear in the size of the original polynomial. When we say sublinear, we ideally would like to build something which is polylogarithmic or even proportional to the security parameter, and in this work we'll get something which is logarithmic in the degree. As for security, you want the commitment part to satisfy the standard definition of commitment binding. I should not be able to open a polynomial commitment to two different polynomials. And then from the interactive protocol, you want it to satisfy this generalization of commitment binding, which is evaluation binding, meaning I can't convince you that the committed polynomial evaluates to two different values on the same point. For any given point, there's only a unique target point that I can convince you this polynomial evaluates to. So I'm committed to its evaluation points. And a slightly stronger property would be to say that if I'm able to run this eval protocol and convince you of the evaluation of the polynomial on any given point of your choice, then I must actually know the entire polynomial. So this is saying that it's an argument of knowledge, meaning that I can't succeed in this protocol unless I actually know the whole polynomial itself. We would also like to have some hiding properties in order to plug this into a zero-knowledge proof system. And for that, we would say that the commitment scheme needs to be hiding as a standard commitment scheme, meaning that from a commitment, you have no information about what the committed polynomial is. And the interactive protocol should be a zero-knowledge argument of knowledge, meaning that if you only learn what the claim is, you only learn the evaluation of the polynomial on a point, you don't learn anything else about the polynomial. Another thing that we would talk about is whether the polynomial commitment scheme has transparent setup or not. So what is a transparent setup? Well, remember there's this setup procedure at the beginning which generates some public parameters for the scheme. And if that setup procedure requires some secrets that must be discarded after the process, then it's called a trusted setup. And often that would be implemented through a multi-party computation in order to distribute that trust among several parties. It's the same concept that you probably have heard in the context of snarks, where there are certain snarks which are trusted setup. They have a ceremony at the beginning to establish parameters for the scheme. This has been talked about as generating toxic waste, meaning secrets that have to be discarded or destroyed. You heard a little bit about that yesterday. And it's the same thing here. And in fact, what we'll see down the road is if we have a polynomial commitment scheme that does not require a trusted setup, then we can build snarks that do not require a trusted setup. So the previous construction, which is the most performant construction of polynomial commitment schemes, requires a trusted setup. It requires the trusted party or group of parties who are doing a multi-party computation to compute powers of this group element G, where this S exponent or powers of S are secret and have to be destroyed and discarded after the entire procedure. If anyone figures out what S is later, then the security of the protocol is broken. So our main result is to try to build a polynomial commitment scheme that does not require any trusted setup, okay, but that still has decent performance. And so what we end up doing is getting a transparent setup polynomial commitment, and we get an evaluation argument that, as I mentioned before, scales logarithmically in the size of the polynomial, so the degree of the polynomial. There's also a generalization to a multivariate variant I won't talk about. And we apply this in order to build a transparent setup snark for arithmetic circuits where the size of the snark scales logarithmically in the size of the circuit. And I'll explain a lot more how all this gets plugged together throughout the talk. So just to start with a rough comparison of what we end up with in the end with this transparent snark and how it roughly compares in terms of its asymptotics to other snarks out there. We have the most performant snarks, which are not transparent and they don't even have something called universal setup. That would be like Groth 16. It requires a new setup for every different type of circuit or computation which is being proven. But those are the most performant. And then you have much more recently, you have Planck and other systems similar to Planck, like Marlin or Sonic, which have a universal setup, so they're still not transparent, and they perform very competitively with Groth 16. So you see that the proof size is going to be basically a constant number of group elements, and the verification time is basically just one pairing. It's actually, this is a little bit inaccurate, it's a couple pairings. But then you have Starks, which are also transparent, and you have many other things in the class of Starks, like fractal. I'll give more detailed comparisons later. But you basically have this class of FRI-based proof systems, and they are not only transparent, but quantum secure, but you have asymptotically much larger proof sizes that are scaling like log squared of the size of the computation. And that's where you end up getting these, maybe around 1 million gates, you get around 100 to 200 kilobytes in size versus around 10 kilobytes in size, which is what you have with what we're calling supersonic. So supersonic sits kind of in the middle. It's transparent. It has a proof size that scales logarithmically in the degree. And the verification time is a logarithmic number of exponentiations, but these different exponentiations across different schemes don't directly compare because they're exponentiations in different types of groups. So in supersonic, we're doing it in RSA groups or class groups, whereas in Groth 16 or Planck or Boneh proofs, it will be over prime groups. And in FRI-based schemes, we're computing hashes. So it's a little hard to compare just based on the asymptotics. This is just to give you a rough idea. And then Boneh proofs, of course, is good on prover time and proof size, but it is linear in the circuit in terms of verification time. So for very large circuits, say on 1 million gates, it would not scale at all. So let's go through the main construction, which will be the rest of the main focus of this talk, which is how to get this new polynomial commitment scheme. So we start with an integer encoding of this polynomial over this field fp. So we represent a polynomial over fp as an integer polynomial simply by mapping the coefficients to representatives in the range 0 to p, right? And then we choose another integer q, which is greater than p. In fact, later you'll see we have to choose q to be substantially greater than p, but you'll see that I'm cheating a little bit now, just for simplicity. We output the encoding, which is this f hat of q, which is going to be just an integer in z. So to give you an example, if f hat of x was this 4x cubed plus 2x squared, etc., then if we were, and q was equal to 10, then the encoding, the integer encoding of this polynomial would simply be the number 4213. So notice that now I've only described how we're mapping these polynomials to integers. We haven't done anything to make this a commitment scheme or succinct. It's still the same size as the original polynomial f. But the whole point is that I've mapped it to the integers, and now what we're going to do is use integer commitments. So let me first convince you that this is a valid encoding, meaning that you can get back to the original polynomial from the encoding. So the first fact to observe is just that every integer in this range, 0 to q to the d plus 1, is uniquely decodable to an integer polynomial with positive coefficients. And that's just doing base q decomposition of the number that you got. Right? So over here, base 10 decomposition would give you the original coefficients back, 4213. We actually need a slightly fancier fact because we're going to, as a detail that comes out of the construction, we're actually going to encode them as integers that could also be negative. But then it turns out that they're decodable to polynomials with coefficients of absolute value bounded by q over 2. So notice also that this encoding has some homomorphic properties. If you add the encoding of f and the encoding of g, then you get the encoding of f plus g, as long as q is sufficiently larger than the coefficients of the original polynomial. What you're trying to prevent here is overflow. So you can still basically use base q decomposition. You need the coefficients of f plus g to still be smaller than q. And this is why, as I said before, that in the end, we're going to get a protocol where we have to choose q to be substantially larger than the original polynomials because we're going to be doing homomorphic operations on encodings and the coefficients will be growing. So we want the coefficients of the added polynomials to still be smaller than this q that we're using for the encoding. We also have this interesting property called a monomial homomorphism, which is that if I have f of x and I want to derive, and I have f of q, which is the encoding of f, and I want to derive an encoding of x to the k times f of x, then that's just simply q to the k times f of q. So then what we're going to do is we're going to use this key object called a group of unknown order. Okay? And this group of unknown order, what it does is it gives us the ability to commit to integers, and the commitment is not only succinct, it's just one group element, but it is also homomorphic. So if I have the commitment g to the x for an integer x, then g to the x times g to the y is g to the x plus y. So the way that we're going to commit is basically get our integer encoding of the polynomial, that's f hat of q, and then just commit to this integer f hat of q. And this will inherit the same homomorphic property if I have an integer, if I have this integer commitment to f hat of q, and an integer commitment to, say, a different polynomial g hat of q, then I can multiply the commitments to get a commitment to g to the f hat plus g hat of q. So there are several different types of groups of unknown order. The most certain one is the RSA group. This is just based on the RSA assumption. And basically, if you take n to be a large number, which is the multiple of two secret large primes, p and q, then you get a group of integers co-prime with the order of the group, which form a group under multiplication mod n. And so for, like, say, a 3048-bit n, you get around 120-bit security, we believe. The only problem with this group of unknown order is that it requires someone to choose the secret p and q, so it is not a trustless setup group of unknown order. And so if we were to use this for our scheme, then we would not have trustless setup. We would have something called universal setup, but we wouldn't have trustless setup. But the RSA groups are, say, based on the most standard assumptions. So then we have class groups, which are also believed to give us groups of unknown order. We believe it's hard to compute the order of the group. It's also hard to take odd prime roots in these things called class groups. But the really nice thing about class groups is that all you need to do is specify something called the discriminant of the group, and then you can start doing operations in this group. So it doesn't require anyone to produce some kind of trusted setup parameters. Nobody has to choose some secret numbers, which are then discarded later. And so for a discriminant around 1600 bits, we believe to get around 120-bit security, about equivalent to 3048-bit RSA. And this will also, the discriminant will also, size will tell you the size of the group element representation itself. There's also a new candidate group of unknown order that appeared on ePrint maybe just a few days ago. So I would say this would naturally be the least trusted type of assumption, but it is very exciting because this new group, which is based on Jacobian groups of genus 3 hyperelliptic curves, has a group element size of just 303 bits, they claim, for around the same security of 120 bits. So that's the conjecture in this new work, and this will require further study, but this would be extraordinarily exciting because it would give us excellent performance with what I'm going to show you. So the main part of the dark polynomial commitment scheme is now I've showed you how to commit to polynomials. How do you do the evaluation protocol? So the intuition is that I'm going to describe a recursive protocol where at every step I basically split the polynomial into a left part and a right part. So I start with a polynomial of degree d. I split it into two halves which each have degree d. But if I split it into two halves which each have degree d, then that wouldn't help. So actually what I'm going to tell you is that FL and FR are basically a polynomials of degree d over 2, where FL has the left half of the coefficients and FR has the right half of the coefficients. So in other words, f of x is equal to FL of x plus x to the d over 2 times FR of x. I've just factored out all the x to the d over 2 terms from the right part of the polynomial. So now I have two polynomials FL and FR, which are degree d over 2. And then what do? Well, the verifier is going to send a random challenge to the prover. And then the prover is going to, both the prover and the verifier are basically going to compute FL of x plus alpha times FR of x. And so that gets replaced with this new f prime of x. And now this thing is degree d over 2, and we recurse. Now, obviously, this is not the actual protocol because this would not be succinct. I'm sending these polynomials in the clear. This was just to give you the information theoretic intuition about what's happening. What actually happens is that we're going to leverage the homomorphic properties of the commitment to do exactly the same thing over commitment. So the prover sends a commitment to the left part and the right part, and then the verifier can basically use the homomorphism of the commitment to compute this linear combination of the two polynomials in the exponent and derive g to the f prime of q. Now, putting a bit more information in here, in order to convince you that it evaluates to a certain value, we also have to send some extra terms. So basically, the prover is going to send the claimed evaluation point y equals f of z modulo p. And then the prover will send the evaluation of the left polynomial on this point z as well as the right polynomial. The verifier will be able to check on its own that y is consistent with yl plus z to the q to the d over 2 times yr. And so the left part and the right part are equal to yl and yr if and only if the original polynomial evaluates to y at the point z. Now, there's only one part that I haven't explained yet, which is how does the verifier check the consistency of the left commitment and the right commitment with the original commitment? In other words, how does it verify that this left commitment CL times CR to the Q to the D over 2 is equal to the original C? Also note that this is leveraging the monomial homomorphism, which is that we're able to compute the commitment to the polynomial x to the d over 2 times fr of x by using q to the d over 2 in the exponent. So this last part is going to use this proof of exponentiation trick. It's the same trick that's used, the key trick that's used for VDFs. And the way we described it in the original dark paper, it's using Wesolowski's proof of exponentiation. And so this is basically a protocol in order to convince you that CR to the Q to the D over 2 is equal to some group value, C over CL. The reason why we need a proof of exponentiation is because it would be too expensive for the verifier to run this exponentiation on its own. It has size, linear in the degree of the polynomial, and we want to have a scheme which has logarithmic verification time. So without going through the details, because I want to get to other material, proof of exponentiation is a really, really neat interactive protocol that allows you to verify a claim of this form where the verifier is very efficient. There's one extra issue, which is that every time we recurse, we multiply one of the polynomials by this random challenge alpha. And alpha is going to be, say, chosen in the range 0 to p. So the coefficients of the polynomial get larger and larger with each level of recursion. So what we actually end up needing to do is to set this encoding point q to be greater than p to the 2 log d. And that's so that after we do multiple levels of recursion, the homomorphic operations still work. So the final step, when we get to the last level of recursion, we end up with a degree 0 polynomial, just an integer. So the prover will just send this integer directly to the verifier, and the verifier will check whether this integer is indeed the integer, consistent integer commitment, as well as check a bound on the size. And checking this bound on the size, checking that f0 is less than p to the log d, will imply that all the other polynomials were also had coefficients within a correct bound. And that's not a security proof, but we go through the work of showing a security proof to do that more formally. The intuition is that this check at the end is going to imply that all the polynomials above were encoded properly, and therefore that they were binding commitments. So in the end, the proof size is going to be from all the recursion 2 log d group elements and 2 log d field elements. The verification time is around 2 log d exponentiations in G. The proof size is like 2 log d plus 3 p log d. And the prover time can also be optimized with pre-computation, so you get down to O of p times d operations. So the original security theorem is that very informally, the dark evaluation protocol is an argument of knowledge based on the following assumptions: low order assumption, strong RSA assumption, and adaptive root assumption. All of these assumptions pertain to groups of unknown order. And here's a rough asymptotic comparison to other PCS schemes. I'm going to skip over this a bit now because I'll give you a bit more detailed information. I want to mention the work that we've done since the fall when we released this paper. So we have new work, darker, which I won't go into the technical details of. Benedict gave a talk about that at the VDF Day. But the highlights are that there are both performance and security improvements. So we can get security, which is only based on the RSA assumption, rather than having these other assumptions like low order and adaptive root. The eval approver time is brought down to scaling basically like square root of d with some other polylog terms, which is a substantial improvement over the towards getting much more practical prover times. Computing a commitment is still linear in the degree, but this means that the eval time is going to be an insignificant part of the computation compared to computing a commitment when we plug this into a snark. It is also of independent interest that we can get an asymptotically square root of d eval protocol. And the verifier time stays about the same. The proof size increases slightly to 3 log d instead of 2 log d. So to give you concrete sizes, if we were to use 3048-bit RSA, this would be around 23 kilobytes. This is using the larger, darker protocol, which has faster evaluation time, slightly larger proofs. With 1600-bit class groups, we would get around 12.9 kilobytes. With this really new Jacobian group of unknown order, we would get all the way down to 3.2 kilobytes. So we're very excited to see whether this new group of unknown order holds up. I want to mention that if you're evaluating on a zero polynomial, then you don't actually need to send any field elements, so these numbers come slightly down. And that actually ends up being the case when we plug this into the machinery that allows us to build a snark. So rough prototype performance. This implementation was done by developers at Fedora, Philippe Camacho and Fernando Krell. The performance charts basically show you that the new, darker protocol is a substantial improvement over the old one. And if we were to extrapolate the prover time for the evaluation protocol using the new improvements that we've made since the fall, then we're looking at about under 70-second time for evaluation on a polynomial of degree that goes up to 1 million. So now let me just say a few words about plugging this into the machinery to build a snark. You've heard about this yesterday, so I'll go over this pretty quickly. Basically, the modern paradigm is to construct constraint systems based on polynomial testing, to build these information theoretic protocols that involve polynomials, and then to replace and evaluating polynomials on points, and then to replace those polynomial evaluations by polynomial commitments and polynomial commitment evaluation protocols. So abstractly, the prover is sending first oracles to the verifier, and then the verifier is querying on points. That gets replaced with sending polynomial commitments to the verifier, and then running these evaluation protocols. The interactive evaluation protocols would be then compiled with Fiat Shamir in order to get non-interactive evaluation protocols, which then leads us to a snark. There's also some interaction as well in the polynomial oracle proof part, so that also gets included in the Fiat Shamir compilation to a snark. Here's a variation on a theorem from Planck, just to have something specific that I can now plug dark into. So there is a 3-round polynomial interactive oracle proof that has just 2 preprocessed oracles, 3 online oracles, degree 3n, and 5 queries with non-zero outputs, and 8 queries overall. So we compile this using the paradigm that I basically described, replacing the oracles with polynomial commitments and the evaluations with the eval protocol. An important optimization, which I won't go into the details of right now, is that we can actually open a commitment at multiple points by sending no field elements. And so for the dark protocol, this is based on the homomorphic properties of the dark protocol. It leverages the monomial homomorphism. And what ends up happening is that the cost of opening at k different points is actually just one extra commitment and one eval on a zero polynomial. This technique actually generalizes, and this is explored in a paper that, by Boneh, Justin Drake, myself, and Ariel Gavizon that you can look up on ePrint. And it describes this more generally for both Kate polynomials and additive polynomial commitment schemes. So putting this all together, if we look at the dark version of Plonk, so plugging dark into Plonk, we get a proof size that consists of 5 field elements, 4 commitments, and 1 eval of degree 3n. So with 1600-bit class groups, that's around 10 kilobytes. With 303-bit Jacobians, this is going to be, under 3 kilobytes. And the verifier time is milliseconds. The prover time is relatively expensive. If we move to darker, we get slightly larger proofs. Still, for class groups, it's around 14 kilobytes. For the Jacobian, it would be only 3.2 kilobytes. And based on our estimates, although take this with a grain of salt because we need to really run this more carefully, a prover time will be about 700 seconds. This is with 1 microsecond class group operations. So very, very, very rough comparison of snarks. Take this all with a huge grain of salt. I'm just trying, it's very hard to give comparisons of these systems because you have to do the benchmarks carefully on the same, and I don't want to insult anyone as well. Like, take this with a huge grain of salt. If there are numbers here, shout out from the crowd that they're wrong. I'm just trying to give you a general picture of where things fit in. So in terms of proof sizes, as I was saying over and over, the universal setup and trusted setup snarks give you really small proof sizes. 3 to 4 kilobytes for universal setup, just 0.2 kilobytes for Groth 16. Bulletproofs are very small as well, but they have poor verifier time. If you look at on the other end of the spectrum, the quantum secure transparent snarks, then you're in the range of 100 to 300 kilobytes. And class group dark is going to be around 10 to 14 kilobytes. Jacobian dark, if it works, will be super exciting because it's now down in the range of the universal setup snarks, around 3 to 4 kilobytes. As for verifier time, the best performance is still from the Plonk or Groth 16 or Marlin, less than 10 milliseconds, say around 2 milliseconds. Fractal performs very well as well, around less than 10 milliseconds. For us, this is going to be more around 75 milliseconds. And based on the work that we've done to bring down the prover time, we're now in the same ballpark as these other systems, like FRI-based snarks like Fractal and Stark, etc. We're still going to be, say, about 7 to 10 times slower than Groth 16 or the K-Plonk. Okay, thank you very much. I hope that gave you a good overview of the dark polynomial commitment scheme, our new transparent snark, and the progress that we've made since the fall. I can take any questions if there's time.
There is a mic here, or raise your hand.
Hi, Ben. Really
Hi.
awesome work. I
Thank
had a
you.
question about the evaluation proof.
Yes.
I'm sure you guys have thought about this, but maybe you could elucidate what's wrong with using a KZG-style approach to an evaluation proof where you commit to a quotient and you prove that the quotient times x minus the evaluation point equals the, yeah.
Yeah, so the short answer is it just doesn't work. But we can, you know, it would be really nice. Actually, we were trying to get a constant size polynomial commitment scheme from groups of unknown order. But we can talk offline about
Sure.
what we ran into with trying to make that idea work. Yeah.
Cool, thanks.
Any other questions? Okay, well, thank you very much for your time.
Thank you. We now have a half-hour break, and at 11 o'clock we have a session on blockchain economics.
In the scientific spirit of always questioning everything you think you know, now we're going to have Tim Roughgarden, who's talking about axiomatic approach to block rewards.
Okay, thank you, Bram. Can you hear me in the back? Yeah, okay, great. So good morning, everyone. I wanted to tell you about some work with a couple of my Columbia colleagues, Xi Chen and Christos Papadimitriou, an axiomatic approach to block rewards. So this is a paper about incentive issues in blockchain protocols. So I'm interested in thinking about whether protocols have been designed in a way that motivates their users to behave in the way that the designer intended. And so this talk is very much in that spirit. But before I get to the specific contributions of this paper, let me give you a couple slides about sort of my big dream, which is to build a bridge between a well-studied part of economics known as mechanism design and incentive compatibility in blockchain protocol design. So what is mechanism design? It's often referred to as inverse game theory. So what's game theory? Well, you write down a description of a strategic situation. So you have your players. Those might be, for example, miners in a blockchain protocol. Each of the players has actions, so for example, honest mining and various deviations from honest mining. And players have payoffs, so perhaps the expected reward that a miner might receive. And the usual approach in game theory is descriptive. So you just write down your game, you sort of passively look at its equilibria, and you try to reason about the strategic setting through properties of that equilibria. All right, so mechanism design, as inverse game theory, you don't start with a game, rather you start with an intended outcome. And then you put on your engineer's hat and you ask yourself, can I somehow design the rules of a game so that this intended outcome arises as an equilibrium? Okay? And so I hope this idea, designing the rules of a game so that sort of, participants behave in the way you intend, I hope that sounds potentially relevant to incentive issues in blockchain protocol design. And so indeed, what I'm really interested in is opportunities for technology transfer from mechanism design to blockchain protocol design, both in the sense of sort of specific technical tools, but also, mechanism design, it's a very well-developed, very successful theory, and so I think it can offer a sort of blueprint for what a theory of incentive-compatible blockchains might look like, say, 10 years from now. All right, so why am I and so many other people sort of a big fan of mechanism design? What has it done for anybody? Well, let's start simple. In mechanism design, you have a formal articulation of the design space. So if you walk up to a random mechanism designer on the street, and you use the phrase, the space of all mechanisms, that mechanism designer will actually know what you're talking about in a precise and mathematical sense. And wouldn't it be nice if we had some mathematical proposals for what the space of all blockchain protocols look like? Now, once you have a formally articulated design space, all kinds of doors open up. For example, you can pick your favorite objective function and optimize over the design space. Look for a protocol that is in some sense optimal. And once you have that optimization mindset, you generally wind up exploring parts of the design space you hadn't considered before. So I think this whole exercise also holds the promise of guiding us to new and interesting blockchain protocols. Okay? So that's the big dream. Let me now sort of pass on sort of specifically to what this paper is about. This paper is very much in this spirit, but we're also going to be focusing very narrowly. So we're going to be analyzing in detail a very small piece of the overall puzzle. In exchange for that specificity, we will be rewarded with sort of very crisp mathematical results, as you'll see. Okay? So you can think about incentive issues on blockchain protocols at various timescales. And in this paper, we look at kind of the shortest imaginable timescale of interest, that of a single epoch, of the creation of a single block. Now, mind you, the most famous incentive attacks on blockchain protocols, selfish mining and other forking attacks, for example, they take place at a longer time scale, thinking about miner behavior over multiple blocks. So I'm not talking about that. I'm talking about incentive issues purely in a single epoch for a single block creation, specifically incentives for Sybil attacks and for collusion, okay, at the time scale of a single block. So what is the design question I want to look at? I want to look at how block rewards get distributed. So go ahead and think of Bitcoin for a concrete example, but in general, I'm thinking about some blockchain where each block creation is associated with some reward, maybe a block reward or transaction fees or both, it doesn't matter. And then somehow the protocol has to decide how the reward associated with this block gets distributed back to the miners. So for example, in a proof of work context, you would want to distribute rewards to the miners, or expected rewards to the miners, that is a function of the computational power they bring to the table, as a function of their hash rate. Okay? So that's the design question. Given the computational power people bring to the table, how should you distribute the block reward? So what's the dominant paradigm? How is this done in something like Bitcoin? Well, it corresponds to what I'm going to call a proportional allocation, meaning the expected reward of a miner is just equal to the fraction of the overall hash rate that belongs to it. So if you bring 20% of the overall hash rates, your expected reward is 0.2 times the block reward. Okay? So the goal of this paper is to really investigate this and ask, is there any reason to do anything different? Could there be some deviation from this proportional allocation rule, which was better in some sense of the word? Or equally interesting, can we prove in a formal sense that the dominant paradigm, that the proportional rule is optimal in some sense? Both of those are things I would be interested in. Okay? So can we do better than the proportional rule? So to start investigating that, I need to tell you what are the other options, right? So what's the design space, okay? And the abstract formalism we're going to be using is that of an allocation rule, okay? And that's just a function from a vector of hash rates indexed by public key to a vector of expected rewards, again, indexed by public key. Okay, so it just maps contributed hash rates back to expected rewards. So that's a function. In our context, it's natural to think specifically about budget-balanced allocation rules. That just means that the rule always distributes the entire block reward, nothing more, nothing less. You can think about relaxations, like allowing the protocol to keep some of the reward for itself, but for the most part in this talk, I'm going to just focus on the natural budget-balanced case. All right, so I'm saying other options might be other budget-balanced allocation rules. So next you might say, well, that's all fine. I mean, anyone can sort of write down a definition on a slide, but you might be wondering, does this mean anything? Okay, especially if you're thinking about sort of proof-of-work type blockchains, you might be wondering, doesn't this whole proof-of-work paradigm sort of force us into the proportional allocation rule? Right? So I mean, it's just a fact that if you have 20% of the mining power, under the random oracle assumption, you're 20% likely to be the first one to solve a hard crypto puzzle and get the corresponding block reward. So the next point I want to make is that at least in principle, if we really, really wanted to, we could implement kind of any alternative to the proportional allocation rule that we wanted. Okay, I'm not saying we should, but I'm saying if we really wanted to, we could. How might you do that? The reason is basically the law of large numbers. So I want you to think about the way Bitcoin does leader election as taking a single sample from a probability distribution. The probability distribution that is proportional to miners' hash rates. You take one sample, the selected miner is then the one who authorizes the block and gets the entire reward. So an idea is to take not one sample from the hash rate distribution, but 1,000 samples or even 10,000 samples over the course of an epoch. With that many samples, you're going to have almost an exact estimation of the hash rate that everyone contributed over the course of that epoch. And once you know basically what everybody's hash rates were, the protocol is then free to distribute rewards however it wants. Okay? Now you might ask, how would you actually implement these thousands or tens of thousands of samples? And one way you could do it, again, at least in principle, is you could do it the way that mining pools do it. So in addition to having a hard crypto puzzle, the solutions of which sort of define when epochs end, you can, in parallel, have a much easier, 1,000 times easier, 10,000 times easier version of the crypto puzzle and collect so-called partial solutions to the easier puzzle along the way. So between each two solutions to the hard puzzle, you are expecting to see 1,000 or 10,000 samples of the easier one, which gives you those samples from the hash rate distribution. Okay? So again, I'm not saying we should deviate from proportional, but I'm saying if we really wanted to, we could. All right, so we're going to investigate this question using sort of a tried and true methodology from economics, namely the axiomatic approach, right? It shows up in the title. So this is basically a two-step recipe to reasoning about design decisions. And step one, you kind of get up your courage and you actually write down a formal mathematical specification of what you want. Okay, so the desiderata or constraints on the design. Okay? Once you've written down these axioms or these constraints, now you explore the ramifications. So you ask what part of the design space, if any, satisfies all of the axioms that you've written down. So famous kind of role models that we had in mind when we sort of started, we were thinking about sort of classical expected utility theory, like von Neumann and Morgenstern, which characterizes utility theory in terms of consistency axioms over preferences over lotteries. Arrows and possibility theorem from social choice, which says that when you have 3 or more candidates, there's no voting rule that satisfies a natural list of 3 axioms. or Shapley's characterization of his Shapley value as the unique cooperative game value satisfying a list of 4 particular axioms. Okay? So this is sort of the steps we want to follow in. And to be clear, right, so we wind up often proving impossibility results, saying that nothing satisfies all the axioms, or maybe uniqueness results saying that only one thing does. That doesn't literally mean the problem is impossible or that there's only one way you could solve it. Right? Take Arrow's impossibility theorem. Right? It's not that we cannot run an election with 3 or more candidates. We do it all the time. Rather, Arrow's impossibility theorem clarifies exactly what compromises we have to be prepared to make. So if you run an election with 3 or more candidates, you will violate one of Arrow's axioms, and it's up to you to figure out which violation is the most palatable and design your voting scheme accordingly. Okay? So I really view the benefit of the axiomatic approach as clarifying what you have to give up from the list of what you want. Okay? All right, so axiomatic approach. So step 1 is I owe you some axioms. Okay, so there's going to be 3. And the way we'll arrive at these axioms is I'm going to throw out some straw man, crazy allocation rules to you. And you're going to look at them and you're going to be like, I hate this rule. And then we're going to take the reason why you hate that rule and turn it into a constraint. Okay, and those will be our axioms. So the first straw man allocation rule, let me just call it the uniform allocation rule. So here's what you do. You take all the public keys you've ever heard of. You pick one of them uniformly at random. And that's who gets to authorize the next block and get the whole block reward. Okay? Terrible idea, as you all see immediately. This proposal is totally missing the point of a permissionless blockchain where Sybil attacks, where identities are cheap. If you implemented the uniform allocation rule, certainly everybody would be doing tons of Sybil attacks, because the more public keys you make available to the protocol, the higher your probability of collecting that reward. So we would like to reject any other protocol which suffers from this same flaw, okay, which is vulnerable to Sybil attacks. So that leads us to axiom number 1, Sybil-proofness. I think it states what you would think it would state. So if you start from any given hash rate, and if you think of one of the miners shattering themselves into a bunch of Sybils, where, of course, the combined hash rate of the Sybils should be no more than the miner had originally. The miner can't just fabricate the hash rate from thin air. So whenever a miner shatters itself into Sybils with the most of the combined hash rate, the total reward earned by all the Sybils can only go down. Okay? So this miner was at least as well off before it tried to mount the Sybil attack as it was after. You can do a Sybil attack, but this asserts that the total reward that you earn is either the same as it was before, or if it changes, it's going to go down. Okay? The proportional allocation rule, right, by design, is certainly Sybil-proof. Right? If you're a 20% miner and you shatter yourself into 2 10% miners, the collected reward of your 2 Sybils is the same as what it was before, 0.2 times the block reward. Okay? The uniform rule, as we've seen, does not satisfy this axiom. So that's axiom number 1. So let me throw out a second super crazy allocation rule to you, the winner-take-all rule. So suppose we're in that regime where we're taking thousands of samples or tens of thousands of samples during an epoch. So we have a super accurate estimation of everybody's contributed hash rates. Then one thing we could do is deterministically allocate the entire block reward to the biggest miner, okay, the miner that contributed the largest hash rate during that epoch. This, again, probably immediately you're bothered by it. Notice the issue is not Sybil-proofness. Okay? This is a Sybil-proof rule. If you only reward the biggest miner, there's certainly no incentive to shatter yourself into smaller miners. The problem, in some sense, is the opposite and the unstoppable force towards centralization that it introduces, okay? The incentive to collude. Right? If you're only going to reward the biggest miner, nothing to anybody else, what would you possibly expect miners to do other than basically form a 51% pool to guarantee getting that reward? Okay? So our second axiom is that we want to reject any other allocation rule which suffers from this same flaw, which is vulnerable to collusion. So that brings us to collusion proof. Again, I think it says what you'd think it would say. So given a vector of hash rates, if a bunch of miners get together and combine forces, right, so their combined hash rate is going to be the sum of their original hash rates. If they combine forces, then the total reward that they earn does not go up. Okay? Either it stays the same or it only gets worse because they colluded. Okay? The proportional rule, again, by design, is collusion proof. Two 10% miners, if they want, can join forces and become a 20% miner, but their expected reward, 0.2, will be the same as the sum of their expected rewards was before they colluded. Okay? So those are axioms 1 and 2, robustness to Sybil attacks, robustness to collusion. We are going to need a third axiom just to kind of get rid of some other annoying rules. The axiom is anonymity. Okay, so this basically says that the way rewards are distributed should not depend on what your public ID, public key actually is. Okay, it should just depend on the hash rates that you see. Or equivalently, if you permute everybody's hash rates, the reward should get permuted in exactly the same way. So what does this rule out? This rules out some ridiculous allocation rules like a dictator rule, which always allocates it to the lexicographically first public key that you've ever heard of. Okay? Technically, that's an allocation rule. Technically, it's Sybil proof and collusion proof, but it's obviously ridiculous, and it's ridiculous because it violates this anonymity axiom. Proportional allocation, of course, is anonymous in this sense. Okay? All right, so we have 3 axioms. We have at least one rule, which satisfies all 3, the proportional rule. So the question then is there anything else? And so the first main result of the paper gives a negative answer to that. No, there is nothing else. So the unique budget-balanced allocation rule that satisfies Sybil proofness, collusion proofness, and anonymity is the proportional allocation rule. If you insist on exact budget balance in those 3 axioms, there is nothing else you can do. So again, as far as interpretation, so one interpretation would be to just kind of throw up our hands and declare victory and say, cool, this is the way we're doing it anyways, and this is a justification for that. Don't have to second guess anymore. The interpretation I like even more is that it says, well, you know, maybe or maybe you don't want to deviate from proportionality, but if you do, then you have to relax or give up on one of these 3 axioms. So they really sort of just they clarify what you have to give up if you want to deviate from proportional allocations in any way. Okay? I should say I found out recently that basically the same result was proved in parallel by a couple of economists in unpublished work, Jacob Leschno at Chicago Booth, and also Philip Strack in the Yale Econ department. So proof's not long, so let me just tell you the proof. It's going to take place over a couple slides. Let's see why this is true. For the proof, just to keep it simple, let me assume all the miners' hash rates are positive integers, so 1, 2, 3, or more. Okay? There's a boring argument that extends it to rational hash rates that I'll spare you from. No surprise, the proof's going to proceed by induction. So induction on what? Well, the first thought might be induction on the number of miners, or on the number of public keys that you know about. But then you realize you're going to have to be dealing with these Sybil attacks and collusion attacks, which actually change the number of public keys that are out there, okay, which sort of messes up the induction. So instead, we're going to induct on the number of miners who contribute a hash rate bigger than the minimum, who contribute a hash rate of 2 or more. Okay? That's what the induction will be on. With this induction parameter, the rest of the proof will write itself. We'll basically just sit back with satisfaction as the 3 axioms do all our work for us. Okay? So the base case, that's when there are no miners with more than the minimum hash rate. So we just have some number of miners, capital H, each with hash rate exactly 1. Okay? So here's where anonymity plays an important role. Okay? If everybody's contributing the same hash rates, they all have to get the same expected reward by anonymity. By strong budget balance, the sum of the rewards has to be equal to 1, so we even know what everybody's expected reward is. It's 1 over the total hash rate or 1 over capital H. Okay? So anonymity and budget balance do the work for us in the base case. What about the inductive step? So think about a hash rate vector that has at least 1 miner with a hash rate bigger than 1, hash rate 2 or more, and fix one such miner I. Okay? Basically, what we're going to see is that Sybil proofness gives lower bounds on what you can pay I, and collusion proofness gives upper bounds, and the proportional rule will be the only one which sort of threads the needle. Okay? So first, let's imagine a deviation from the proportional allocation which underpays this minor I which has a hash rate of 1 or more. Okay? This is going to witness a failure of Sybil proofness. Okay? Why? Well, this miner with hash rate H sub I, which is being underpaid, it can shatter itself into H sub I Sybils, each with hash rate exactly 1. Notice that increases the number of public keys, but it decreases the number of miners with hash rate bigger than 1, okay, because H sub I has sort of gotten rid of itself. So the inductive hypothesis applies. We know those Sybils will be paid proportionally, 1 over H each, which means the little H sub I Sybils collectively get more than this miner was getting originally. The Sybils get H sub I over capital H. The miner originally was getting strictly less than that. So that's a successful Sybil attack because miner I was underpaid. Case 2 is sort of works in reverse using the collusion proofness axiom. So now suppose that a rule tries to deviate by overpaying this miner I in the hash rate vector H. Okay? Now we have a collusion attack. Okay? If the real world is actually H prime, okay? So imagine before H prime had these Sybils, imagine now they're not Sybils, they're actually legitimate miners, each of which just happens to have a really low hash rate, a hash rate of 1. Well, if the rule overpays miner I in that first hash rate vector, then those H sub I hash rate 1 miners have an incentive to collude, fuse, join forces, and get that bigger than proportional rule in the hash rate vector capital H. Okay? So that's how the proof goes, and that's how the axioms kind of team up to give us the uniqueness result. The paper has various extensions. Let me just mention one. So you can poke the setup in a lot of ways. For example, you could relax budget balance, make it weak budget balance. Give the protocol the option to keep some of the reward for itself if it wants. Okay? This is now a bigger design space, so you could ask, can we escape the uniqueness theorem by relaxing budget balance to weak budget balance? And in some sense, yeah, I mean, the design space goes up at least a little bit trivially, right? If nothing else, you could sort of keep half the block reward for yourself and split the rest proportionally among everybody. That would satisfy the 3 axioms. More generally, this takes a proof, but it's true. You can scale the proportional allocation rule by any number between 0 and 1 that's a function only of the sum of the hash rates, and moreover is a non-decreasing function of the sum of the hash rates. So we call these generalized proportional allocation rules. It's proportional scaled by a total hash rate dependent function, which is non-decreasing. Turns out all of those satisfy all 3 axioms. And then theorem, there's nothing else. Okay? So if you're weakly budget balanced and you satisfy the 3 axioms, your allocation rule must have this form. There must be a choice of the function little f, non-decreasing, so that this is exactly how you're distributing expected rewards. Last technical thing I want to say, just a little bit about risk aversion. So one thing I've been sweeping under the rug this whole time is I've been assuming that miners are risk neutral. So for example, indifferent between having a 20% chance of getting the entire block reward or having a 100% chance of getting, deterministically getting 0.2 fraction of the block reward. Okay? So that's the risk neutrality assumption, which has been implicit in the discussion so far. You look out there in reality, there's plenty of evidence that miners are not in general risk neutral, that they're risk averse. There's multiple reasons you might want to join a mining pool, but certainly one of the biggest, if not the biggest, is to smooth out your rewards, okay? Like having an insurance policy, all right? So there's a standard economic model to talk about risk aversion. In our context, it basically says, don't think about miners acting to maximize their reward, but rather think of them acting to maximize their utility of their reward for some strictly concave utility function u. Think of it as like the square root function or the logarithm function. Again, intuitively, this model of risk aversion just says that all else being equal, miners are going to prefer certainty over uncertainty. Okay? So variance is a bad thing if you hold the expectation fixed. So observation is that if we actually relax our assumption of risk neutral and allow miners to be risk averse, our uniqueness theorem kind of turns into an impossibility theorem a little bit, in the sense that the proportional rule, which was always satisfying everything we wanted to, no longer satisfies one of the axioms, no longer satisfies collusion proofness, or at least the sort of standard randomized implementation of the proportional rule where you take a single sample from the hash rate distribution, that does not satisfy collusion proofness with risk-averse miners. Why? Because there's an incentive to form mining pools to keep their expected rewards the same while lowering the variance. That's going to raise their expected utility, so they will be incentivized to form those pools. Interestingly, we could also think about implementing, one more minute, yeah. We could also think about implementing it in a deterministic way. So remember we had this regime with 1,000 samples or 10,000 samples. One way you could use those samples is to actually split the block reward essentially deterministically. Okay? So that if you bring 30% of the hash rate, it's not that you have a 30% chance of getting everything. It's that you'll basically deterministically get a 0.3 fraction of the block reward. Okay? Once the rewards are deterministic, it doesn't matter if you're risk averse or risk neutral. The incentives are exactly the same. So for this implementation of the proportional rule, we recover the positive results, the positive part of the uniqueness result, and the proportional rule, again, works. Okay? And I should say a reviewer pointed out to us that you can sort of interpret fruit chain, if you pick the parameters properly, as a kind of implementation of this idea. So I'm out of time. I'll leave the summary slide up there, and then I'm happy to take your questions. Thanks a lot.
Any questions?
So in some sense, you are arguing for us to have a more sampled solution in this space, right?
I'm saying there would be benefits, right? So I mean, it's certainly a more onerous implementation. So I'm not going to opine on, you know, if the trade-off's worth it. But if you did in principle implement it, there would, I mean, so basically what this implementation does is it takes the functionality of a mining pool and it brings it basically into the protocol itself, which is sort of analogous to something known as the revelation principle for mechanism design, right? Because once the protocol is doing the mining pool work, all of a sudden there's no reason for me to join a mining pool. So one would have to decide whether that was, you know, worth the extra implementation hassle to get rid of the mining pools.
So this is really cool, but so what would it take to generalize this to also encompass Sybil selfish mining and those types of attacks?
Yeah, good question. I think there's various directions you could go. I mean, I think sort of the easiest next step. So if you think about it, what was I really assuming about how the blockchain rewards work? I was assuming that the reward is associated with a single block. Okay, and it doesn't matter, you know, so like the Ghost protocol or something would be outside of the scope of this. Or if you had a proof of stake world, then you kind of had history dependence, like staking or slashing. Again, that would be sort of outside the model. So to me, the natural next step is to try to capture the more complex way that rewards are distributed, but still try to get this kind of axiomatic characterization. Now, as far as the longer time scale, this is a fundamentally more complicated problem, because basically, you're now thinking about sort of an iterated game, a sequential game. And so that's just much more challenging. So we've had a couple sort of nice epsilon Nash equilibrium analyses of some specific protocols like Ouroboros and Snow White. I figure those have got to just be special cases of some more general theory, but we certainly are quite far from that theory at the moment. But again, 5 years from now, or maybe 10 years from now, I really hope we have it.
So one thing we are seeing now is all the miners go to where mining costs are cheap. So in Bitcoin, we now have 60% of the mining power in China.
Right.
Have you thought about relaxing the anonymity rule that it would allow to give more money to people that are, in this case, in not China or generally have other nice distribution properties?
Yeah, that's a good question. I have not. So the proposal was, you know, could you actually, you know, could non-anonymity actually be a positive thing? Could you use it to correct certain things you don't like about the hash rate distribution? I mean, you certainly could, and so you'd at least say, could I at least get, you know, the Sybil proofness and collusion proofness? And there are examples, so there are rules which would satisfy the first two axioms, but not the third. And one way you could do it is by sort of differentially penalizing people if you thought it was worth it. You know, doing this work, we kind of figured that was off limits. That seemed out of scope, but you could think about that. Yeah.
And one last question.
Thanks. So I'm wondering if it's actually going to make things somewhat simpler, maybe not simpler, but achieving the expected reward to be exactly proportional to the hash rate that you bring in is actually not that easy. So maybe looking into a long term, so not just looking at one block, but over many, many, many blocks, making a big number average out may be easier, because I think this is actually something that the mining pools distribution of the rewards, in some sense, this actually is like a lesson for the mining pool runners, like how they should distribute their mining rewards. And I'm sure you're familiar with the impossibility of the decentralization work in proof of stake system by Eugene Kwon and Yongdae Kim and Don Sung, and how they showed that the Sybil price, the amount of price that you have to pay when you Sybil your identity, has to be positive to compensate that Sybil proofness. I think that actually it applies here as well. So another direction that I think you can also go is to look at the price curve, like how much money you have to spend to get how much hash rate. And the curve is not linear, obviously. So if you consider that into that equation as well, then I think what this is actually saying is that maybe it is actually more beneficial for you to have multiple mining identities, spending that much money versus having one identity with way better equipment, so that if you can actually guarantee proportional rewards to the hash rate they bring in. So I think that's actually another extension that would be awesome to see.
Right, so just to recap the last point, I mean, so there's no modeling of investment in this model. Miners just show up with their hash rate however they got it. So that's another very natural next step of how to make this sort of more elaborate. And then it would be very interesting if there was any feedback behind your investment model and these results. I'm not sure there would be, but that would be interesting to explore. Yeah.
Thank you.
Okay.
And next we have Tarun Chitra, and a rather timely talk, given the flash lending things that have happened recently, is going to be talking about competitive equilibria.
Great. Yeah, thanks, Bram. So, as Bram mentioned, there's been a lot of kind of odd financial attacks that have taken place both in the DeFi space and also in staking. And I think this talk aims to show that the threat model for staking is definitively different than that of proof of work, and there are these financial attacks that you have to account for when you're trying to make a full threat model. So we're basically going to go through kind of a high-level overview with some kind of intuitive market dynamics, and then we're going to sort of build up an agent-based model that correctly kind of goes through all the different participants that are necessary to stress test these staking situations. Then we'll go through the assumptions that we make in the model, kind of break them down one by one for each of the different components. Then at a high level, I'll kind of give some of the formal probability proofs, the statements of them without giving any proofs themselves. And then finally, we'll go through some simulation results, which should basically give you a more comprehensive idea of how you can apply these types of tools if you are designing a monetary policy for a staking network. So overview and a thought experiment. So, proof of stake claims to have a sort of similar security model to proof of work. But in a lot of ways, the entire network security of the network depends fundamentally on the total quantity staked, as well as the relative value of that staked asset. And the relative value means that you need to make sure there are not many other alternative mechanisms for getting token-denominated yield outside of the block reward and fees. On the other hand, on-chain lending provides decentralized access to token-denominated liquidity. And you can kind of see this curve. The on-chain lending market grew from about less than $10 million in 2018 to roughly $1 billion. This metric is sort of a weird metric. I wouldn't take it too seriously, but it has grown significantly, as has crypto lending in general. But the key to this is that you have purely on-chain access to kind of non-censorable loans. And finally, in some sense, this security of these proof-of-stake networks can really be eroded from by this on-chain lending type of mechanism. Okay, so let's do a little thought experiment. So suppose you have a proof-of-stake asset, P. It's securing a smart contract platform. It's a Sybil resistance mechanism. There's an on-chain lending contract on this smart contract platform. The contract allows people to borrow and lend the underlying asset at algorithmically determined interest rates, and we assume that greater than 50% of users are rational and profit optimizing, so expected utility optimizers. So what happens if the interest rate that the lending contract offers is significantly greater than the staking rate? Well, if you're rational, 50% of users are suddenly going to move their stake unbond and kind of go into lending. How could this happen? Well, when the price of P crashes relative to a secured asset, like a numeraire, like dollars, Bitcoin, the demand to short this asset will go up. When the demand to short goes up, that means the borrowing interest rate goes up significantly, and then the interest rate for lending goes up, and that can kind of lead you to this deflationary spiral. Now, that's sort of the high-level idea. But, a natural question is people saying, like, would this actually happen? Can this happen? So, as Bram pointed out, there have been a number of attacks in the last week that have kind of proven that there are rational actors, and once there's enough money in the purely on-chain financial system, people will start taking advantage of these things. This would actually sort of, why restrict this to on-chain lending? Why not think about centralized lending? The key is that the censorship-resistant nature of these lending pools means that you can't really stop people from unbonding and moving their assets into these pools and taking that yield. The other question is fees that validators, fees for doing this attack should probably spike around the time it's happening. While that's true, there's kind of like it's actually quite hard to predict miner and validator behavior with respect to transaction fees, as this paper by Narayanan et al. Shows. The strategy space is actually quite complicated and has a very complicated phase diagram. Exchanges and validators won't let this happen. Well, okay, at that point, then why don't we just have the exchange run a database for you? And the last thing is, do rational lenders or rebalancers actually exist? And this flash loan type of stuff in the last week has kind of shown that. So in some sense, this is really a bank run on a proof-of-stake network. So let's get some intuition for why this doesn't happen in proof of work. So proof of work is really secured by what's known as miner extractable value. It's been kind of analyzed in a variety of different circumstances. But we can break that down into two main components. One is the hash power committed to mine the next block, and the other is really, as Tim was just talking about, the economics and fees of the proof of work asset. The components are not interoperable in proof of work. You can't directly convert hash power to the proof of work asset in kind. You need an exogenous asset. You need a hash power derivative, you need an oracle, you need something else to actually connect the proof of work asset to the hash power directly. In proof of stake, that's not true, because the same asset that's securing the network is also the asset that you're using for transactions, e.g. loans. And this is by design. If you look at kind of the first Bitcoin talk post on proof of stake, the idea was, hey, let's take the limit of constantly reinvested proof of work, where you can immediately reinvest your block rewards, and you earn fees with this virtualized hash power. So in some sense, you cannot trustlessly lend proof of work security, where you can trustlessly lend proof of stake security. Okay, so how do we talk about this in terms of models of users, rational users? Well, I think I think every single presentation I give, I always use this quote, but I love this quote by Matt Levine, which is basically cryptocurrency just basically relearns the lessons of finance's past, but maybe at 1000x speed. And so we can kind of go to models from finance for how people model cascading failures and bank runs to give us an idea of what to do. So the thought experiment reveals a little secret. In some sense, rational actors are really solving a portfolio allocation problem at all times in staking. They're really saying, hey, I have a portfolio of staked coins, and there's K ways that I can make yield. Some of the ways include staking, other ways include lending, other ways might include more esoteric things like staking derivatives. But at the end of the day, the rational actors are constantly rebalancing their portfolio and trying to optimize this. So let's suppose that everyone views their entire portfolio of staked assets as a portfolio of staked assets or lent assets. And there's kind of two different interest rates that are competing, and we also model the agents as having different types of risk profiles. So one risk profile, when you're very risky, is basically having a rebalance policy where the moment the interest rate spikes in on-chain lending, you move all of your assets from the stake supply to the lent supply. A more risk-averse user of the system would maybe say, oh, okay, look, well, if the interest rate in the lending contract is only 5% greater than the staking contract, I'll only move 5% of my assets. And so that's these are kind of the two ends of that spectrum. So one of the simplest ways to kind of model these portfolio reallocations and rebalances is modern portfolio theory, pioneered by Markowitz in 1953. But there's roughly $5 trillion of US assets that sit in this. So like you go to any quantitative hedge fund, like this is actually how ETF portfolios are rebalanced, this is how equity portfolios are rebalanced. And it only requires 2 real inputs. That's like the nice thing about these models. So they're kind of simple and interpretable. One is sort of the alphas, which is the expected return over the next period. And the other is the covariances, which is basically the covariances between the assets and the volatilities of the assets themselves. And you solve this problem by doing a very simple thing. You have a strictly convex function. The value x is the portfolio weights. So x you can think of as a vector on the probability simplex. It tells you the proportion of each asset you hold. So you solve this strongly convex problem given those 2 components, and then you're done. So we define rational staking agents to be those that optimize their individual belief based on these risk preferences and expected rewards. On-chain lending. So I'm not going to go through the whole mechanism of on-chain lending, like how this works and how these systems can stay stable, or have stayed stable so far. But this number of 215 million was taken from this morning. So Compound has around 215 million, so roughly 10% of, say, Celsius or BlockFi, which are the main centralized lenders. But from the end user perspective, the way that these on-chain lenders work is there's a smart contract. The smart contract has a pool of assets. People who lend their tokens to that pool get paid interest on every block. People who are borrowers put up collateral. So let's say I lend a stablecoin to this pool. Someone who's an Ethereum whale wants to borrow $100. They want dollar liquidity. So they collateralize a loan by locking some Ethereum up, taking out the stablecoin, and then paying it back over time. If there's a default, basically the lending pool socializes the risk in the sense of it's shared pro rata. Now, how are the interest rates computed? They're computed by what the cryptocurrency community calls bonding curves, but has existed in algorithmic game theory for almost 20 years in market scoring rules. And these rules basically take demand and supply, take deterministic functions of those, so how many tokens people want to borrow, how many people who want to lend, and compute an algorithmic kind of interest rate. In this case, in Compound, they define a utilization rate. C is the demand, L is the lent quantity, and it's between 0 and 1, and then you can compute these interest rates from that. A minimal viable proof-of-stake model. So as Tim said earlier, you should always really be thinking of all of these types of things in cryptocurrency as sampling probability distributions. And you could kind of think of each block produced, each block update, as sampling the stake distribution and then updating it. In a lot of ways, this resembles, if you're familiar with sort of statistical learning, like how you construct Dirichlet processes and things of that nature. So, but we'll simplify it and just have 2 state variables. So one is the reward schedule, which is the block rewards at height h. The other is the validator stake distribution at the current epoch. So we sample a proof of stake trajectory pretty simply. We draw a set of block producers based on the probability distribution. For each block, we sample a Bernoulli random variable to define, which sort of says there's a static slashing probability to decide if the block producer is slashed. And then, given those block rewards, we update the validator distribution and continue. But what assumptions have we made? Well, so first of all, let's talk a little bit about why we have to make some assumptions. So modeling these kind of like complex systems with many components, right? There's many agents, there's the staking network, there's the lending protocol. You have to make assumptions to kind of like be able to both reason about these things and also to have formal results. These assumptions will deviate from reality, but the idea is if you can explicitly state everyone and where you use everyone in a similar way to the axiomatization of block rewards, you can slowly relax them and then go to simulation or numerical methods to try to optimize for different things. So the things we don't handle really are unbonding times, staking derivatives, delegation, and locked rewards up front. But with these assumptions, we get this model that gives us formal probability proofs. So these are classical Doob-style inequalities. There's a phase transition. There's a way of measuring volatilities. And you can slowly relax each of these assumptions to get them to be more realistic. So the goal of all of the model assumptions we're going to describe is to remove all sources of variance and noise that arise from factors that are not rebalancing. So the proof of stake assumptions: fixed number of agents, synchronous communication, money supply is deterministic, no transaction fees, no immediate compounding, single validator per block, and no explicit unbonding period. And basically, these descriptions of these kind of conditions explain why they're all variance-reducing assumptions. And these two pictures are just of two very different kind of proof of stake. One is the ETH2 emission, and one is the Celo emission, and you can see that there's kind of like, they sort of violate some of these. What do we assume about our agents? All pseudonymous identities are known by all validators, so it's just more that, you know, every validator is assumed to have a synced blockchain at all times. Agents cannot choose the order of their transactions. There's no miner extractable value from you being both a miner and a rebalancer. Again, we're kind of, this is to reduce the variance of mempool type of mempool sniping gas auction. Agents draw their risk preference from a static random matrix ensemble. If we're at equilibrium, if there is an equilibrium, then the risk preference distribution should be stationary. If it's not, then we're not at equilibrium, so that's kind of an assumption. The agents choose their risk, their volatilities based on the expected epoch time and the expected time that a loan takes. And we always assume that there is a fraction, this is a model parameter of delta, of altruistic validators who are always staked. And the reason for this is that if there's not some fraction that's staked, then the lending transactions can't go through, and you just, you know, the system's not running. Finally, lending assumptions, no external market. Again, that's kind of variance reduction. We assume for the formal proofs, we make this assumption that there's a constant relative demand relative to the money supply. For the simulation results, we actually simulate different borrowing demand distributions. And the flows in and out of the lending contract are the only things affecting yield. In real life, that's not true because there's staking derivatives, et cetera. So the formal proofs. So you know, I want to give a disclaimer based on a review comment I got, which is don't drown the audience in any math. So there's this very famous paper by John Carty on Schramm-Lohner evolution for theoretical physicists, where he tries to tell mathematicians not to read it. So I redlined it a little bit for you. And this will be the only slide that uses the word martingale. So 3 key results. Lending supply volatility, uniformly bound staking outflows. So the idea is that the stake distribution fluctuations are completely controlled by the lending fluctuations. The second is that there's this phase transition where the lent supply kind of goes from strictly growing, so like it eventually maximizes, it saturates, or it kind of like oscillates between like being lent and not lent. And so we'll see some pictures of that so it's clearer. And then the last thing is deflationary monetary policies provide poor staking returns and eventually everyone goes to lending. So the key variables we have here, we have the lent supply, we have the change in lent supply, we have the money supply, we have the change in stake, and we have the 2 temporal parameters, we have the lending rate, and then we have this fraction of altruistic state. All right, so claim 1 is basically if the inflation rate is greater than the expected stake epoch time, the end, basically at all times, all validators have non-zero stake, then the fluctuations in the stake distribution are uniformly bounded by the fluctuations in the lent distribution. The next thing is this phase transition. So basically, this phase transition says there is a lending rate at which basically, if the lent rate is below this value, eventually the total lent quantity goes to 0. There's kind of an upper bound where if the lending rate is always in between these 2 parameters, you basically never have the stake supply completely lent, and you never have the lent supply at 0. And then if the interest rate stays above a certain number, basically the lent supply goes to the maximum saturated value. And the last thing, which is for this deflationary thing, it basically says, if you have a deflationary monetary policy, Bitcoin-like, then you're going to have rebalances that are greater than the altruistic amount staked with high probability. And if you have polynomial or inflationary schedules, then the rebalances will kind of be negligible. And there's some technical reasons for choosing this delta, but this kind of gives you like an idea of like what you need to do. Simulation results. So we kind of model different demand distributions. We have a more clear view of staking. We have different parameters for the risk and for the interest rate curve and compound. So we do Monte Carlo simulations of those. And what we do is we kind of take these Skorohod clamped geometric Brownian motion processes. So Skorohod processes, if you remember, are things that have reflections. So take an Ito process, reflect it at boundaries. So kind of like this. That's why it's called like a clamped process. And the idea is you can model different properties of the token distribution. So you can say, okay, this percentage is locked at this time. That represents the lower bound. You can also talk about margin. When there's margin trading in the system, that the demand can go higher than the supply. And what we see is this is the heat map of the staked supply minus the lent supply normalized by the total money supply. And the x and y axes are the interest rate curve parameters for compound. And we see that basically when it's yellow, that means we're like quite staked. Like there's way less that's lent. And when it's purple and pink, it's actually basically at purple it's negative, and pink it's basically about even. And you can see as we increase the inflation rate, we slowly move the expected quantity. And each of these points represents 1,000 samples. And with different inflation policies, you can see how homogenized this is regardless of inflation. And then the last thing is this oscillatory thing with the phase transition. You can basically see in the left case, this is what happens when everything goes to the lent supply. Here we say there's 1% altruistic. And then in the right case, you actually see this kind of oscillatory behavior. Conclusions. A monetary policy of a proof-of-stake network needs to account for on-chain lending, fundamentally. Capital can always be cannibalized by other forms of on-chain yield. And the censorship-resistant nature of on-chain lending basically means you can't really stop this if, unless there are admin keys, as we learned in the BZX attack. We kind of formally demonstrated for this constant demand model, and we also looked at kind of other demand distributions to kind of show that there's even for more realistic, like the Skorohod type of processes, that things kind of match what the theory says. POS networks really look like central banks much more than POW, fundamentally, because they have to adjust their monetary policy based on real lending activity. That is exactly the same as repurchase agreements and like how overnight lending works. And deflationary policies seem to be way more detrimental to proof of stake than proof of work. So what do we have to do for the future? Improve the simulation to reflect some of these more realistic conditions. Add in more models of transaction fees to show that there's a certain kind of level of burstiness that you need. It can't be this like autoregressive type of process, and transaction fees to kind of get it to account for this. Add in other forms of leverage. In this BZX attack, there were a lot of wrapped tokens like IETH that were involved. One question is if you have a proof of stake asset that's in a wrapped token and a significant supply is wrapped, can someone kind of execute some type of weird lending attack? And then the last thing is add in effects from sharding, which obviously complicates these types of things. And thanks to all of these people.
Do we have any questions?
So have you looked into the possibility of the monetary policy being related to this issue? So instead of, say, defining a staking rate that could be exceeded by lending, you could instead have a proof-of-stake blockchain whose parameter for staking was basically an economic value or a quantity of staking, and the staking rate would fluctuate according to a bonding curve or something else?
For sure. A lot of people's designs, so like in particular, like the ones I know the most intimately, like Cello, they just kind of toss this to governance. So like people can vote on updating, almost like Maker, where it's like, that is really central bank-like, right? Where it's like strictly adjusting the monetary supply. The other types of things you could imagine, which I would caution against, are really the staking derivative type of things, where people borrow against their staked quantity. They seem very, validator pools seem to really want to do this right now, but I would say, you might be able to get around lending being the primary activity by making the protocol have a lending protocol built in at the base protocol level, which is what a staking derivative would do. But it's, you know, I don't know. Choosing those parameters seems very, very difficult. I wouldn't want to be tasked with that.
Hi, Tarun. So you had previously mentioned that the POS system very much mirrors central banking functions and repurchase agreements, so repos. Could you give a little bit of more intuition behind that claim?
Okay, yeah, sure. So basically, you know, a central bank sets a main interest rate. So let's say they set like the current Fed funds rate at 2.25% or something. Then basically every day they observe the total kind of like lending activity that takes place, as well as sort of, you know, how much individual banks are involved in money creation. And then the central bank adjusts, basically repurchases bonds from the wholesale market to try to make the interest rate match the target rate every night. So banks do money origination, they do the money origination, and then they basically they have these accounts at the central bank. Those accounts, based on their inflows and outflows, tells you like the net lent quantity in the system, roughly. You can approximate it. And based on that, the central bank adjusts how many bonds they issue or buy back in accordance. So it's very similar to these kind of like governance to account for lending quantity type of behaviors.
Last question. I guess we're... Actually, I have a question. Are we going to imminently see a collapse of things based on these sorts of issues?
Yeah, but you know, it's going to happen 100,000 times faster than it did in the normal world. So it's cool.
Next up are the lightning talks. So if you have a lightning talk and send you the deck, then please line up in the order of your talks. And so these lightning talks are going to be at most 2 minutes each, and I acquired, let's see whether this works. I will use this to send off the speaker if they go over, so please move along quickly. And feel free, and you know, maybe 30 minutes, we'll have some lunch outside. You can grab some lunch, but please don't have conversations inside and be quiet and respectful to the speakers.
Can you go to mirror? You need to go to mirror.
Okay. Isn't normally this? Does it automatically?
Go to mirror.
Open display preferences. Mirror display.
Excuse me, I just submitted one at...
Sorry, it's too late. I cannot change that.
Can we plug in our own computers?
No. So, and here's the speaker, so you can use that. So, if you please line up, make sure that you know the order of the talks, and please line up in that order, and let's go start. So, yeah. Thank you very much.
Hi, folks. My name's John. I work at Chaincode Labs in New York. We are a non-commercial Bitcoin research and development group. All of the work we do is open source, and we are hiring. So if you're a researcher, more specifically, if you're a cryptographer or a mathematician, or you're an engineer and you want to work on cool open source Bitcoin projects, apply. Chaincode.com, or just come and talk to me. Second announcement is we are running our residency program again this summer. This is the 5th time that we've run a residency. It is for developers who want to get started in Bitcoin protocol development and Lightning protocol development. Free of charge. We have travel and accommodation stipends on a case-by-case basis. Again, if you're interested in that, if you love Bitcoin and want to work on Bitcoin protocol development, come and talk to me or go to residency.chaincode.com. Thank you.
Okay. Hi, everyone. My name is Kate Sills, and I'm a software engineer at Agoric. And today I want to talk a little bit about a smart contract that I've been building on our platform that's called Zoe. And let me back up a bit. So what Zoe does is it introduces this, this new safety property that we call offer safety. And what it says is that a user is guaranteed to either get what they want or get a full refund of what they put in. Okay? So I don't have time to go through how this works entirely, but just to give some of the details. So Zoe is a smart contract. There are smart contracts that run on top of Zoe that have particular business logic. So it might be an auction, it might be a swap, it might be whatever the business logic is. But users escrow their digital assets with Zoe. They never give their digital assets to the business logic smart contracts. And the smart contracts are only able to communicate with Zoe in terms of information. So they never actually get access to the assets. They tell Zoe to try to reallocate the account balances. And at that point, Zoe tries to enforce the offer safety invariant. So we think this will really drive rapid innovation in smart contracts. And if you're interested, feel free to Google it, Agoric Zoe, or come talk to me. Thank you.
Hello, my name is Jan. I'm CTO at Arrow Labs. At Arrow Labs, we started from the premise that cryptocurrency and blockchain is a really daunting and mysterious thing for the average consumer in the general public. So the further away we get from this room, the harder it is for people to really grapple with it and use it. And we think that consumer crypto, though, will be the thing that really blows up the market value of cryptocurrencies. And just to give you an idea, I posted here the total percentage of the global population using the internet, starting from about 25 years ago. And just to show you that crypto today is still at that sort of sub 1% level that the internet was 25 years ago. And so our challenge is really, what do we do to make the cryptocurrency and blockchain space something that consumers can approach and actually not be daunted by? And so one piece of the puzzle that we've come up with is actually to give people the power of a locksmith on a smart card. So we actually are distributing to our customers smart cards that actually have elliptic curve key generation on card. And this is something that makes it very easy for the general public to have under their control something that allows them to have relative parity to the members in the audience today who can generate their own keys with confidence. So we think this is one little step along the way, and we hope that you join us as we try and figure out what consumer crypto is going to be like.
Is this? I don't know. Is this Nope. Oh, okay, go ahead.
How to play back?
Yeah.
Okay, sorry. Okay. Where is the back?
On the left side.
Left. Okay.
Just left and right.
Okay. So seems it's not working. It's not working. I press in left. Oh, okay. Okay. Hi. My name is Igor. I am building Zerapool and tell about circuit of private transactions in Ethereum. We have two inputs and two outputs in our circuit. It is join split transaction. Here is the properties of input, token ID, token amount, native amount, owner, and salt to make an input unique. Purple is private data, green is public data. We pick with Merkle-proof picker leaves from our anonymity set. Also, we're using ECVRF to compute nullifiers. ECVRF is like non-malleable
elliptic curve signature, so we can use it for nullifier computation to create unique nullifiers. For example, we can build it in hardware wallet, and after that, put ECV array of nullifier and proof to a proving machine. Here is some checks for a native token and another tokens. Now I will tell how to build atomic swap, private atomic swap with tokens. We have Alice with n token 0 and Bob with m token 1. The first Alice compute n token 0 belong to Bob, transfer the data to Bob. After that, Bob create a transaction, moving his tokens to Alice and send the Alice this transaction. After that, Alice make paired transaction and execute. Thank you.
All right. Cool. Hi guys. My name is Ram. I'm an engineer at Alchemy, and I'm here to talk about scaling blockchain infrastructure. One thing Alchemy does is we're an infrastructure and developer platform. We power about 4 million users in over 197 countries and power a large chunk of the top Ethereum applications. So let's start with more traditional applications. So when Facebook, let's say they started with 1,000 users, they were able to just put all their traffic through a web server. When they upped it to 1 million users, they were able to just like scale the web servers, split the traffic. This is because all the web servers had the same copy of the data, and it was easy to do. And I know I'm oversimplifying it. I'm sure Facebook does more complicated things. Whereas when you get to blockchain, if you have a bunch of users, and let's say you're running a bunch of nodes, the difference is that each node has its own copy of what the network is. And so let's say a user makes a request to get the latest block number, and it sends it to node A, you would get a block number of 5. And then later, the user tries to get information about that block, and it gets sent to block B. But block B is only on number 4. So then this creates a problem, and the user is very confused. So you can imagine if you have some sort of crypto wallet where someone sent you $1 million in ETH, and it gets processed on block 5, and you see $1 million in your account, and you click refresh, and then all of a sudden it's gone, because it's just gone to the wrong block. So this is just a small example of a consistency issue that generally blockchain developers deal with. And at Alchemy, sort of, we've built robust infrastructure to deal with some of this. Obviously, I only have 2 minutes, so I don't have time to get into this. But please find me afterward, and more than happy to talk about that and a lot of our dev tools as well. So here's my Twitter and email. Thanks, guys.
Hello, I'm going to talk today about one number theoretic function which I believe to be the simplest one-way function, and whether or not it can be used for creating an entirely new public encryption or not remains to be seen, but I would like to introduce the idea. One possible application, obvious, is related to the first talk today about fast generation of RSA keys. We know very well the factorization problem. This is RSA 768. It takes huge efforts to produce the 2 prime factors, but at least it's possible. The question is, can we radically change this and go from one extreme, from primes to number with really small prime factors, so-called smooth numbers in number theory, and from multiplication to addition? So the question is, if we add 2 smooth numbers, is there a chance, and they are mutually primes, is it possible to decouple them? If the answer is no, we don't know, that would create probably the most simple one-way function that we can hope to have. And here is one conjecture, which if we restrict the largest prime factor to be log n to the power of k for k slightly more than 2, then very likely every number can be represented as the sum of 2 smooth numbers, which I call anti-Goldbach conjecture. So the question is, so there are several things you can use with this. First of all, if you add 2 mutually prime smooth numbers, you can guarantee, and they contain all the primes, all the prime factors up to a certain limit, you guarantee that the sum is not divisible by all the small primes much quicker than the Chinese remainder theorem approach outlined. That's one thing. Another thing is that there is a theorem saying that every one-way function can be used to build a random number generator. So how this a potential one-way function can be used is really interesting to see. And lastly, can we build a radically new, completely orthogonal to the RSA's encryption system? Okay.
Hello. I just wanted to advertise this result that I have with my PhD student Paweł Kędzior. It's about a new way of splitting payments in the payment channel networks. So if you remember how payment channel networks work, for example, Lightning, you have a group of parties and they want to send money between each other. So say they send it from left to right. So 2 coins go like this, right? And then this guy receives it. He gives a receipt that goes back. A natural question is if you can divide payments on the way. And that's what we do in our recent paper. So it would work like this. You have these 2 guys here. One would send 2 coins to the neighbor. And then instead of just sending 2 coins further to the right, this guy would send, say, 1 coin to one of its neighbors. And then maybe think a little bit. Maybe there is some more capacity in the network available. So then spontaneously, depending on the situation in the network, this guy can send it to another guy, like the remaining 1 coin, right? So there were 2 coins sent, and they were split ad hoc or spontaneously into 2 payments. And then, for example, this can go further to this one. So there will be a receipt. This will also go further. There will be a receipt. And a nice feature of this protocol is that the receipts can be aggregated. So this guy here can aggregate these 2 receipts and into 1 short receipt and send it back to the sender. Okay, so this is the novelty of this approach. And if you want to see more, then just go online and see this paper, or just ask me after this talk. Thank you.
Hello, everyone. I'm Bharat from Infosys Consulting, and I have Vaibhav from Matic Network. We're going to talk about, we are working with Matic on layer 2 scaling and the solutions around it. So we have seen this problem in most of the side chain. The side chain is pretty much governed by a single operator, and the users have a problem from exiting from the chain. So we are presenting this idea of censorship-resistant optimistic roll-ups. So if you're interested, please talk to us after the talk. Vaibhav, you want to?
Yeah. So the basic idea is that L2 solutions suffer, like they don't really care about decentralization, and that's where we get the scaling from. But this has some other issues that the single operator can censor some user transactions. For things like Plasma, this wasn't really an issue because we had things like which would allow users to go on-chain and still execute their transfers or withdrawals. But for things like optimistic rollups and ZK rollups, this is a problem because withdrawals happen on the sidechain and not on the Ethereum smart contract. So any operator can actually censor a particular user's withdraw transactions and have them not leave the chain at all. So the solution we have are actually 3. Either you have multiple operators, either the user who is getting censored, he puts up the stake amount, and or the other idea that we have here is that a user just goes on chain and submits his transaction bytes and forces the operator to include this transaction in the next batch. Yeah, that's it. Thanks.
Consumer IoT adoption is on a hockey stick growth curve. Amazon's creepy doorbell camera Ring sold 400,000 units in December 2019 in the United States alone, up 3 times from the year before. Google's Nest, Amazon's Ring, and Wise were all involved in successful headline-grabbing attacks in the last 6 months. Those attacks had 2 flavors. 1, server-level breaches, Wise, and 2, password breaches from brute forcing or harvesting passwords off the deep web, which was Google's Nest and Amazon's Ring. The problem is not that existing consumer IoT architectures expose consumers to enterprise-level security threats. It's actually a much deeper problem than that. The advertising business models of big tech are based on extracting and analyzing data every time a user generates a data point from their IoT device. IoTeX is offering a solution by bringing decentralized, user-owned identity to the consumer IoT market with our first product, UCam, a home security camera. Retailing for less money than Amazon's Ring or Google's Nest, UCam uses a unique DID model to serve as a single key end-to-end encryption architecture. DID, you can think of it as a data locker on wheels. The data locker can go anywhere, but only the user has the key to unlock it. This eliminates server-level data breaches. DID is also used for password login. It's a private key that's held under root access on the user's phone, and it's used for all login. DID and UCam is about a lot more than just giving users access to the data control and also eliminating password breaches. It's a complete inversion of the data collection business models employed by big tech. UCam is just the beginning. We're rolling out DID to every IoT consumer IoT product on the market. I think that giving data privacy controls to users in IoT is one of the biggest problems of our time. Thank you.
Hello, Vincenzo Nicola, co-founder at Conio and proud CS Stanford alumnus. So what is Conio? Conio is a startup mainly based in Italy that strives for ease of use and safe custody of cryptocurrencies for normal people. Now, as you know, the main strength at the same time the main weakness of cryptocurrencies is that you're in control, which means you're in control, but at the same time you can lose control. And whenever you lose your key, I can tell you it's not pretty for a normal person. So from the get-go, we developed a solution, a multi-signature solution, 2 of 3, where the customer has one key on their smartphone here, Conio, our company, has another key on their servers, and then there is a third key on a third-party offline server, can be a bank, for example. Now, 2 keys out of the 3, normal situation, the key of the customer plus the key of Conio, you move the fund. If something happens to the customer loses the phone, the customer forgets the key, or the customer, knocking wood, dies, things happen. At that point, the customer or the heir goes to Conio. Conio verifies the customer is entitled to recover the funds. And at that point, the Conio key and the third-party entity key, 2 keys out of 3, you move the fund of the customer to a new wallet of the customer. Same thing if Conio disappears, hopefully never happens. But at that point, the customer can go to the party entity, the bank, and at that point, 2 keys out of 3, you move the fund to a new wallet. Now, this approach, this multi-signature approach, works very well with Bitcoin. Bitcoin supports multi-signature natively. It does not work with other cryptos like Ethereum. And for us, I mean, we think it's a bummer, a major problem. And we thought, how can we solve this? So we leveraged at the point this concept of threshold signatures, and we were able to create this layer, or we call it multi-signature virtualization layer, with the same entities that, as I told you before, user, Conio, and the third-party offline entity, which is a bank, for example. They work together with rounds of multi-party computation, and underneath you see only a single signature transaction. So the blockchain underneath can see only a single signature transaction, but on the top there are multiple parties. So multi-signature for ECDSA and EDSA. Thank you.
Hey, so I'd like to talk about Nodal today. We are basically a network, a global decentralized network to connect IoT devices. We can do that to connect assets that we call smart assets. We have a network stack to secure them. And eventually, we can provide insights. So, if you operate some location and you want some insights on what's happening in your location, we can provide that to you. Our network is global today, so we are basically everywhere. And we're currently building on Stellar. And by building on Stellar, we went over 1 million transactions a day on the network, only with Nodal. Today, we are extending our network with a new set of technologies and tools that we build on parity substrates to remain compatibility with Stellar. And we are planning to add multiple features like zero-knowledge proof or various privacy-preserving schemes. So here, we are here today to eventually talk to you if you have such kind of technologies, if you want to discuss about it, think about it, or just try your app and see what we can do. Thank you.
Hi, hello. My name is Jingyue Li. I'm associate professor from Norwegian University of Science and Technology. Here I'm going to introduce a project we just got funded. It's a project to be financed by the Norwegian Research Council and by the Ministry of Science and Technology in China. So the project will last for 3 years and will start from April. And the Chinese fund is around $1 million and the Norwegian fund is around $3 million. So the background of this project is that Norway exports a lot of seafood to China every year, and we have found a lot of cheatings in the supply chain of seafood. One example is that the serial number of the package of seafood can be reused. So Norwegian food is packed with a box and with a serial number. Serial number will indicate where the fish comes from. And some sellers, they buy one box of Norwegian seafood and get the serial number, and they copy the serial number into 10 boxes and put fishes from other countries or from other places and sell them as Norwegian seafood. It is because Norwegian seafood is often more expensive. That's the motivation of doing this kind of cheating. So another scenario is that the seafood has been transported by using refrigerators, and there are sensors in it, but the sensor data have never been shared to the users, and the user will never know whether they bought fresh food or not. So the purpose is to fight the cheating of this supply chain, but we also want people to trade the seafood by using cryptocurrency because there are a lot of small players in the picture, and they need to pay each other across borders. So we hope that by using cryptocurrency, we can save a lot of transaction fees for these small players when they trade across countries. So there are a lot of interesting research challenges in this project. If you are interested in that, please contact me, and I'm looking forward for the collaborations. Thank you.
Hey guys, I'm here to talk about two things. The first thing is a company that I co-founded, and the second thing is a podcast that I currently run. So regarding VDF Labs, VDF stands for fast in French. We are a layer 1 public smart contract platform, and our flagship product is a decentralized exchange, a true decentralized exchange with on-chain order book and on-chain everything. So as long as an asset is natively VDF, then it can trade with almost near centralized exchange user experience. So we're currently bootstrapping liquidity, and so if you're interested in checking out the platform, feel free to do so. The website is vitex.net, V-I-T-E-X.net at the bottom. And if you're interested in finding out how this came about, so the Vitex is built on top of VDF, the protocol. We're basically a modification on top of the block lattice ledger structure of Nano. So you can think of us as Nano plus smart contract. Separately, we also have a multi-chain wallet that supports VDF native coins, ETH, ERC20, and GRIN. And one way for us to acquire customers is actually supporting GRIN, which is notoriously difficult to support in terms of mobile wallets. So the second thing I want to talk about is a personal passion project of mine. It's called the Blockchain Debate Podcast. So there's tons of blockchain crypto podcasts out there. The conversation is generally one way. The hosts do not have the knowledge or the courtesy, or I guess the lack of courtesy to challenge the guests that come on. And I feel there's so many different sects within the space. Everyone believes what they believe, and very firmly so. So an interesting thing to do is to get them to talk to each other, and the rest of us can watch, observe, and then make decisions, make up our mind as a result. So anyway, so we got all these different guests, and we have very interesting episodes coming up. Check it out. Thank you.
So good afternoon, everybody. I want to go back to the foundations. We have an amazingly diverse audience of academicians, blockchain entrepreneurs, economists, developers. But all of you, I think by now, know about Byzantine failures. Did anybody in the room not hear about Byzantine failures? Raise your hand. Super awesome. So, at the core of blockchains, like the Libra blockchain and others, is a mechanism for driving decentralized agreement, decentralized trust-based agreement on the history of payments. And this core problem received attention for over 4 decades and was accelerated due to this killer use case of crypto-economic systems with tremendous results. One of them is a technology that I was involved in, the hot stuff technology that drives linear agreement in face of Byzantine failures and is at the core of blockchains like Libra and others. But at the same time, everybody we talk to never tested for all possible infinite number of failures that can occur under the Byzantine model. And that's almost a tautology, an axiom. Can you test for all possible infinite behaviors? Nobody has actually experienced in their mainnet a Byzantine attack. So we are now looking beyond Byzantine and kind of double-clicking on Byzantine and asking what type of corruption failures or compromises actually happen in practice. And we're looking at a number of dimensions. This is not an exhaustive list, but for example, timing faults where everything else behaves according to usual, but you only have asynchrony. A model that we introduced in a paper, ABC, and various other testing strategies for shades of Byzantine faults. Thanks.
Hey guys, I'm also Calibra, so I work in the cryptography team along with my colleagues Payman, Kevin, and Lera, and actually we're announcing our plans to actually have an RFC for proofs of liabilities. And if you don't know, the problem is very basic and very easy to understand. So imagine you have a bank, a wallet, or an exchange. There are users in this exchange, and actually your balances are accounting records in some database. And let's assume we want to prove that this bank or the wallet or the exchange is solvent. They have to prove to us if everyone tries to withdraw their money, they will be able to sell their assets and they will pay back. So this is a problem we're trying to solve, and actually we're focusing on the blue database thing, so only on the liabilities part. The thing that we didn't focus on the assets is because it's different per asset. So it's a different thing to prove solvency for Bitcoin, for Zcash, for Libra, for anything else. The nice thing is that we actually build on top of provisions. And I ask you to actually read this paper. It's very interesting. And the Maxwell protocol as well. So we created a tree structure of provisions. We added some extra plugins on top of it, like KDFs and VRFs to have some deterministic shuffling. So you cannot put all of the users from the right side or of the left side and actually remove some checks and the balances. We use sparse Merkle trees. We add padding on this because previously we had the problem where the auditor or people who were checking the proofs knew the size of your database, why the wallet should expose that we have 1 million users. And we're also adding some new features because from theory to practice, we realized the auditors require tools to be compliant with the regulations. So they need to do sampling as well. So we had to add more information on this. Some more interesting applications. I don't think it's mentioned in the provisions paper, but it's not only for solvency. You can even use it. You can see the last bullet point, even for corona proofs. Do you believe that the numbers announced now are actually real about the infections? If we had the way, these are liabilities as well. If we had the way to actually, for every infected person to prove, I'm included in this advertised number of 70,000 or 80,000. So it's exactly the same problem. Thank you.
Hello all, my name is Jyoti Panapalli and I'm here representing DTCC. DTCC is the Depository Trust and Clearing Corporation. We are a premier global financial markets infrastructure provider. We provide governance, risk management, and operational efficiencies to the financial industry market, regulated markets. DLT, as we know, provides a variety of value propositions to the financial industry use cases. And along with the potential enhancements it brings, it also brings along a unique set of risk profiles and security exposures that cannot be addressed using traditional cybersecurity frameworks. The DLT landscape, as we know today, is in a fragmentary environment with standards and guidance. Organizations are navigating across this landscape in a very siloed approach. Owing to that, in lieu of that, DTCC published a white paper, and we just released it last week, in fact, called Security of DLT Networks. It is calling upon the financial industry stakeholders to come together, contribute, and collaborate to build a comprehensive DLT security framework for financial services industry. To bring along standards along the way, and standards that streamline governance, talk about agreed upon terminology, as well as ensure that interoperability exists and it doesn't remove the risk of fragmentation within the ecosystems. So I encourage everyone to read the white paper, and please reach out to the contacts published on the last paper, on the last page, if interested in participating in the consortium. Thank you.
Hello, my name is Qi Zhou. I'm the founder of BlockChain. We are building next generation blockchain technologies using multi-chain sharding technologies. And so one project we are actually currently working is sharding Libra, which by applying sharding technologies to Facebook Libra. So Facebook Libra is a prominent project that aims to bring financial services to all billions of unbanked people. However, it has several concerns in terms of, for example, performance. It has limited scalability with roughly 1,000 transactions per second. It is permissioned with roughly about 100 validators. And also it is lacks of flexibility in terms that actually it's highly tied to move language and also Libra BFT. So we found there's a huge improvement that can be made to Libra by utilizing sharding technologies so that we can achieve greater scalability and decentralization without compromising security and also slightly latency. So by running multiple blockchains, we can easily achieve more than 10 times or even 100 times performance improvement. And we are also be allowed running these shard chains to run different consensus so we can encourage more people to join the network and contribute blocks. And also, we can employ this greater flexibility so that we can enable heterogeneous chain interactions, for example, by moving the Ethereum resources access to, for example, move resources. Especially, we also found actually move language itself is very good fit for sharding technologies since we can safely move these resources from one chain, one shard chain to another shard chains without worry about creating, copying, or destroying these resources. All these are secure by the consensus and also the languages. So if you are interested in this new direction of technologies, feel free to contact us at blockchain.io. Thank you.
Hello, my name is Pranay Bhattacharya. I'm a grad student at Georgia Tech, and I would like to talk about a project that we've been working on. So a little background, Venezuela is in an economic crisis, and many individuals there are very interested in cryptocurrencies as they feel it's more stable than their own currency. And in many instances, there's locations where there's not enough fiat for people to receive. And so these individuals, they're looking out into the blockchains and crypto space, and they found that there's games out there that reward cryptocurrency. So they've been playing these games, earning cryptocurrency, and they've been using this cryptocurrency to exchange for goods, services, and materials. So we wanted to encourage this behavior, and so we've decided to create a microloan system using smart contract on the EOS blockchain that these individuals can take part in. So we've sent down a number of smartphones so that they can take part in the blockchain. We give them the phone, they pay it back through the blockchain, and they feel empowered and socially empowered because they can see the financial process is transparent to them, and they also can feel empowered because they can participate in the blockchain themselves. And there's, let's see, some individuals that are accepting EOS there are like pediatricians, street vendors, taxi drivers, and the people are so interested that in the blockchain technology because they can participate, they can write their own smart contracts, they want to learn more about it, and it's open to them. It's not closed off. Thank you.
Hi everyone, my name is Alex. I'm co-founder of Matter Labs, and at Matter Labs we work on ZK Sync, a scaling technology for Ethereum based on zero-knowledge proofs. And here on the left side you can see a piece of our zero-knowledge circuit used in ZK Sync, written in Rust with Bellman framework, which is the most advanced Rust-based zero-knowledge circuit construction framework. And on the right hand, you see the exact same code written in simple Rust. As you can see, it's a lot less because writing circuits right now in Bellman and like in most frameworks is hard. Like it's very verbose. You have to understand nuances. You can easily make a mistake, which will cost you security. So we decided to create Zinc framework to make writing circuits safe and simple for general programming audience. In Sync, this piece of code looks exactly as you see it on the right side. So like here's a bigger example. It's essentially a subset of Rust, which compiles into a virtual machine, which is R1CS friendly. We have backends for all the various new proof systems. Please try it out. I'm going to post a link to a discussion group in the Telegram group. Please reach out if you want to try it out and discuss. Thank you.
Hi, my name is Kinsa from SpareX Protocol, and I'm here to give a brief overview of our BFT consensus. So for BFT consensus is designed for a network model which is partially synchronous, which includes open internet and also P2P network. And we found that it's actually quite difficult to design a consensus that's both secure and guarantees liveness, as we've analyzed a few BFT protocols, BFT consensus. For example, we found a flaw where a network can come to a deadlock and stay in deadlock even after GST when it comes to a synchronous state. So our research team has designed our own SpareX BFT, which is mathematically proven to guarantee safety and liveness, and it is also the fastest consensus on the BFT consensus on the market. So yeah, we have an event tonight. Come check us out at the event, or feel free to just contact me for more info. Thank you.
Hi, I'm Swaroop. I'm one of the co-founders of BlockVisual, and we are building an API gateway that allows any developer to build on blockchain with zero experience. So a couple of years back, I was trying to build my first prototype on Ethereum, and even for a seasoned developer, it was overwhelming to sort of understand this new paradigm. And it wasn't just restricted to sort of maintaining a node infrastructure, but sort of writing on chain using wallets. And in the country I was in, I couldn't even buy crypto to get the gas. And this is true for tens and millions of developers who are out there that haven't, they are still trying to build on blockchain. So we built this sort of a RESTful API that allows you to interact with smart contracts using a dynamic open API spec. So you can use your existing tools, whether it's curl, Postman, or language of your choice. You're not restricted to just a JavaScript framework. We have a sort of a very open transaction lifecycle, so it's not just reading. We also have write transactions through a rollable API key. So we do that through meta transactions so that the developers are always in control of their contracts. We also have smart webhook and WebSocket monitoring that allows you to just get the data that you need, whether it's for your application or anything on-chain. And you can hook it up to oracles or like Zapier integrations. So our docs are live on our website, blockvisual.com. We also have this unique tutorial framework that allows anyone to sort of learn and build a blockchain app in real time. So feel free to check it out, and I'll be around to answer questions for the rest of the day. Thank you.
Hi, everyone. My name is Mahdi Zamani. I'm from Visa Research. So today I want to talk about and introduce a new sharding approach that is called InstaChain, which can break the limits that exist on traditional sharding protocols like RapidChain and OmniLedger. in terms of shard size, because that's a big problem in these sharding protocols. And so InstaChain would be able to allow higher the throughputs through this smaller shard sizes. As an example, RapidChain divides the network of consensus validators into 16 disjoint shards, each with 250 nodes. In a synchronous network, this guarantees an honest majority in each shard, and was shown to provide a throughput of more than 7,000 transactions per second. In contrast, in InstaChain, we divide the network into much smaller shards, 80 shards of 50 nodes, which is 5 times more than RapidChain. This, of course, results in losing honest majority in some of the shards, but by choosing the shard size carefully, we can still bound a fraction of dishonest nodes in each shard to 65%. Next, we adjust the quorum size parameter of the consensus protocol such that safety is maintained in all shards, but liveness may be compromised in dishonest majority ones. Out of 80 shards, this results in 51 live shards, which is 3 times more than RapidChain, and 29 inactive ones that cause no harm but can't process transactions either. By taking this into account and also the overhead of redirecting mempool transactions from inactive shards to active ones, and also resharding the network more often due to smaller shards, we estimated a throughput of more than 13,000 K, which is roughly 2 times better than previous work, specifically RapidChain. Thank you. And we are also hiring at Visa Research.
Oh, sorry.
Hi, my name is Joseph Wu, and I'm a product manager by trade. And for my talk, let's zoom out and take a long view of the industry. Not just blockchain, but peer-to-peer in general. So I still remember way back when I was 6 years old, watching my dad connect to dial-up internet, fascinated by his every move, and thinking that the internet was a magical portal into a digital world, unconstrained by physical limits. And it was this same curiosity that drove the world to adopt a technology that even its creator said would fail. And in the early days of internet, we saw ourselves embrace peer-to-peer technologies like Napster, like LimeWire, and many more. And at its peak, over 1 in 3 computers in the world used LimeWire. But shortly after, as we know, peer-to-peer file sharing applications like LimeWire and Napster got squashed by government regulators, and peer-to-peer communication protocol like Skype got acquired, and the first thing they did was reroute the network through centralized servers. So as centralized solutions came to dominate the internet, and as I grew up, the internet seemed less and less like a magical portal and more like a surveillance camera, tracking my every move online, generating consumer profile, and selling me and helping corporations sell me more things that I don't want. And I'm so happy to be with you all today because we're on the cusp of profound changes, the potential to redefine our relationship with the internet. As we usher in the second generation of peer-to-peer applications with battle-tested solutions like Bitcoin, Ethereum, torrenting technologies, and initiatives like IPFS for the decentralized web. It's safe to say today that peer-to-peer is back. And as everyone in this space, let's keep our eyes on the prize and dream big. Woo!
All right, hi, I'm Berk Sunar. I'm with QuantumSafe.io, and I want to tell you a little bit about our efforts in looking into post-quantum schemes in deployments of blockchains. And in the last year, we have seen a serious competition, brewing up between Google and IBM, and with announcements, publicity, and so on. And whether you're taking that seriously or not, it's not really that much of an issue because the US government is actually moving in and building a new standard. So there is a NIST competition going on for post-quantum signatures and as well as key encapsulation mechanisms for public key exchange. That's going to come to a conclusion within a year or so. And there was also an NSA advisory earlier last year urging companies to move away from traditional crypto such as ECC and RSA and so on. And when that happens, if we are forced, let's say, in the context of blockchain, to move away from ECDSA to these signature schemes that are being considered for standardization by NIST, we will see a significant drop in the TPS rates because the overhead is pretty high. And what we have been working on is to find a solution. And essentially, we found a way to aggregate signatures and public keys. And in this colorful graph, the colorful dots are essentially the price points or performance figures for signature sizes and public key sizes for the post-quantum schemes in logarithmic scale. Okay. So, and then the exception is, and you see a bunch of distribution, hash-based, multivariate, lattice-based are sort of clustered in the middle. The red dot that you see close to the origin is ECDSA. So that's what we're using now for blockchains. And what we have been able to do is to find an aggregation scheme based on lattices to move that point. You see with the two arrows, one is public key compression, the other is signature compression close to ECDSA. So if anybody's interested, get in touch with us. Thank you.
Hi, everyone. My name is Trinshi Liu. I'm a PhD student from George Washington University. I'm here to present one of our security research currently. So it's called TOCoin. It's a coin-based access control scheme for IoT devices. So what's wrong with current IoT devices? IoT access control. So there are two classes of like popular access control. So one is the permission-based access control, and one is capability-based. For the permission-based access controls like Linux access control list, so it's like a read, write, execute, yes, no. So obviously very coarse grain. So it's also found in Oakland. There's many overprivileged attacks targeting these vulnerabilities. And also there's a poor accountability to access activities. So what it means is that once you're granted access privilege, then your actual access activity is not monitored. It's actually you can access unlimited times. And this is the same for capability-based access controls like OAuth. And also for capability-based access control, the leakage of the actual token is very dangerous, it's very untraceable, and you can be unaware of this. And in practice, your IoT device is controlled by the manufacturer. Like Alexa is controlled by Amazon. And they have the technical highest control privilege. So that's why you find like there's eavesdropping news on the Alexa and so. So our working here is that we propose a TOCoin is to manage the access capability just like cryptographic coins. So we want it to be very accountable. So when you own an IoT device, you issue a TOCoin representing an access activity. So one TOCoin is one access. No TOCoin is no access. You can guarantee that your device will not be attacked with high cryptographic confidence, like based on the assumption of blockchain security. And also, fine-graininess, we write a fine-grained security policy inside a TOCoin. And yes, we kind of have a trusted execution environment implemented for autonomous access control. Thanks.
Hello, my name is David Vork, and I'm here to talk about Skynet. Skynet is an extension to the SIA protocol, and it enables file sharing and data publishing in a decentralized way. So we did a survey recently of dApp developers and applications in the decentralized space, and we found that for the most part, they really struggle with decentralized storage. Either, a lot of times it says IPFS on the sticker, and then on the back end, they've got a custom solution that is centralized to make things performant and have uptime. So we've developed a solution that is fully decentralized. It's high speed. It's capable of doing video, audio, text, images, and it has its own built-in decentralized pinning. So we think that this is a system which can enable the application space to decentralize its data storage layer. Thank you. We have a meetup tonight. You can check us out, Skynet Meetup.
Hi, everyone. So I'm going to be speaking with you about oracles. Oracles are related to something called the oracle problem, where you need to connect a smart contract to external data securely. Because you have an oracle problem where you can't do that natively from the contract, you have a huge limitation of what you can do. You can't build many things like DeFi, insurance, or anything other than tokens. And this is the problem we work on. It's a very timely problem because there's been recent hacks related to decentralized financial applications that have failing oracles. So, how does this setup usually look? Basically, you have decentralized computation that's very secure. You have an oracle mechanism you rely on to securely transport data. Then you have data sources. So the first category of attacks that people should really keep in mind is the capacity for that oracle mechanism to get compromised. And they try to solve this with DevOps or other monitoring solutions, but this often fails, and it's not a good idea. And also security through obscurity is not going to help you, so I really suggest you think a little bit deeper about this. The more recent attacks have actually been people going after data sources, and this is a problem in the architecture that people decide to do. They say, hey, I don't know anything about data, but I'm going to use an exchange API from one exchange or a single DEX. Looks good today, so it'll be fine in 2 months, but then it's not fine because it becomes thinly traded, it's because there's a flaw in the smart contract, and then you lose a lot of money, and people don't like DeFi. So I want people like DeFi, so please, when you build a nice DeFi app, make sure you consider both the security of the oracle mechanism and the quality of the data source and how it'll look in a few months, because you're introducing a large attack surface area that's a very serious dependency. Now, on-chain DEX prices are doubly dangerous because now you're saying, I'm going to go to one exchange that's probably going to be thinly traded in a market where volume swings very quickly, and I'm going to have an oracle mechanism that might have smart contract flaws in a language that nobody really understands that we can't formally verify. So now you're doubly in danger, and I wouldn't put client funds in that situation. Let's please learn from the lesson. It's not a good idea. Now, what can you do? My advice is use a secure oracle mechanism, whether it's Chainlink or whatever else. Go to high-quality data aggregators. Rely on them to smooth out data. Bloomberg, Reuters, data companies, the reason they're multi-billion-dollar companies in the financial sector, they smooth out risk. Now, if you really want to smooth out risk, you get multiple secure oracle mechanisms that go to multiple data sources. You smooth out risk at the data level, at the oracle level, and you can assess risk and scale up the amount of security you need as value increases. That's what we do. So if you need a high-quality oracle, we have a bunch of them, not even enough to fit on this page. If you're building a DeFi application, you can go on alone on this one. Good, you can try that. You're going to save a lot of time and be more secure if you just use a good oracle mechanism connected to good data sources. That's my sincere advice to you.
So let's give a huge round of applause to all of the Lightning speakers. And the really important goal for next year is that usually at these conferences, there should be at least one song or one, a lot of funny talks, but at least one song during the Lightning session. So maybe we'll move it to during the reception when there's a little bit of alcohol, which usually makes the songs even better. So thank you very much, and get some lunch.
going to get started with the next session. So come in. Okay, this next session is going to be about consensus protocols. And first up, we have Vitalik Buterin. What can I say about Vitalik? Vitalik is from Canada. He is a former writer for Bitcoin magazine and often can be seen wearing unicorn shirts. And he'll be telling us about beyond 51% attacks. Take it away.
Okay, so hello everyone. Okay, so I guess I will start off by just reminding everyone that 51% attacks are in fact bad. So bear with me for a few minutes because this is kind of important. Sure thing, I will. Hold on. This is this better? Okay. So first of all, what can 51% attacks do, right? So there's different kinds of 51% attacks, and 51% attacks can do different kinds of things to different applications. They can have different kinds of consequences. So the kind of 51% attack that you're probably most familiar with is just reverting blocks that have already been accepted, right? So I have a transaction that deposits some money into an exchange. Then I publish that on chain. Then on the exchange, I go and trade those coins for some Litecoin. I withdraw the Litecoin, and then I do a 51% attack on the blockchain that reverses that transaction. And now I have both the Litecoin and whatever coin I just 51% attacked. So this is kind of the major kind of 51% attack that we've been talking about for kind of the last 10 years, and it's the one that there's been kind of the most thought about, but it's only one kind of attack, right? So transaction censorship is also another kind of 51% attack, and transaction censorship is particularly dangerous in light of layer 2 protocols and DeFi, both of which are kind of fairly big trends recently. So in the context of many layer 2 protocols, so including Plasma, channels, general state channels, Lightning networks, optimistic rollup, interactive computation, TrueBit, censorship equals theft. So if you can censor challenge transactions, then you can basically steal money from people. This does not apply to ZK rollup, but it does apply to the great majority of layer 2 protocols that people are thinking about right now. And in the context of DeFi, it's risky because censorship basically gives you a very powerful tool at basically market manipulation and extracting value, right? If right now I can censor every transaction going to the Ethereum blockchain that touches Uniswap, and then I wait a day, then chances are the ETH price will move a bunch, and the prices of a bunch of other tokens will move a bunch, and I will be able to just extract a huge amount of arbitrage value out of that attack. So censorship is also dangerous, and in the context of DeFi and layer 2 protocols, censorship is also theft. 51% attack could get invalid blocks accepted by the network. So this does not apply if everyone is running a full node, but many people are running light clients, and if you're running light clients, then a 51% attack could lead to those light clients accepting a chain that contains blocks that just contain totally invalid transactions. Bad signatures, malformatted transactions, signatures that without authorization just like steal money from one account and move it to other accounts, all sorts of things. They can get unavailable blocks accepted by the network. So who here is familiar with the data availability problem, by the way? Okay, so not all, but many people. So basically the idea here is that you can make a chain where you publish the block headers, so the light clients still see the chain, but you don't publish some or all of the data in the block bodies. And the reason why this is bad is because if the data is not published, then it might be correct, it might not be correct, but there's no way to actually generate a proof to anyone else that it's incorrect. And furthermore, you're kind of denying people information that they might need to create future transactions, right? So unavailable blocks also extremely dangerous. And the final kind of attack is a discouragement attack, which is kind of my term for kind of griefing other participants, so kind of causing other participants to lose revenue, driving them to either become part of your pool or drop out. So selfish mining, kind of above the 1/3 mark, is probably the first example of a discouragement attack other than 51% attack, but 51% attacks are extremely powerful discouragement attacks too. So 51% attacks are powerful. 51% attacks are a threat to blockchain's immutability. So who here remembers this? This was when a pile of money got stolen from an exchange, and they kind of considered pushing for basically a day-long reversion of the Bitcoin blockchain in order to get the money back. If things like this are possible, then things inside of blockchains can get reverted, and blockchains basically kind of lose the key property that makes them blockchains, and this is terrible. So, and also 51% attacks are not democratic, they're plutocratic, and so nothing good about them as a governance mechanism. 51% attacks can be done. So this is a panel in Hong Kong, 90% of Bitcoin's mining power, kind of all kind of conveniently sitting together in this wonderful pose, like, I got the power. 51% attacks have been done. So Ethereum Classic has been 51% attacks, Bitcoin Gold has been 51% attacks. I'm sure I missed some other kind of top 20 chain that's been 51% attacked recently. It's been happening. The kinds of 51% attacks that we've seen are not even the worst, right? So spawn camp attack, this is kind of the worst case, kind of worst nightmare 51% attack that you could see. Basically, get enough hardware to attack a chain, attack the chain, wait for the chain to recover, attack it again because you still have the hardware, and then just keep attacking it over and over again. Eventually, the community gets fed up and they change the proof of work algorithm, and then, well, there's not enough time for them to build ASICs, and so now you just rent CPU and GPU hash power and you attack again, and the chain is dead until they switch to proof of stake. Now, can proof of stake break the cycle, right? So this is a blog post that I made in 2016 where I tried to kind of describe a philosophy behind kind of what proof of stake is and kind of why this is something kind of natural that we should kind of expect to exist, and it's something that makes sense to get behind. And the main argument I made is this kind of asymmetry in proof of stake that basically says that unlike proof of work, where you only have rewards, and so your penalties for participating versus not participating in an attack are only as large as the block rewards in a proof of stake system. If you attack, then that can be detected, and your entire deposit, which is way larger than your rewards, can be slashed. And so these ideas since then got turned into Casper FFG and Casper CBC and a bunch of other proof of stake algorithms that are based on security deposits and slashing. And so here, in theory, the goal is that a 51% attack becomes extremely expensive, right? So, but basically, in order to attack a chain, you need to buy up a bunch of coins, get like more than 50% of the deposited coins in the system, attack it. Then, when you attack it, you get caught, you get slashed. Then, if you want to attack it again, you have to buy even more coins. And because you keep buying coins, the price is going up. And then you attack the chain, then you get slashed again. And then the price of this chain you really hate just goes up again. And then you keep on buying coins, and then you get bankrupt. And so instead of the attacker going POW, we have the chain going POS. Now, here we get to the first problem, right, which is what about other kinds of attacks? So the main kind of attack that this kind of reasoning focuses on is finality reversion, right? So this diagram over here, 2/3, 2/3, 1/3 intersection, 1/3 gets slashed. This is kind of fairly standard from Byzantine fault-tolerant consensus theory, but the core idea basically being that if 2/3 already finalized one side and then they end up finalizing another side, then there's kind of, because of the way the algorithm works, there have to be 1/3 of all the validators that kind of made two contradictory messages, and you can detect this and you can penalize them. Now, the problem is that this is about reversions. Now, what about the other kinds of attacks that I mentioned? What about data invalidity? What about data unavailability? What about censorship? And what about griefing? So we're going to kind of collapse the problem a bit. So first of all, we're not going to care about data validity, right? So we're going to kind of notice that if you have guarantees of data availability, if you have guarantees that if a block is part of the chain, then all data in that block can be downloaded by a node in the network, and if you have censorship resistance, so if you publish a block, then it will eventually get included, then from these two things together, you get validity. And the reason is like interactive computation, rollups, kind of all of these existing protocols, right? Basically, you can just have a rollup, and then for the rollup, you publish all that data on chain, and then the chain guarantees its availability, and you have some fraud proofs, and you can guarantee that that if some computation is invalid, you can publish a fraud proof. It's not going to get censored. It'll get on chain, and it'll get processed. So data validity, we can kind of not think about as much as a concern, because either layer 1 fraud proofs or kind of layer 2 fraud proofs can solve this. If you cannot censor, you generally can't grief, because if you can't censor other people's blocks, then you can't prevent other people's blocks from getting included on chain. And as long as the incentives kind of don't penalize more limited forms of censorship that are still possible too much, then the griefing is also going to be not too much. So we now have two big focuses of what nasty things 51% attacks can do, which is one, data availability, and the other is attacks, and the other is censorship. So can we improve on these? Can we improve on resistance to these things? So data unavailability, right? So this is a paper I wrote with Mustafa and Alberto Sonino back in 2017, where I described this scheme for basically allowing clients of a blockchain to verify data availability of that blockchain without actually downloading all of the data. Right? And the simple kind of straw man version of the scheme is like this, right? So first, the dumb way to check that a block is available is you just download the whole thing. But here we're assuming a scalable blockchain, possibly an ETH2 kind of sharded blockchain where you have more than 2 megabytes per second of data flying around on chain. And so clients are not going to be able to download the whole thing. Now, what we're going to do for a client that wants to check that data is available is it's going to do a kind of random sampling test. It's going to just randomly select, for example, 80 specific pieces of data. It doesn't have to be 80. It could be 40. It could be 30. It could be 120. Choose your security margin. Randomly select some positions. Ask for Merkle proofs of that data. And you accept a block as being valid only when you receive valid replies for all of the positions that you personally selected. Now, the idea here is that if you accept a block using this scheme, then you kind of probabilistically know that with very high probability, more than 50% of the data is available. Because if less than 50% of the data is available, if, say, everything to the left of here is available, but everything to the right of here is not available, then a whole bunch of checks with very high probability, at least one of your checks is going to fail. Now, with this kind of scheme, an attacker does have the ability to trick a small number of specific clients, But if the attacker tricks more than a very small number of clients, if the attacker tricks enough clients that the leaves that they've downloaded kind of together make up half the data, then those clients can just basically go and kind of reconstruct the data from there. Now, you might notice that this doesn't prove the block is completely available. It might still be missing one piece, but it does prove that more than half the block is available. Now, it would be really nice if there was a kind of mathematical technology that would let us recover 100% of a piece of data given only 50% of a piece of data. Erasure coding. So basically, we're going to take the data, we're going to pretend it's evaluations of a polynomial, we're just going to evaluate that same polynomial at even more points, and now any 50% of this kind of extended data d prime is going to be enough to recover everything, and so it's going to be enough to recover d. So now what we basically have is we have this scheme where you can verify that blocks are available and blocks of potentially very large sizes are available, while personally only downloading like somewhere between 20 and 200 kilobytes of data. So this is the first part, right? So this kind of covers data availability attacks, and this is also part of kind of ETH2's sharding solution, and this at least allows us to give kind of scalable and sharded blockchains the same kinds of availability guarantees and through fraud proofs validity guarantees that you kind of existing non-scalable blockchains that demand everyone to download everything already have. Now, one challenge is, well, how do you actually prove that you computed d prime correctly? So how do you actually prove that this root actually is the root of like an erasure coding of this? How do you prove that you haven't just kind of stuck junk data in here? And there's a bunch of schemes. So there's some schemes that use fraud proofs. So basically, there's schemes such as this kind of two-dimensional one where if you encode anything incorrectly, then someone can make a short fraud proof of it. And so they can broadcast this through the network, and the network would reject the block. So this was for the 2D scheme was for myself and Mustafa in 2017. There was recently something newer on coded Merkle trees, which basically kind of create a Merkle tree and then encode every level of it, and that has some really nice properties. There's also approaches that do not depend on fraud proofs. So one of them is to just basically use a Stark or use a Snark to just prove that the Merkle root has been correctly computed. And then the other possibility involves polynomial commitments, right? So the way that you would use polynomial commitments here is basically, well, you have your data D, you interpret your D as being evaluations of a polynomial, figure out what that polynomial is, make a polynomial commitment to that polynomial, and then you just like make a whole bunch of openings of that using the polynomial commitment scheme at a whole bunch of points. And your data availability check would be, instead of asking for 80 positions, you would just ask for like basically 80 openings. Or potentially you could even get more efficiency if you use like clever algebra to get some kind of multi-opening. So the nice thing about these schemes is that they don't depend on fraud proofs, and so your scheme for verifying that block data has actually been published like doesn't have any extra built-in latency assumption anymore. So another important thing for sharded blockchains, right? So sharded blockchains that exist today generally depend on committees. And the current idea for how many of these sharding strategies work is basically you have a whole bunch of nodes, you randomly sample some of the nodes, and you need like some majority or some supermajority of them to sign off on some block for the network to accept that block as being valid. Now, the problem is that any kind of committee-based scheme is going to be censored by bad actors that go above the threshold. And if we're going to talk about resisting 51% attacks, then we want to talk about a system where if a majority starts attacking, that even a small minority can continue the system kind of reasonably operating by itself, right? And so sharding with a fixed threshold is not really going to help you. And so the solution here is basically that instead of kind of relying on committees, protocols would need to just rely kind of much more fully on these kind of data availability checking schemes. So now we get to the really fun part. What about censorship? Who here wants to prevent censorship? Okay, that's a good number of people. So this was not good. So this was a post by Ryu Nakamura, who has done a lot of wonderful work around formally verifying Ethereum things. And he wrote this post that basically points out that there exists strategies by which a majority can censor blocks in the current ETH2 design, where that censorship is indistinguishable from single block latency, and it's very hard to kind of attribute who's actually responsible. Like the scheme, the attack here is actually pretty mean. Like the idea basically is that what the attacker does is the attacker sometimes censors other people's blocks and just kind of puts their weight behind blocks that do not have whatever thing they're trying to censor. But then the attacker also sometimes themselves publishes blocks that have the thing that they're trying to censor, but they publish them 1 second late. And so the network is kind of inclined to support another block that has already been published. And then the attacker kind of takes some of their validators and uses them to vote for that other block, and then uses some other validators to vote for their own their own block that actually contains the thing they want to censor. But the thing with their own votes doesn't actually have enough votes to kind of go over 50%, and so the blocks they're trying to censor or the thing they're trying to censor never actually gets included. So there's a lot of kind of misdirection of multiple kinds going on, and but the kind of summary is that in ETH1 and in ETH2, like a 51% attacker can censor, and it's kind of difficult to kind of pin down when enough censorship is going on that it's kind of worth trying to do something about it. So how do we fix it? So here is like the bare minimum thing that we could do, uncle inclusion. So the idea here is like basically the thing that we do in ETH1, where blocks that are not part of the chain can be included later, except unlike in ETH1, we add an in-protocol rule that says that transactions in an uncle also get processed. So you have a chain, you have this block kind of going off as a stale, then you have this chain, and then this block gets included as an uncle over here. And what you do is when you process this block, you kind of process all of these transactions, and then you process these. And then you go off and process the rest of the chain. So this is something that kind of has already been done to some extent in kind of DAG blockchain protocols, and so those things are good. But the general idea here, right, is that this makes total censorship much more distinguishable, because in order to kind of totally censor blocks that contain transactions you don't like, you would have to prevent them from getting included in the chain for all the way up to the uncle inclusion period, which you could theoretically make as long as you want, right? So total censorship becomes distinguishable from all latency up to an extremely long period. So this is already a huge improvement. So now, well, let's get to something that's even stronger. Imagine if we could have at least clients that are online, so clients that are kind of on the network, downloading things, and regularly normally talking to other clients, have kind of detect whether or not they saw that a block arrived on time. And we're going to do something a bit risky, right? We're going to say if they see that a block arrived on time, and they see that that block has not been accepted into some chain for a really long number of blocks, then that block is automatically disqualified. And if a block is not on time, then potentially you could use this to disqualify kind of reversion 51% attacks as well. Right, so the idea is that clients just kind of locally detect whether or not they see a block as having arrived when it should have arrived, and they use this as information in determining which chain to follow. Now, this so not every node is going to be able to follow the protocol because offline nodes exist too, right? But the idea is that unless a 51% attack is actively happening, then, like, if there's no attack happening, then the chain that is winning is going to be a chain that's fine anyway. And if an attack is happening and you're offline, then you pretty much would have to kind of check the social layer to see what's going on. But it's only a relatively small number of actors that would have to do that, and everyone else would already have a pretty clear consensus. Now, the problem with this kind of technique is these edge attacks, right? So basically, what happens if you make a block and whatever definition you have for that block arriving on time, some nodes are going to see that block arriving at one point, some nodes are going to see that block arriving at another point, and so nodes might disagree about whether or not a block was censored for kind of too long, nodes might disagree on whether or not a block was published on time, nodes might disagree on any of these timing parameters, and an attacker can target this, right? An attacker can deliberately publish the block at exactly the right time to maximize disagreement. Really, the attacker can pretty much kind of target whatever points on the bell curve they want, and they can kind of do lots of things, right? And so they could even kind of create long-running disagreements about whether or not an attack is happening, and they can kind of wreak a lot of governance havoc. So let's have better timeliness detectors. So we're going to go back to the Byzantine generals problem, this wonderful Leslie Lamport paper from 1982. And as it turns out, this paper contains an algorithm that people don't really talk about, but people, in my opinion, should talk about a lot more. And it has this kind of sentence hidden in the abstract with unforgeable written messages, meaning digital signatures. The problem is solvable for any number of generators and any number of possible traders. So basically, Lamport here is claiming that he's got a consensus algorithm that is fault tolerant up to 99% faulty attackers. Now, this algorithm works, but it has a catch, right? And the catch of this algorithm is that it only works as long as you have a synchrony assumption, not just between the people doing the consensus, so not just between the miners and the validators, but also between the miners and the clients, and between the clients and other clients. So it has this kind of much stronger assumption about who is supposed to be online, and it uses this assumption to get this kind of higher level of fault tolerance, but it is a really serious assumption, and it is an assumption that we're not kind of comfortably making by ourselves. Now let's look at how this mechanism works, right? So I'll describe a version with a kind of single attester, right? And here we'll assume that the single attester is honest, but then we'll kind of generalize and we can have n attesters, and we only need one of n attesters to be honest. So the idea here basically is that imagine a block B gets published, then clients and attesters have a kind of deadline by which they need to receive the block in order for them to consider that block as being on time, right? So for clients, that deadline is going to be T, and then for the attester, that deadline is going to be T plus delta. So the proposer here is going to publish B, and we're going to assume the proposer is a bit evil and the proposer attempts an edge attack, and node 1 sees it before the deadline and node 2 sees it after the deadline. Now here's what the attester does. The proposer sends the block. Because of the network synchrony assumption, if even one node accepts the block, that means the attester is guaranteed to accept the block before their own deadline, because if nothing else, the node could just kind of send the block over to the attester. And then the attester, when they see this block, they're going to add their own signature. And a block plus a signature has a deadline that gets offset by 2 delta. So if even one client sees the block as being on time, then the attester is guaranteed to see it before their deadline, and so the attester is guaranteed to add their own signature. And so, because of network synchrony again, the other client is going to see the block plus the signature before the deadline for a block with one signature. Now, the way to extend this to having n attesters is very trivial, right? Basically, you just have lots of attesters, and the deadline is going to, for clients, is going to be t plus 2 delta times k if the block comes with k signatures, and for attesters, it's going to be t plus 2 delta times k plus another delta. I have a post on ETH Research about this, so if you want kind of more details, feel free to check this out, but that's kind of the approximate idea, right? This idea that you have this kind of set of actors, each of which have the ability to kind of delay the deadline by a bit, and so if a block gets received by one, then it kind of propagates the kind of the timeliness of the block to the rest of the network, as long as the network delay is below whatever your delta parameter is. So fun fact, if you have this kind of timeliness detector, then timeliness detectors give you a blockchain by themselves. So basically, the protocol is simple. You just kind of process all timely blocks in order of self-declared time, and that's it. And the only problem with this is it requires a really long block time, right? So this might be an interesting protocol to use if you want just like to process validator deposits, to process validator withdrawals, to process slashings, but this isn't the best protocol for just running a blockchain. Now, more realistically, you can kind of use timeliness detectors to kind of detect attack chains, detect censorship, and lots of other things, right? So as a summary, right, so these, the anti-censorship technique in particular is definitely kind of less perfect than the other techniques, and the key reason why it's less perfect is because it does depend on a synchrony assumption between the network and clients. And you can set the assumption to be kind of however long or however short you want, but it just depends on kind of how long, like what level of censorship you're willing to tolerate and what level you want to prevent. But you can at least kind of get this guarantee of agreement between the set of nodes that are online, and of whether or not a chain was censoring for too long, whether or not, or in the event of an attack, whether or not some given chain is an attack chain, and all of these other things. And you can kind of use this as at least the beginning of this kind of partially social consensus for kind of which way to recover. And because you have this stronger level of consensus, like it would be easier to kind of assign kind of higher and stronger penalties to attackers because you can more reliably actually identify who the attackers are. Now, in general, kind of the mapping to attacks, if the attacker publishes it on available chain, then data availability checks, it'll get ignored. If the attacker publishes it in valid chain, fraud proof, it gets ignored. If you censor blocks for a short time, the blocks just get included as uncles. If you censor blocks for a long time, then the chain kind of automatically gets ignored by the network. And if you censor blocks for a medium time, then like you can use these kind of timeliness detectors to kind of just cleanly force things into either the short case or the long case. And if the attacker tries to not participate in or break committees, then the response is to not use committees. So there we go, right? So we basically have this kind of collection of tools that essentially lets us kind of fear 51% attacks much less, and either kind of ignore, resist, or recover from many kinds of them. So thank you. Just ignore, resist.
Okay, we'll take maybe one question. Sure. Okay.
In the attack example about the Binance attack, at least like for proof of work chain, then you have to talk to the miner and negotiate for the purpose of this attack. But in the proof of stake scenario, because for example Binance may have a majority of Ethereum on the exchange, so they can borrow that for free, and then they have immediate like a responsibility to correct it if there's any stolen events happen. So it sounds like it's easier to attack.
Well, remember, if Binance actually doesn't attack, then Binance gets slashed, and Binance customer funds get slashed, and so you'll have like a lot of people get insanely angry at them. Right?
But could they use like more token to actually slash the valid validator and then correct the
how would you slash a valid validator? It's like the point of the slashing mechanic, right, is that like it doesn't slash the minority, right? It slashes whoever the attacker is. And so the idea here is that you can detect the attacker even if the attacker is the majority. And so you can, like, if Binance decides to attack the chain, then like you actually would be able to like act in whatever chain ends up coming out of that, kind of take away a huge portion of Binance's deposit that in most cases would be much larger than whatever they could get by doing a reversion.
Okay, let's thank Vitalik, and I'm sure you can ask him more questions offline. So next up we have Benjamin Chan. He is a PhD student at Cornell University. He works with Elaine Shi, and he'll be telling us about a new consensus protocol. One challenge in consensus protocol design is to build consensus protocols which are provably secure and have new properties. But another challenge is building them in such a way that they're easy to understand, because in the end of the day, they have to be implemented. So he'll be telling us about a very simple presentation that gives us intuition into a class of recent consensus protocol constructions.
Is my mic on? Can you hear me? Awesome. I'll wait for like a few seconds for it to settle down. I'd like to thank Vitalik for the nearly packed hall. This is quite amazing.
Right now. So the overflow room is open if there isn't room in the back here.
Okay, amazing. Hi, everyone. My name is Ben. I'm currently at Cornell University. This is joint work with Elaine Shi, who's also at Cornell. And today I'm quite excited to show you this new consensus protocol that we call Streamlit. You might be asking, why do we need another consensus protocol? And the answer is really simple. We think that our protocol is remarkably intuitive, remarkably simple, and also, arguably, the simplest protocol that we've seen so far. Okay? And this is quite a bold claim, but hopefully the protocol will speak for itself. Now, what's interesting is consensus protocols have this reputation for being incredibly subtle, very difficult to understand, and also, and most importantly, very hard to implement in practice without one of those million-dollar safety bugs. And what we want to do is take this reputation and sweep it not under the rug, but out of the door. That is our goal here. That would be absolutely fantastic. So yeah, without further ado, let's just jump right in. Here's a quick outline of this talk. First, I'll be modeling the consensus problem. What problem are we exactly trying to solve? Then I'll spend a few seconds on motivating simplicity as a goal. I don't think I need to spend a lot of time on that because simple protocols give us simple implementations. Finally, I'll spend the bulk of this talk going line by line through our protocol, showing you the whole thing. It's really short. And hopefully, by the end of this talk, all of you in this room will walk away and be able to say, yes, I understand a consensus protocol. I can describe it. I can maybe even prove to myself why it works. And to me, this is absolutely remarkable because never in my own life, and I've worked on consensus protocols for a while now, never have I ever been able to understand a consensus protocol in 30 minutes. And this is a very lofty goal. I hope we get there.
What about the longest chain protocol?
Well, you'll see, with good finality guarantees. What is consensus? Consensus is arguably the most fundamental algorithmic question that blockchain tries to solve. In some sense, every system is trying to solve this problem. Hey, we have a lot of people. How do we get agreement on this set of people who might all have very different opinions, and some of which who may be malicious? And we're going to present a version of this problem that we call blockchain, as you might. Yeah, it's kind of funny. And the difference here is that we want to reach agreement on a sequence of values and not just a single value. So here's the problem statement. We have some known set, a priori. We have some set of processes or players, users of the protocol. So yes, we are very much in the permission setting. And you might wonder why. Hey, why are we in the permission setting? Aren't blockchains by definition like permissionless? It's a good question. The answer is proof of stake. Right off the bat, our stakeholders give us a permissioned authenticated set. And moreover, many of today's modern protocols, such as Algorand and many more, do this thing where we elect a committee of participants using a VRF or some other crypto, and then run a permissioned consensus protocol or permissioned blockchain on top of that. So I argue that permissioned consensus is increasingly relevant to blockchain research today. So back to the problem statement. We know that we have some set of users, once again. Each user is going to maintain an ordered chain of blocks. This is their version of the blockchain. And we want two properties. First, we want consistency. Intuitively, consistency says that, hey, everyone wants to see the same chain. This is our agreement property. More specifically, if Alice has a chain and Bob has a chain, then Alice's chain must be a prefix of Bob's chain or vice versa. But for the sake of this talk, basically everyone wants to see the same chain. The second property we want is liveness. Okay? And this basically says, hey, if I have some transactions I want to add to our blockchain, we must be able to confirm them fairly quickly. It can't take a million years. We're not advertising a blockchain for immortals, though I could see that happening. And we call a blockchain with the consistency property a finalized blockchain, or like confirmations. These are the colloquial terms when we talk about these blockchains. Now, in order to turn this into the distributed algorithms problem that we all know and love and try to avoid, we introduce some adversaries. Some subset of our users might be malicious. And when I say malicious, I mean they can lie. They can tell different things to different people. They can pretend like they go offline. Messages, on top of that, our network might be flaky. So messages might be lost or delayed and reordered at any point in time. So it's clearly a pretty bad situation to be in. One example of this is like, hey, what happens if someone decides to cut all the submarine cables that connect the United States to the rest of the internet? I think this is very implausible. But we want our system not to have double spending, not to fork, even when the network is partitioned. And this is the holy grail. An example of why this might be very difficult to achieve is this diagram I've put on the slides. On the left side, everyone's honest. Someone's on an airplane. So you can't really, you don't know where they are, but they're on an airplane. They can't communicate with you. On the right side, one of the users is malicious and just pretending to be on an airplane. We don't know which side is which, right? Everything looks the same to us. And this is fundamentally the difficulty in solving these blockchain consensus problems. And yes, this problem is notoriously hard. I drew a brief survey of the literature. It started with Paxos in the 1970s, PBFT, Raft, you might have heard of all of these. And here's some paper names, some follow-up papers that I think have interesting names. Paxos made simple, ABCDs of Paxos. So clearly there's a protocol that needs to be simplified. PBFT has this paper called Hot Stuff. And Raft, well, we have Raft refloated. Do we have consensus? This is traditionally a very hard problem. And you might ask, hey, what about modern blockchains, all in the permission setting? Or not permission, but like under the hood, we have some Byzantine agreement protocol. Dfinity, Casper, Algorand. My co-author and I, we've worked on some of these systems, and to say the least, it still takes months of onboarding time to really understand the consensus protocol and know what's going on. Okay? And this motivates our work. Can we eliminate these subtle voting rules that seem to be inherent to every single consensus protocol that I've seen so far? And I don't think we really need this slide, but hey, what do we get from simple protocols? We get a simpler implementation, fewer bugs, lower onboarding cost, which means more people looking at your code and doing code reviews, better open source. And of course, there's the financial problem where a bug might lose you $1 million. So a picture I like is the Leaning Tower of Pisa. I'm going to label this blockchain. And to make matters worse, I'm going to put a giant weight on top of it. And this weight represents maybe $1 billion in virtual assets that are hanging in the balance. What I'd much rather have is this, right? And I just noticed this, actually. The little dome on the top also looks like a weight, but like, it looks a lot more stable, right? This is what we want. This motivates our work, Streamlit. Once again, our goal here is a simplest possible, easy to understand consensus protocol. And I'll just jump right into it. There's no reason to beat around the bush. First, we're going to make two assumptions. The first assumption is that of epochs. Processes are going to have local clocks, which I think is very reasonable, and run in synchronized epochs of about 1 second each. And to kind of picture how this works, like imagine you start at epoch 0, you set a timer for 1 second. After the timer expires, you enter epoch 1, and then you set another timer. After another second, you enter epoch 2, epoch 3, so on and so forth. And ideally, these epochs are synchronized. So every process enters the same epoch at the same time. Now, we can relax this assumption later to avoid, even in the case where we want to prevent double spending, but it's intuitive to keep it here. The second assumption that we're going to make, which is perhaps a little stronger, is that every epoch will have a leader, a single leader, randomly chosen, but known to all. Okay? And an example, a concrete way to do this is, for instance, to pass the epoch number into some random oracle or some hash function, and then take the modulo, and that might just give us a leader. I do want to mention that both of these assumptions have been thoroughly explored in the literature and can absolutely be relaxed in practice. But they do make the protocol explanation a little bit easier. I've put the assumptions in the top right. Now here's some definitions before we get into the meat of the protocol. First, a block. What is a block? You might know what a block is already, but a block here is a pointer to a parent block. We're going to put the epoch number in which a block is proposed inside the block. So every block is going to be associated with an epoch. We're going to put that in the block, and this is quite important. And then we have some transactions that are part of this block. On board so far? I'm going to represent these blocks as these boxes with the epoch number. So on the bottom there, you see a block that was proposed in epoch 7. Next, I'm going to define a notarized block. A notarized block is a block that has been signed using digital signatures and a PKI by 2/3 of the network. And this implies that a majority of honest processes have signed this block. Very simple, something you see all the time in the literature. Okay? And I'm going to denote a notarized block by this double boxing notation on the slide. Now we can define what a blockchain is. You know what a blockchain is. A notarized blockchain is just a piece of the blockchain for which all of the blocks are notarized. Oh, one more thing I forgot. I want to emphasize that the block height might not necessarily correspond to the epoch number. So here you can clearly see that some of the blocks have heights that are different than our epoch numbers. We might skip epochs. Yeah. I'm also going to put these definitions on the side, and now we can finally get to the meat of the protocol, which is what I'm most excited about, our protocol. And every epoch, from e equals 1, 2, etc., our leader is going to create a new block extending the longest notarized chain. Again, a notarized chain is one for which every block has been signed by 2/3 of the network. The leader is going to choose its longest notarized chain, build a new block on top of that, and then propagate this to the network, embedding the current epoch number. Simple. And finally, this is almost the whole protocol. The voters are going to sign the first such block that they see from the correct leader for the given epoch that they're in, if and only if the block extends the longest notarized chain the voter has seen. You're always looking at the longest chain. Proof of work, I mean, it's all the same, the longest chain. I'm going to just leave the slide up for maybe 5 seconds so that we can parse, because this is the most important piece of the protocol. And finally, the trickiest part is the finalization rule. how do we know when to confirm a block? Well, we take any notarized chain that ends in 3 consecutive blocks with 3 consecutive epochs. We chop off the last block, and now that whole chain is finalized. Really, really simple. This is the meat of the finalization. Okay? So this is our entire protocol. A leader proposes a block that extends its longest chain, and a voter votes for that block if it is indeed on a longest chain. And once you see 3 blocks in a row with consecutive epoch numbers, like 1, 2, 3, or 4, 5, 6, then you can finalize that entire chain, and all of a sudden you have agreement. That's it. A single message type, maybe 2, depending on how you implement it. Isn't that really pretty? So let's just walk through an example. We have some genesis block that we take to be notarized a priori. Maybe we skip epoch 1, and then the leader of epoch 2 decides to propose a new block. Let's say we have a 4-node network, so 3 of them are honest and 1 of them is malicious. Let's say they all vote for this new block in epoch 2. And ta-da, this block is notarized. We've seen all the signatures, it's notarized in our view. Once again, we skip a bunch of epochs, maybe the network got partitioned, and all of a sudden the leader for epoch 8 proposes a new block in epoch 8. It looks fine, looks valid, everyone's gonna vote for it. It extends the longest chain that we've seen so far. It also gets notarized. And again, and again. And now you see we have 3 consecutive blocks with 3 consecutive epochs. Right there. Now we can apply the finalization rule, and we have finalized the blocks that I've highlighted in green. Everyone in the network is going to agree on the green blocks. Now, this protocol has some pretty standard properties. We get consistency without any synchrony assumptions when the number of faults is less than 1/3 of the network. And we also achieve progress with some minor synchrony assumptions, and this requires an expected constant number of rounds. If you don't understand these terms, that's fine. It doesn't really matter. And we can obviously optimize this protocol, as you can see in our paper. But let's go through another example to build some intuition on why this protocol works. So again, we start with some genesis block. The leader in epoch 1 proposes a new block. Everyone thinks it's a good block. It extends the longest block, longest notarized chain so far, which is the genesis block, so we vote for it. But maybe all of our votes get delayed. And in epoch 2, the leader still hasn't seen a notarization for the block in epoch 1, so the leader for epoch 2 proposes a new block that competes with the epoch 1 block. And everyone is also going to vote for this, because no one has seen a notarized block yet, because the network dropped a lot of messages. But now maybe all of the messages eventually end up reaching their source, so we have 2 notarized blocks at the same height. This is entirely allowed. We clearly don't have agreement here, but we'll see how to get agreement. Maybe this happens again. In epoch 3, another proposal comes. Everyone votes because it extends one of the longest chains. Again, the votes get dropped, so a competing block gets proposed. In epoch 5, we skipped epoch 4. Now we have these dueling blockchains that are competing with each other. Maybe epoch 6 goes off without a hitch. This is amazing. We allow 2 notarized blocks at the same height. Who would have thought? Usually. This example is particularly compelling because it shows you when 2 competing notarized blocks are allowed and when 2 aren't. On the left, the situation is possible. On the right side, the situation is impossible. And the reason is because we've applied our finalization rule, or we could apply our finalization rule here, and finalize 3 blocks up to epoch 3. In particular, this epoch 5 block cannot exist at the same height. And our finalization rule basically argues that the epoch 3 block is the only block at that height. Therefore, any longer blockchain must extend that block. And this is how everyone kind of sees the same blockchain in the end. So we'll work up to that consistency proof, but first let us set up this example on the left side. We have 3 epochs in a row, epochs 5, 6, and 7. Once again, we finalize every block up to the second. So the genesis, the second epoch 2 block, the epoch 5 block, and the epoch 6 block. And now what do I want to prove? I want to prove that this extra block that I just added on the screen in any epoch x cannot exist. How do I prove that? First, we need a helper lemma. Every epoch is associated with at most one notarized block. And this is really easy to see by a simple, if you've heard about it before, a quorum intersection argument. The argument is as follows. Every honest process is going to vote at most once during an epoch. You vote for the first proposal that you've seen so far. Now, each notarized block requires signatures from at least 2/3 of the network. Therefore, if you have 2 notarized blocks within the same epoch, we need a combined 4/3 of the network to notarize. Now, because only malicious nodes can vote twice, and the number of malicious nodes is smaller than 1/3 of the network, then we just don't have enough votes to go around. So this is impossible. So let's go back to the previous example. I've put the protocol back on the bottom so you can refer to it. Again, in every single epoch, we can mint at most one new notarized block. So in particular, this cannot happen. Now, the crux of the finalization rule is the following. Remember, we want to prove that no competing block that competes with the block at epoch 6 at the same height can ever exist, either before or after we see this picture. And the way we prove that no other notarized block in past or future can share the same height as block 6 is as follows. First, let's assume that there exists such a block. Let's call it epoch x. If x is less than 5, then in our example here, this block must have been notarized in epoch 4. So let's look at this example. I'm particularly interested in the epoch 5 block. Once again, let's say we have 4 processes, 3 of whom are honest and 1 of them who is malicious. And because our epoch 4 block is notarized, then 2/3 of the network must have voted for it. So 3 votes must have gone to this block. And in particular, because voters will only vote for blocks that extend the longest notarized chain that they've seen, the 2 honest blue votes that have voted for the epoch 4 block, they've seen a notarized epoch 3 block. So they will not vote for the epoch 5 block. Is everyone on board? So the epoch 5 block just cannot be notarized. I'm going to go a little faster here because I think I'm running out of time. What about if x is greater than 7? It's the same thing. If the epoch 7 block that we've seen is already notarized, then 3 votes must have gone towards that block. And at least 2 of them must be honest votes. And because the honest voters have already seen, by definition, the epoch 6 notarized block, they will not vote for the epoch 8 block. Exact same argument. And so if x is greater than 7, such a notarized block cannot exist. And that's it. I've just proven to you that once we apply this finalization rule, where we see 3 consecutive epochs, it's sufficient to demonstrate that no competing block at that last finalized block can ever exist in past or future. And therefore, all new notarized chains must extend from that block. And a little bit of intuition here, what I'm saying is that we cannot rewrite history. Once a block is notarized, we can't go back in the past and write a competing block into this ledger. In particular, we can add a new notarized block at the same height as an existing notarized block, but we can't add a new block at a smaller height. And this gives us consistency because, once again, every longer notarized chain must extend block 6, which implies that every longer finalized chain must also extend block 6, because every finalized block is also notarized. No synchrony assumptions. So let's recap this consistency argument in a more intuitive way. First, we can't rewrite history. We can't notarize blocks in the past. Second, we can work on at most 1 block per epoch. It's kind of like an honest Bitcoin miner choosing which fork to work on. And third, our finalization rule intuitively is demonstrating to us sudden chain growth. We've got 3 consecutive epochs in a row on the same fork of the chain. This gives us a chain that is provably longer than all of the competing chains. And if you see a resemblance to proof of work, you're not alone. And this is, I think, a very elegant approach to traditional consensus. All right, I'm going to put the protocol back on the screen in case you were curious. Now let's talk about whether a protocol can make progress. And the answer is yes. We do need many good leaders in a row, obviously, to work on the same fork. And we either get lucky by electing these random leaders, or we have some stable leader election mechanism. Okay, it's not bad. And I'm sure there's ways to optimize this, and you can refer to our paper for this. All right, so that's it. That's the entire protocol. I hope you see what's going on. Just to recap, once again, in every epoch, the leader is going to propose a new block extending the longest chain, and the voters are going to vote for the block that extends a longest chain. And we finalize when we see 3 blocks in a row with consecutive epochs. Our goal is as simple as possible drop-in replacement for a protocol like PBFT, and I hope we have it. We have a consensus mechanism that requires a single message type. All you have to do is sign a block and propagate that signature. And I think this minimizes, in some shape or form, the subtlety that is going on in these consensus protocols. We achieve consistency. We achieve liveness in the GST model for those of you who are more interested in the formalism. And our paper is online in ePrint form at that URL. And now it's time for questions. Thank you very much.
We have 5 minutes for questions.
Quick question. So like for one epoch, what if the leader proposed like 2 blocks simultaneously, and the rest they don't know what to choose?
Yeah, so in this example here, let's say the epoch 9 leader proposed 2 different blocks. Remember, our voters are only going to vote for 1 block within an epoch. So either no block gets notarized, or maybe one of the blocks gets notarized. It's impossible for 2 blocks to get notarized by the same arguments I made before.
Hi, I was curious if you could go into how voters are chosen, and if this system is like susceptible to 51% attacks, where if more than 1/3 of the voters are colluding, they could stop new blocks being added to the chain completely.
Yeah, this system, like most of the literature in the permission world, that does have these good finality guarantees when the network is partitioned, only tolerates 1/3 of the network being malicious.
Can you extend this to support changing node IDs or counts?
Sorry, could you repeat that?
If the identity of the validators changes,
yeah,
or if the count of the validator changes?
So the way most protocols deal with this is, the one I'm most familiar with is Algorand. But we can certainly elect a committee and then run this protocol on the committee and then do this in a way where you can change the membership at every step. I think that's entirely possible.
But you need to know exactly how many validators there are in order to make the assumption.
Yes.
Hello. I was wondering, so I know the answer, but could you comment on the difference with the hot stuff protocol? Because I think it's a very small difference.
Hot stuff?
Yes.
There's a lot of versions of hot stuff now. The one I'm most familiar with is the 3-phase protocol. You have like a prepare, commit, right. And to my knowledge, I think there's some pretty subtle voting rules, and you change some states like, it's not immediately clear. The difference is that this one's simpler. Like, let's just put it at that. And,
so the version of hot stuff that is deployed in LibraBFT, so the slide will be exactly the same, except the voting rule is not based on the longest height, but it's based on a different criteria.
Sorry, I can't hear you.
So I was going to say, so the voters sign the first valid proposal if only if that's part of the sentence would change, and the rest is the same. So I think it's very interesting to see variants of hot stuff protocol with equally similar proofs.
I would not call this a variant of the hot stuff protocol. In particular, because like the one I'm familiar with is a chain hot stuff version, and there are multiple message types, and the voting rule is not something like this. And actually, I think all of the protocols kind of have the same general structure. Like PBFT has this structure as well. The complexity is in how you vote. So like, for instance, in Pala, you have this freshness rule that is a little bit subtle and that we found to be kind of hard to implement. And it is these subtleties that we've managed to get rid of here.
I can send you the link to the report that we wrote.
Let's take the rest of the questions offline. Let's welcome our next speaker. So our next speaker is Lei Yang from MIT. And he'll be telling us about Prism, which has to do with scaling Nakamoto proof-of-work consensus.
Oh, gosh. Right. Come on.
Okay. Hello, everyone. I'm excited to be here to talk about our implementation and evaluation of the Prism consensus protocol, which achieves 10,000 times better performance than Bitcoin. So this is a multi-university collaboration between MIT, Stanford University, UIUC, and CMU. And I'd like to thank my collaborators, Vivek Bagaria, Gary Wang, my advisor, Mohammad Al-Lazidi, David Xie, Julia Fanti, and Pramod Vishwana. So we all know that Bitcoin has very good security, but in terms of performance, Bitcoin is not that good, okay? Because Bitcoin can only process 7 transactions per second, and it takes hours to confirm each one of them. And we found that Bitcoin couples performance with security in a sense that Bitcoin ties those parameters together with one design parameter, the mining rate. So if we want to increase the performance, we found that you will suffer a lot in security and vice versa. So what Prism does is that we decouple the two. And we do that by doing a natural extension of the Nakamoto consensus protocol. And we do a deconstruction, and we scale each part. And I'm going to talk about how we do that in a minute. And I like to say that the Prism protocol is a very natural and beautiful protocol. And so it's so simple that we implemented it in 10,000 lines of Rust in just about 6 months. So we are happy with the protocol and the implementation. So I'm going to show a demo here. Yeah, that's a good point. So I have just started 100 EC2 machines right before the talk, and I'm going to launch one instance of Prism on each of those machines. And we open source the code, so feel free to check it out on GitHub. Okay, let me continue. Okay, let me continue. In this talk, I'm first going to talk about the Prism consensus protocol, and then I will introduce our system implementation, and finally, I'll talk about the evaluation. So let's dive in. Because Prism is built on longest chain protocol, so I think it's necessary that we do a quick recap on the Bitcoin consensus protocol. So Bitcoin uses the so-called longest chain rule, where every miner will try to extend and mine on the longest chain. And when it's a fork, which happens when two blocks accidentally attach to the same parent block, miners will choose the longer fork. So basically, they always follow the longest chain. There's a very important parameter here called the mining rate, which defines, on average, how fast the miners are going to mine new blocks. And in Bitcoin, this is said to be 1 block per 10 minutes. Another important aspect of the Bitcoin protocol is when do we actually confirm a transaction. So consider the following scenario where I have a transaction which I care about coming in a new block. When are we going to confirm that? A simple thinking is that we can confirm the transaction immediately, but however, there's a problem because it's possible that an attacker is mining a private chain, which, because the mining process is random, it's a Poisson process, it's possible that the attacker can get lucky and mine the first few blocks faster than us. And when that happens, the attacker is going to release this private chain, and suddenly our transaction is deconfirmed because it's no longer in the longest chain. And our transaction is gone forever because now we have a longer chain, and everybody is going to switch to that. So obviously, it's not going to work. And Nakamoto proposed a solution, which is instead of confirming a transaction immediately, we're going to wait for the transaction to be buried K deep inside the longest chain. And that helps because even if the attacker can get lucky for the first few blocks, it's very unlikely that the attacker can get lucky in the long run because, after all, the attacker has less mining power than us, right? So Nakamoto did the calculation in his white paper. He made a table. And when we consider that there is a 30% adversary, in order to get a 0.1% probability of being attacked, we have to wait for 25 deep. So that's 250 minutes. OK, so now that we have learned how Bitcoin works, let's talk about the performance. So first, there's the throughput, which is how fast, on average, the Bitcoin can confirm transactions, how many transactions it can confirm in a given period of time. And this can be calculated by multiplying the block size, how many transactions are there in a block, and the mining rate. How fast are we going to mine those blocks? And then we have latency, which is how long does it take for us to confirm a transaction. And we can do that calculation by dividing the confirmation depth K we just talked about and the mining rate. OK, so far, it seems that we have a good solution to improve the performance. We can simply increase the mining rate such that we both get higher throughput and lower latency, or at least we can increase the block size such that we get higher throughput. However, that is not going to work because of forking. And if we increase the mining rate or we increase the block size, we'll get more forking. And that happens because forking happens when two nodes in the network cannot hear from each other quickly enough such that they accidentally both mine on the same parent block. And if we increase the mining rate, then it's more likely that two nodes will accidentally both mine new blocks within a short interval. And if we increase the block size, then it takes longer for the block to propagate through the whole network, and both will cause the forking to increase. And forking is bad because forking compromises security. And to see why, we can see that on the left, there are 6 blocks in a perfect chain manner, and on the right, still 6 blocks, but with a lot of forking. If we compare them with the same adversary, we can see that on the left, we're secure, but on the right, we're no longer secure. We're outperformed by the security because forking essentially reduces the honest mining power. How bad is it? So we did the calculation. If we increase the mining rate or the block size just by a little, we actually sacrifice a lot of security. So in summary, Bitcoin couples security with performance. So next, let's talk about Prism. As I said, Prism does decoupling in order to improve the performance. And the first insight we got was in Bitcoin, a block actually serves two roles. The first is the new block will add some transaction to the ledger. And second, more implicitly, a new block is also certifying all of these direct and indirect parent blocks. It's like saying the block and the chain I mine on is the one true longest chain. So the first role, proposing, is directly tied to the throughput, because the faster we can propose, the more transactions we can add to the ledger. And the second role is tied to the confirmation latency, because the faster you can vote, the quicker you'll get confidence in a transaction. So let's first deal with the throughput. We already saw that in Bitcoin, the throughput is limited because of a forking. So what if we have a structure that does not have even the notion of forking? And that's why we introduced the transaction block. So transaction block is mined by the miners at a high mining rate. But however, we don't assume any structure, any chain structure between transaction blocks. So we can mine very fast. We can mine a lot of them, but without fearing that we increase the forking, because forking does not exist here. Okay, then what are we going to do with them? We're going to bring them to order by introducing proposer blocks. So proposer blocks are lightweight blocks which only contain hash pointers to those transaction blocks. And the proposer blocks will be mined in the Bitcoin rate and chained together as a Bitcoin longest chain. And because we mine them slowly and they are small, so the forking does not increase, however you increase the throughput. And that's how we increase and that's why in Prism, we can achieve the physical limit of your underlying network without even sacrificing security. And I'd like to mention here that Prism is also based on longest chain, it's also based on proof of work. And a miner will mine two types of blocks simultaneously, and they will use the hash value of the block to decide what type of a block, transaction or proposer, it becomes. So now that we have dealt with throughput, I'm going to talk about latency. So to deal with latency, we first note that even after we introduce the proposer chain, the voting rate still doesn't increase because we only have one proposer chain doing the voting. So we're going to do this deconstructing thing again and separate the voting job from the proposer blocks. And watch this. I'm going to redraw this graph in this way. So for now, it seems that we just separate a proposer block to two parts. One only contains the hash pointers to the transaction blocks, and the green ones that we call voter blocks, they only contain the pointer we call a vote to the proposer block. And we no longer assume longest chain structure in proposer blocks, but instead we assume a longest chain structure like Bitcoin in the voter blocks. So far we have not improved the confirmation latency because still we only have one voter chain, and it's very important that this voter chain is secure, so we still have to wait for 25 deep. Otherwise, the attacker can simply attack the voter chain as they do for Bitcoin. But now that we have separated the proposing and voting job, we can introduce a lot of voter chains, for example, 1,000. And an interesting discovery is that now that we have 1,000 voter chains, we do not require each one of them to be as secure, because even if, say, the attacker can attack one of the voter chains with, say, 30% probability. However, it's still very low probability that the attacker can simultaneously target 500 of the voter chains. So that's why we can reduce the confirmation latency K in Prism without sacrificing security. In a recent paper we published in ACM CCS 2019, we mathematically proved that as long as the adversary has less than 50% power, Prism guarantees security and liveness and consistency as in Bitcoin. For throughput, Prism provides 1 minus beta times C, where beta is the adversary power and C is the underlying network throughput. For confirmation latency, Prism's confirmation latency is proportional to the underlying network delay D, proportional to the confirmation reliability we need, and inversely proportional to the number of voter chains. Okay, now seems that we have a very good theory. It looks promising, but we also want to understand how it performs in the real world. And the theory doesn't just tell us that, because first, we have to admit that the protocol is a little bit more complex. It's a little bit more complex than Bitcoin. And second, actually in the theory, we assumed a simplified networking model. And also, recall that when we describe the confirmation latency of Prism, we use the big O notation, so that it's just a proportional. We don't know the constants here. And finally, there must be some other bottlenecks than network. So what are those bottlenecks going to be? That's why we did a system implementation, and I'm going to introduce that next. We implemented Prism in 10,000 lines of Rust. The implementation uses the UTXO-based model and supports pay-to-public key transactions. And we have the code open sourced. So I'd like to switch back to the demo. Sorry. First, let's see this visualization. It gives you a better sense of how Prism works. On the left, we have transaction blocks being mined at a very high rate. But recall that there's no structure within transaction blocks. The proposer blocks will refer to those transaction blocks so that it brings order to the transaction blocks, because you can just trace the proposer chain down. And we have a lot of voter chains, which gives votes to those proposer blocks. So those are the voter blocks, those are the proposer blocks, and those are a lot of transaction blocks. And here's a dashboard of the running system that I just started like 15 minutes ago. This is the topology. We have 100 nodes, and still every node will connect to 4 random peers, as shown in this figure. Here's the total number of transactions being confirmed. 54.3 million. This is the average throughput. This is the instantaneous throughput. I have just displayed like 20 nodes here because otherwise the figure will be cluttered. And here's the average confirmation latency. This is the instantaneous confirmation latency. We can see that it's fluctuating because it's a random process. And finally, we have the forking rate, which is essential to the security. We can see that the forking rate is kept about 0.1 or 10%, so it's very secure. It's secure against a 45% adversary. Okay, now that we have seen the demo, let me Okay, let's continue. we have seen that Prism achieves 70,000 transactions per second and tens of seconds of latency. And we did a comparison with other protocols, which I'll cover in a minute. So when we talk about a blockchain client, we're actually talking about two roles. The first is the blockchain client participates in the consensus. It receives new blocks, connect them together into chains, and also mine new blocks. And also importantly, it takes the blocks and produce an ordering of the transactions. So note the word ordering here. The Prism consensus protocol, the essential role is to order the transactions. And unlike Bitcoin, we allow invalid or double spend transactions to be included in the transaction blocks, because we discovered that as long as everybody agree on the order, then they can individually calculate the UTXO set and remove those invalid or double spend transactions. So that's the job of the ledger keeping module, which takes in the ordering of the transactions and execute the transactions one by one to produce the final updated UTXO set. To be quick, to have a high throughput, we have to be quick in both functions. So after implementing the protocol, we learned that first, Prism is able to move the bottleneck of a cryptocurrency or a blockchain system from consensus to ledger keeping. And more specifically, the bottleneck actually lies in the SSD and the database for storing the UTXO set. And also, we learned that you must parallelize both consensus and ledger keeping in order to achieve a high throughput. So we did a bunch of optimizations. First, we use a so-called scoreboarding technique to parallelize ledger keeping. And we do the ledger keeping asynchronously from consensus in order to parallelize consensus. We also introduce a functional design pattern in our client, and we disable transaction broadcasting in order to get a high network efficiency. So I'm going to talk about the first two optimizations here, and the rest are all in the paper. First, I'm going to talk about the scoreboarding technique. Scoreboarding is used in modern CPU designs extensively to enable parallel instructions to be executed. So for example, we have two coins on the left, A and B, and 4 transactions on the right. And suppose that we have 2 CPU cores and we want to utilize them. So naturally, we want to execute 2 transactions at a time. So in a naive way, we start the first 2 transactions, and if, very unfortunately, the second transaction gets started first, then the second transaction will get through, but the first one will fail because the coin A has already been used, but it's against the ordering of the transactions, so that's not correct. For the next 2 transactions, since the 4th transaction depends on the output of the 3rd, so the 4th one cannot get through because they are started at the same time. So we also get false result. The scoreboard technique introduces a very short table called a scoreboard, which before we execute a transaction, we will note down what coin is this transaction going to touch, or going to use, or going to produce. And before executing another transaction, we're going to look up the scoreboard to see whether there is coin that we're going to produce or use already present in the scoreboard. So for example, before starting the first transaction, we're going to note A and C in the scoreboard. And we have another CPU core, so we want to do another transaction. We found that the second transaction is touching the coin A again, so that's conflict. We are going to skip that first, skip that for now, and execute the third transaction. So we found that they can get through at the same time. And then for the rest 2 transactions, we found that there's also no conflict between them. So we're going to execute them together, and we get the correct result. So our evaluation shows that, so the x-axis is the number of CPU cores we provide with the program, and the y-axis is how fast we can do ledger keeping, the throughput. We note that after our optimization, the client achieves almost a linear scaling in CPU cores, in the sense that it scales up to 8 cores, and beyond that, the performance is kept by the SSD and the database. Another important optimization is that we do ledger keeping asynchronously from consensus. So what does that mean? We noticed that in Prism, the ledger updates is very infrequent compared to how fast the blocks are mined, because recall that we have 1,000 voter chains. So each voter chain and each voter block individually is very unlikely to trigger some new transactions to be confirmed, unlike Bitcoin, where generally every new block will trigger some transactions to be confirmed. So with that, we don't do the ledger keeping every time we receive a new block, as they do in Bitcoin. However, we put it in an asynchronous loop from the consensus logic so that it runs within its own loop periodically. By doing that, we're able to remove a lot of locks in the consensus logic, and our consensus logic is actually global lock-free, so that it can use multiple threads and multiple CPU cores to process the incoming blocks in parallel, so that it can keep up with the high block rate. Okay, so finally, I'm going to introduce our evaluation results. We did the test, we did the evaluation in 100 to 1,000 AWS EC2 instances. And actually, those instances are very lightweight. They are actually less powerful than the laptop I'm doing the presentation. And we connect the nodes into the same topology as in the demo. It's called a random 4 regular graph. Every node connects to 4 random nodes. And we introduce a 120 millisecond propagation delay to each link between peers. And for every node, we set a 400 Mbps ingress and egress bandwidth limiter to emulate a real internet. So we did the following experiments. First, we compared the throughput and latency with Algorand, Bitcoin NG, and Bitcoin. And we test whether whether Prism can scale to more nodes, say 1,000 here. And we evaluated whether our implementation is efficient in CPU or bandwidth utilization. And finally, we evaluated Prism under different kinds of attacks. And I'm going to introduce the first and the third result here. So first we have Prism, which achieves about 10 seconds of a latency and 70,000 transactions per second. Then we have the longest chain protocol, which is the protocol that Bitcoin uses. So we can see that the longest chain protocol couples performance with security, so that if you want to increase the block size in order to get a higher throughput, you have to lower the mining rate so that you get a higher latency. As you can see here, it's a trade-off curve, and you increase the latency, you can also increase the throughput. But if you want high throughput, if you want low latency, you have to pay the price in throughput. And we can see that even with optimization, so we optimize the parameters in the longest chain protocol so that it's actually much faster than what Bitcoin is today. But however, we still cannot be faster than 100 seconds of confirmation latency, and the throughput cannot exceed 10,000 transactions per second. Then we have Bitcoin NG. We implemented Bitcoin NG by modifying our code, and we see that Bitcoin NG achieves better throughput. However, the latency is still as the Bitcoin or the longest chain protocol, because it essentially uses the longest chain protocol for voting and for confirmation. Finally, we have Algorand. We run the public Algorand code in the same setup, the same instance, same topology. We found that Algorand is capped at 1,000 transactions per second, and its confirmation latency ranges from about 2 seconds to about 100 seconds. Then we evaluated the protocols in different security settings. So for example, we increased the security to 33%. We found that we only pay a little price in confirmation latency for Prism. And we don't lose any throughput because in Prism, we decouple throughput from security. We see that we pay a huge price in confirmation latency for Bitcoin NG and Bitcoin. And finally, for Algorand, Algorand's latency will spike up to infinity if we try to increase the security to 33%, so we cannot test that. And finally, we also test Prism with even higher security settings. And for the resource consumption, we see that our implementation is very efficient in the sense that more than 75% of CPU power is used for the necessary tasks, such as checking the signatures and updating the UTXO set. And for bandwidth, it may seem that since we use 1,000 voter chains, it may seem as inefficient, but actually more than 99.5% of data is actual useful data, and only less than 0.4% is for voter blocks. So here are some takeaways. First, Prism does the deconstruction by deconstructing a block in Bitcoin into the proposing job and the voting job, and scale each part to approach the physical limit performance. And we found that we must parallelize everything, consensus and ledger keeping, in a client in order to get high throughput. And we found that Prism is able to move the bottleneck from consensus to ledger keeping, and more specifically, the SSD and the database. And finally, Prism is a very simple and natural extension of the Nakamoto consensus. So here are some results. And so finally recall that Prism builds on POW. So it enjoys the benefits of a POW, but also pays the energy inefficiency. In the next talk, we're going to remove that deficiency. And here are some resources. Please feel free to check them out. And I'm happy to take questions.
Okay, we're running a bit short on time, but if someone has a quick question and Professor Tse is willing to give up a few minutes of his talk, then.
Every node can produce the transaction block, and it's possible that there are overlap transactions in the transaction block, and does the result also account for the overlap transactions? And also, how, if there are multiple chains, how this difficulty being adjusted to make sure that the network is not overrun?
Sure, that's a very good question. So for the first question, I would summarize it as spamming. So we actually thought about that problem because it's possible that, yeah, two transaction blocks may contain overlapping transactions, and we introduced a simple solution by adding a random jittering between mining transaction into transaction blocks, and we're able to show that with only a 3 seconds of a random jittering, we're able to remove 80% of spamming or conflicting transactions, and the details are in the paper. And for the second question, we used the cryptographic sortation so that what kind of a block ends up into is randomly selected, so the miner cannot control that. So basically, we only still have this one difficulty parameter, and to adjust, we don't need to balance between different chains or types of blocks. Yeah, that's true. So it can be solved by the same mechanism as in Bitcoin.
Okay, do we have another quick question? Okay, I have a very, very quick question, which is that the formal analysis of Bitcoin Nakamoto consensus by Pas, Simon, and Shalat involved a delicate dependency of the network delay parameter, how long messages can be delayed in the network, and the mining rate. Did you were you able to show that everything still works with that analysis, or is there further work to do on adapting that formal analysis to your setting?
Yeah, so actually that's the reason that we did the system implementation, because it's very hard to adopt a sophisticated networking model. Mm-hmm. And that's why we did the implementation to show how the real-world performance it is.
Maybe I can add a point here. That, actually, our analysis, our formal analysis, is the round-by-round Bitcoin backbone protocol paper. So we have not extended to the PSS model, but we should be able to.
I see, okay. So that protocol assumes messages arrive in the next round, right?
Yeah, round by round.
Okay, right. Okay, let's thank the speaker. And next up, we have Professor David Say, who is an EE professor at Stanford, very well known for his work in information theory, and is now working on consensus protocols. And we'll hear from him about proof of stake.
Okay, cool. Okay, thanks. So I'm the last talk of the session, so I better make it interesting. If it's not interesting, I'll make it short at least. Okay, all right. So I'm going to talk about proof of stake. And this is collaboration with a few people. Vivek Bulgaria, Amir Dambo at Stanford, Sriram Kannan at University of Washington, and Sieving O, Pramod Viswanath, Shichao Wang, and Ofer Zaytouni at the Weizmann Institute. So our starting point of this project was to come up with a proof of stake version of Prism that you talked about last time. So recall that Prism has very good latency and very high throughput, and it also inherits the simplicity of the longest chain protocol because the security is maintained by each of the 1,000 voting chain. Each voting chain follows the longest chain protocol. And the only potential drawback, for some people at least, is that it's proof of work. And our work here is to convert the proof of work to proof of stake. Okay? So it turns out that the central problem to convert the proof of stake is basically, because of the modular structure of the Prism protocol, is basically to convert each of the voting chain from the longest chain protocol from proof of work to proof of stake. So our problem reduces essentially to solving the problem of a longest chain protocol using proof of stake instead of proof of work. So that is what I'm going to focus on today. Okay, so the problem of designing a proof of stake longest chain protocol is not a new problem. This problem has been worked on by several different groups of people, including from Cornell, Snow White, and from the Cardano project, we have a sequence of Ouroboros papers. Ouroboros, Ouroboros Pralos, Ouroboros Genesis, and they all deal with the same problem, proof of stake longest chain protocol. So that's a lot of papers, and actually there are more probably I missed. And you may ask, so since we already have these papers, why don't we just take one of those systems and replace the proof of work longest chain in our Prism by this, and we're done. Then I can just step off the stage and go to a coffee break, and everyone else can do that as well. So maybe the problem's solved. Why am I standing here? Is the problem solved? That is, how to design proof of stake longest chain protocol. So I claim today that no, the problem is not solved, and there's still work to be done, and I'll show some results. Okay, so what's the issue here? Let me just take one of those 4 papers. They are quite similar, I must say, the solution. So I'll just focus on one of them, is Ouroboros Pralos. And let's understand a little bit more about how it works and what is a drawback of this protocol. So here's how it works. Let's start with Genesis. in a proof-of-stake protocol, a very important thing is to keep a source of randomness around. And this randomness is used to select participants that can propose blocks into the blockchain. Very, very important, this randomness. So you start with a genesis block and initial randomness, okay? And what Ouroboros prowess does is it divides time into epochs, okay? So this epoch is a very long time. I'll tell you how long it is a bit later. Now, within this epoch, the same randomness R0 is used to pick all the participants, okay? So in other words, the set of participants is fixed already in the very beginning, okay, of the epoch, because all of them is driven by the single source of randomness, R0. And then these participants are allowed to build the blockchain along this epoch, okay? And then when an epoch is over, you move to another epoch, and another source of randomness, another randomness, R1 is generated. And this R1 is generated as a function of the blocks in epoch 1, which has already reached consensus, okay? So R1 is therefore consensus among all the nodes, and that is used to select another set of participants for the next epoch, and they can continue to build the blockchain, blah, blah, okay? All right, and you repeat this process, and you're going forever. Okay, so here's the question. Do people know? How long is this epoch? Anyone? 5 days, okay? This epoch is 5 days long, okay? In the current implementation of Ouroboros, in the Cardano project, it's 5 days long, okay? And let's see what happens if you have such a long epoch. There's a very serious, potentially very serious attack. So here's the attack. It's a bribery attack. And here's how it's bribed. So in this epoch, all the participants that are selected is already known. They already know that they can participate in building the blockchain during this epoch. So an adversary will now post on a public website a bribe and say, whoever wants to take the bribe can come and join me. Okay? So in this case, 3 of the individuals take the bribe. Okay? So what are they supposed to do by getting the bribe? What they're supposed to do is to participate in a double-spend 51% attack. Okay? So the honest guys who did not take the bribe will build the blockchain as normal. Okay? The red guys, bribe, they do not participate in building the honest blockchain. Okay? Until a transaction is confirmed. And this particular transaction is the double spend transaction. Once it's confirmed, the red guys will go, because they already can participate due to the randomness. They are now going to build an alternate chain. And this is a double spend, removing that transaction. Okay? And therefore, these participants are now committing a double spend attack. Okay? And all you need to do is to bribe k plus 1 individuals. Okay? If your rule is k deep, because that's all you need to build a long chain. So that's pretty serious, because there are actually many, many such participants here over the 5 days period. And just bribing k plus 1 of them is enough. Okay? 2 things to observe. One is a covert. Okay? So these guys have not done any, for example, signing. So there's no explicit double sign. Because they have not done anything, they only built the alternate chain. So they only sign once. 3, VRF doesn't help. So VRF says that the adversary cannot know who are the participants. Okay? However, the participants themselves know that they can participate. So they can go and take the bribe. So VRF doesn't help to solve this bribe attack. So this is pretty serious. And the whole issue is because this window, this epoch window, is so long. And this is really a prediction window, because it is allowed the participants themselves to know 5 days in advance that, hey, I can participate, and therefore I have plenty of time to go and take this bribe. So this is rather bad. Okay? So the natural solution is to shorten this prediction window. In other words, shorten the epoch time to very few blocks so that this attack cannot be easily conducted. Okay? So you can build blocks like this, okay? And so forth. So what's the problem? The problem is that when the epoch size is small, okay, then there's not enough time to get consensus on the randomness. And the entire Ouroboros protocol design philosophy is based on reaching consensus first on the randomness to drive the next epoch. So if this breaks, then the whole design and analysis breaks for Ouroboros. So it doesn't work for Ouroboros. Okay? So here's the situation. All right. So on the x-axis, we have the prediction window. And on the y-axis, we have the security threshold. That is, how much adversary power is needed to attack the system. Okay? So what Ouroboros showed, the paper showed, is that it has a very strong security guarantee against a 50% adaptive adversary. Okay? So very strong security guarantee, 50%. However, because its prediction window is 5 days is so long, it is subject to these bribery attacks, which is outside the model. Okay? So that's the problem. Okay? So now a natural question is whether one can design another POS protocol with a much shorter window, hopefully, and keep the security threshold as close to 50% as possible. And at the same time, we can provide formal guarantee, just as rigorous as Ouroboros. And the main result of this talk is, yes, we can achieve it. And this is the curve that is achieved by the protocol we designed, and we call it C-correlated POS, which I'll explain a little bit later. Okay? The point is that this protocol is proven secure with these thresholds, even without consensus on randomness. No consensus on randomness, still proven rigorously secure. And you can see that the performance is very close to 50%, except when C is very small. But even when C equals 1, you can get a security threshold of about 27%. 27%, OK? So what I'm going to do for the remaining talk is to focus on explaining what's happening for the C equals 1 case. And the innovation here is really a new approach to do security analysis. And then I'll briefly talk about the whole curve. OK, so C equals 1, what's happening here? So let's look at the protocol. The protocol works like this. So instead of a long epoch of 5 days, we're going to go to the other extreme. Every 20 seconds, whenever a new block is generated, we update the randomness, every block. This is a totally different extreme. 5 days or a burst, 20 seconds, this protocol. OK, so here's what we're going to do. Every time a block picks a leader, a proposer, a participant, based on the randomness R0, then the randomness get updated as a function of the key of this individual and the original randomness R0. You get R1, et cetera, et cetera. So participants are picked one at a time, no longer known in advance. OK, every 20 seconds. All right, every 20 seconds. If there's one block every 20 seconds, OK? All right, so this is very fast updated randomness. No time to reach consensus, no consensus on randomness. And what's the problem here? And the protocol is always our favorite protocol, mine on the longest chain. Always mine on the longest chain. This is the longest chain protocol. No consensus on the randomness, but we have a problem. And this is the reason why our boss doesn't want to go there. But we're going there. All right, so what is the problem? The problem is that we have independent randomness for each of the different blocks, okay? And that gives a lot of opportunity for the adversary to try out many different blocks to try to find an advantage over the honest guy who just keeps on growing on this stupid longest chain, okay? So this is a so-called, or at least a version of nothing at stake attack. And that is the biggest problem of this protocol. So this protocol is actually not new. Several projects have used this protocol already. And in fact, a paper that was actually presented a year ago at SBC analyzed this particular protocol for C equals 1. That is, randomness update every block, okay? Now, unfortunately, they did not give a formal security analysis. What they did is they did a private attack analysis. In other words, they look at one particular attack, private attack, and they analyze the security of this protocol. And in the private attack, what you do is you have the adversary mines the honest guy mines on the longest chain. The adversary mines on every block, which means that it can grow a tree because it can mine on every block. And because there's so many blocks, the opportunity for you to increase, amplify the growth of this tree beyond the stick of the adversary, okay? And so what you get is that the growth rate of the honest, no, let's call it lambda. Let's lambda be the total growth rate. Beta is the adversary stick fraction, okay? And lambda times 1 minus beta is therefore the honest growth rate. This is the honest growth rate. Blue. Blue is honest. Cool and honest, okay? Now, the adversary growth rate should be lambda beta, right? Because beta is the adversary stick. But because of this nothing at stake tree, it has an amplification factor of E. Somehow E shows up. E always shows up at appropriate times or inappropriate times. E times lambda beta. Okay, so if you do the math, this means that if beta is less than 1 over 1 plus E, then this growth rate is slower than this one, and therefore the private attack is failed. So which means that if you look at the threshold 1 over 1 plus E on beta, then that means that if you have power stick more than that, then forget it. The private attack will kill you. So the system is insecure there. But now the leftover issue from Fan and Zhao's paper is what happens on the left-hand side. If it's less than 1 over 1 plus E, what happens? What they showed is that the private attack will fail. Okay? But what about other attacks? Can they succeed? Okay? So here comes the crux of the issue. And to understand this issue about private attack versus other possible attacks, let's go back to the history of the literature a little bit. Okay? So let's go back to the proof of work, okay? Longest chain. So Nakamoto proposed this protocol 12 years ago, 2008, okay? And in that paper, he showed that the Nakamoto's proof of work longest chain is secure against the private attack, okay? A specific attack. 6 years later, a beautiful paper by, again, the Cardano guys, okay? They showed that actually it's secure against all possible attacks, okay? So it takes how much effort to do this. Let's compare effort. Let's measure work by number of pages in the paper, okay? So Nakamoto paper, 9 pages long. Everybody can read, okay, before they sleep. These guys' paper, 46 pages long. Okay, 46 pages long must be more complicated than 9 pages long, for sure. Yes, indeed, it took us 46 days to read this damn paper. Okay, all right. Now, you may say, all right, man, these guys are probably just, they want to publish in some good conference, spend all this effort, but nobody cares. Who cares whether it's 9-page or 46-page? Nakamoto is OK. Turns out that these 40 pages are necessary. Because if you try to modify, for example, and design new protocols, and you think that, hey, like Nakamoto, as long as I'm secure against the longest chain, the private attack, that I'm OK, like this protocol Ghost by these people, where several projects built on this Ghost, turns out that there's an attack. And this attack is a pretty famous attack called a balance attack, okay? Not like the private attack, it's a different type of attack, where they build 2 chains to balance it. And it turns out that Ghost is, although secure against private attack, not secure against the balance attack. So therefore, the 46 pages is necessary. You need the 46 pages. It's a lot of work and sweat, but you need to do the work and do the sweat. OK. Now, so we're going to sweat out. That's us. OK, so we're not Greek. We're not from Cardano, but we're still going to do it. OK, so what are we going to do? We're going to do a formal security analysis on the proof-of-stake protocol that we talked about earlier. Not just the private attack, but all attacks. But man, the problem is difficult. Why? Because the nothing at stake provides a difficulty that is not in proof of work. So in proof of work, the argument basically goes as follows, okay? Although 46 pages long, let me summarize in 10 seconds for you. Basically, that paper says that, hey, whether it's private attack or balanced attack or whatever attack you can think of, the end point is that you have to be successful, you need to build 2 chains. 2 chains. And to build the 2 chains, you need to match, the adversary needs to match the honest nodes block by block. If the honest node has 1 block, the adversary has to have 1 block. And therefore, if the number of adversary blocks that can be generated is less than the number of honest nodes, then no matter what the attack is not possible, which implies 50% security. So the security is obtained by basically 46 pages is basically clever counting of the number of adversary blocks. This whole argument doesn't work for proof of stake with NAS. Why? Because look at this tree. Look at these guys, man. There are exponential number of adversarial blocks over the number of honest blocks. And so therefore, if you follow this argument, you will get a trivial result, which says nothing at stake gets 0% security. Is it true? So the question is nothing at stake 0%, or is it 1 over 1 plus e, or somewhere in between? OK, so we resolve the problem. So we resolve the problem by not using the Ouroboros, so not Ouroboros, the Cardano Bitcoin backbone framework, but we invent a totally new approach. And this new approach we call adversarial proof convergence. So let me take 2 minutes to explain this, OK? So here's how it works. All right, so the blue blocks are honest, OK? And they may not be on a chain, but these are all the honest blocks that have been generated so far as the algorithm, as the protocol runs, OK? All right? Now let's think about what are the adversarial blocks that can disturb me, that can disrupt my security. Well, these are all the trees that could be grown from the previous honest blocks. All the trees. So before, we were looking at the private attack, only one tree. But now we have to deal with all kinds of attacks. We have to look at all the trees, which looks pretty scary, right? So the problem becomes a race between the blue blocks and all the trees. And the blue block is growing at lambda times 1 minus beta. And the red guys, each one of them is growing at e lambda beta. OK? Now, if you look at the race between these guys and the trees that are far back, that's easy. Because e lambda beta, if you're on this side, is going to be less than this number. And so they can't catch up. So that's the essence of the private attack. But because we have to deal with all attacks, we have to worry about all these trees simultaneously. And the guys close by can certainly catch up, because although their average rate is lower, by randomness, they could catch up. So most of the time, actually, there will be some trees that can catch up to me. OK? However, the point, though, is that as I run onwards, I will get some point lucky by random chance that all the trees behind me will not be able to catch up. Just by the sheer of waiting long enough, this will happen. And that's why we call it adversarial proof convergence. Because at this point, the green block, everybody could not catch up. And at that point, I reach consensus on the longest chain up to that point. And every now and then, this will happen, we can show. So every now and then, you will converge. Nobody can attack you, and your longest chain frozen, and then you go forward. And that's how we show that we are OK here. OK? So therefore, this analysis really shows the power of the longest chain protocol, because the longest chain protocol is able to win the race against all these trees. All right. OK, the last thing I want to talk about is how to improve the threshold. So now, humans are very greedy. Because before we were worried that this nothing attack would kill us and get us 0% security. But then we proved this 1 over 1 plus e, which is 27%, which is positive. We should already congratulate ourselves, go to Hawaii, relax, and so forth, right? No, we're going to work harder. Because now we have 1 over 1 plus e, and our bar says 1/2. We want to get to 1/2. We don't want to be less than our bars. What's the point, right? You're here to win. So you want to get to 1/2. So how do we get to 1/2? That's the question. Now, actually, Fan and Zhao has an idea which seems pretty good. He said, hey, the adversary is growing everywhere. Hey, I'm honest, but I can grow everywhere as well. Why don't I change the protocol? Instead of growing one chain, let me grow at a few places. And they call these protocols G-greedy or D-distance greedy, fighting NAS with NAS. Sounds pretty cool. Turns out to be no good. And it's no good precisely because the analysis is based only on the private chain analysis. That is, comparing the growth rate of this guy and this guy. In that sense, it's a good idea. But once you deal with all other attacks, then we show that a balanced attack, because of the confusion among yourself, will kill you. OK? Instead, our idea is to introduce correlation in the randomness. So instead of c equals 1, we introduce correlation, and we allow some correlation of the randomness across levels. And we can control that kind of level as a parameter in our protocol. So for example, when there's 0 correlation, everything's independent, this tree grows like crazy, and you get an amplification rate E. If you increase the correlation, the chance of you having opportunity is reduced, and the growth rate slows down, et cetera. And that allows us to get this curve. OK? And you can see that compared to Ouroboros, only very small c will already get you to very close to 50%. And this operating point allows us to get a very short prediction window against prediction attack, at the same time very secure against traditional adaptive adversary. Best of both worlds. OK, so let me say a few words, 30 seconds. What's the broader story here? So just before my talk, we heard Lei talk about Prism. And the goal of Prism is to achieve vertical scaling. That is, scaling the performance of blockchain up to physical limits of the individual nodes and the network. What I just talked about is POS, which is to achieve energy scaling, to reduce the energy requirement of POW. We have not finished yet. 2 talks. There's one more tomorrow by Sriram Kannan on coded Merkle tree, which is a data availability method for allowing to solve horizontal scaling. That is, using sharding to scale across many nodes, scale the blockchain. And just a little bit advertisement. Going to do some advertisement. We are starting this startup, trifactorchain.com, which integrates all this technology together to commercialize this effort. OK? But one more thing. Completely independently, I need to advertise for my students as well. And there's a paper tomorrow by Joachim Ner on a layer 2 solution, Boomerang. Completely separate, just to be clear, completely separate from the startup or from these other projects, but nevertheless, very interesting. Thank you very much.
OK, so we're into the break now, but if you want to stick around for questions, feel free. We'll take maybe a few questions if there are. But right now, there is a break, and we'll start again in half an hour.
oracles for TLS.
Okay. Hello, hello. Can you hear me okay? Okay, great. Test. Hi, hello everyone. Thanks for coming to the talk. I'm Fan from Cornell. I'm gonna talk about DECO, a privacy-preserving oracle for TLS. This is a joint work with people with Deepak, Jaslyn, Stephen, and Ari from Cornell. I will start with one of the applications, decentralized identity. So what is identity? Well, to use any system, the first thing that the user needs to do is to prove her identity. Namely, she's a legit user to the system, right? And the identity can be descriptive. You can think of a digital identity as a set of description about a user, right? For example, in some states, you order to purchase alcohol online, you need to prove that you are over 21. And being age over 21 is part of the digital identity. So today, the digital identities are established by divulging personal information. For instance, right, existing age verification requires users to send her name, address, date of birth, and even sometimes a picture of your photo ID to a third-party age verification services, such as agechecker.net. So disclosing this private information is a privacy concern, but it also makes these services a central hub of private data storage and ultimately lucrative targets for attack. So increasingly, popular alternative notion is so-called decentralized identity, where users gather and manage their credentials sort of locally and have full control as to what to disclose to relying parties. For instance, in the invasion deployment, authorities would issue special purpose credentials, such as digital ID with age information in it. So the user can prove cryptographically that she is over 21 using zero-knowledge proofs without revealing any other information. Right? Isn't that great? So changing how ID works is an ambitious goal, and many companies are part of the endeavor. Here's a partial list of the members in Decentralized Identity Foundation. And several standards have been proposed. WC3 has one, Mozilla has one, and Microsoft has one. But these proposals didn't address what I think is one of the most critical challenge for any new system to take off. Namely, how do you bootstrap? So proposed designs need these special purpose credentials issued by authorities, such as signed ID from DMV, digital diploma from universities, or proofs of solvency or proof of coverage from financial institutes. But obviously, very few of these authorities do that. It's going to take a long time for them to change, to evolve to the stage that offer these credentials we want. Therefore, here's a very high adoption cost. This is where DECO come into play, right? So for each type of these credentials, there are already trustworthy websites with the data that we want. For instance, Social Security agency websites displays one's date of birth after the user logs in. DECO allows the user, which is the prover in DECO, to convince a verifier that she's over 21 using the web page as an evidence, but without revealing the password she used to access the web page, or even without revealing the exact date of birth. Well, another application of DECO is smart contract oracles. Smart contracts don't have internet access, and they can't get data about the real world directly. Therefore, Oracle is an entity that relays off-chain data to the blockchain. Right. But a challenge in building oracles is much of the data we're interested is just private. A user, for example, might want to prove, again, the same example to the oracle that she's old enough to engage in a legally binding agreement, or that she has enough money to participate in some on-chain financial activities, or that her flight was delayed to collect compensation from a flight delay insurance. So, but all of this data is private, and how can a user grant access to this data without giving away the password or in a privacy-preserving way? With DACO, the user can prove statements about her private data to a party, to an oracle. Basically, this is the same kind of challenge as we've seen before, but the verifier now is an oracle. So here's the strawman protocol, right? So we now internet, we have widely deployed the secure protocols on internet, right? Transport layer security, or TLS, is widely deployed to protect the internet communication and the web pages you see. So a strawman protocol would be to directly forward TLS protected data. So here's roughly how TLS works. In handshake phase, the user and the server establish a session key K, and the server signs that session key with its private key. And I'm simplifying a little bit here because the keys are, the signature is a bit more complex than that, but this description works for our purpose. Then the server encrypts the web page under the session key and send the ciphertext to a user. So strawman protocol for user to prove to the oracle that she's over 21 is to relay this tuple, right? The session key, signature, and the ciphertext. The idea is the verifier here can verify the integrity of the ciphertext by making a chain of verification, and the correctness of the ciphertext can be checked against the public key of the server. Well, however, this simple scheme doesn't work for a very simple attack. A malicious prover, since she knows the session key, can simply forge any ciphertext because the data is not signed. Several solutions to add this so-called provenance property to TLS has been proposed. For the first class of the solution is to change how data sources work. For example, to change how TLS works and ask websites to deploy customized TLS protocols. However, we believe doing so would incur a high adoption cost because there has been millions of websites deployed in the wild, and changing all of them to use a custom TLS is going to be a high cost. Another class of solution is to leverage trusted hardware, right? For example, one of my previous paper uses Intel SGX to build oracles. But generally, using trusted hardware introduces an extra assumption on the security of trusted hardware, and also trusted hardware is not always available. So can we achieve TLS provenance without without changing TLS and without relying on trusted hardware? This brings us to the DACO protocol. DACO is a protocol that facilitates privacy-preserving proofs about TLS data. It requires no trusted hardware, it requires no server-side changes, and it works with modern TLS versions. So let's look into a little bit how DACO actually works, right? In DACO, there are three parties. We have the prover. We started with the TLS server running an unmodified TLS. Then we have prover and the verifier. The goal is for the prover to prove the provenance of TLS ciphertexts. So following the same age verification example, suppose the prover had the following session with the server. These blue boxes are TLS ciphertext. The prover's goal would be to convince the verifier that this ciphertext with the evidence that she wishes to use, indeed is from the the SSA.gov. Once the provenance of ciphertext is established, then the prover can simply decrypt the ciphertext or prove statements about the plaintext in zero knowledge. And again, notice that these ciphertexts are not signed, which is the core technical challenge here. So the main idea in DECO is to hide the MAC key of a TLS session from the prover until she commits to the ciphertext. In DECO, this is achieved using a protocol we call three-party handshake. And for now, we focus on a particular ciphertext, CBCHMAC, a popular ciphertext in TLS, and we will talk about other cipher suites later. So, in a nutshell, at the end of a three-party handshake, the TLS client and the server share the same encryption key. The K-ink is the same as the server and the client, which is just the same as standard TLS. But the MAC key is sort of secret shared between the prover and the verifier. And now, since the prover don't have the full MAC key, the prover can't forge ciphertext and can't sort of spoof the server, as we have seen before. So here's the overview of the DECO flow. Right? It has three phases. In the first phase, shared keys are generated in a three-party handshake. And in the second phase, after the handshake, the prover queries the server as a EuroTLS client. And after receiving the response, the prover commits to response by sending it to the verifier. Then the verifier sends back its share of the MAC key. Now, with the full MAC key, the prover can verify the integrity of the response, and she can either choose to decrypt the entire response or prove statements about the plaintext in zero knowledge. In the rest of the talk, I will briefly talk about each step briefly. The three-party handshake. Three-party handshake is based on the standard two-party handshake in TLS, which has two steps. I'm going to talk about what they are in next slides, but the challenge here is to shoehorn in this third party in a way that is completely transparent to the server. In other words, from the server's point of view, this handshake should appear just the same as a standard two-party handshake. So how do we do that? In order to achieve this, we leverage the homomorphic properties in the first step, and we resort to secure two-party computation in the second step. The first step of TLS handshake is key exchange, where the prover, which is the client in TLS session, establishes a shared key with the server. In a three-party handshake, you can think of the prover and the verifier as two clients with independent with independent Diffie-Hellman and public keys. And the prover combines these two keys into a single one and uses the combined key to finish the standard Diffie-Hellman exchange with the server. And all the three parties compute their Diffie-Hellman value the same as before, but now you can verify that the prover and the verifier end up with shares of the same secret had by the server. So specifically, prover end up with ZP, verifier end up with ZV, and their product is the session secret Z had by the server, which is exactly the form of secret sharing we want. And the second step is to derive a bunch of session keys, encryption key and MAC key from that Z by running Z through a PRF. This is what the server will do, and we don't want to change the server, so we need to replicate the same sort of outcome on the prover and the verifier side. So they need to compute essentially the key in the desired format, but they can't do it directly because they can't give each other their shares of Z. And a natural option to compute on private input would be two-party computation, right? You can think of it as this magic box from the sky that takes in private inputs, computes on the private inputs, and spits out the results. There are generally two ways to realize this magic box of general two-party computation, but they are either optimized for arithmetic circuits or binary circuits, but not both. So here a challenge is we do have both types of computation, right? We have arithmetic circuits in the first step, and we have HMAC-based PRF, which is a binary operation in the second step. Specifically, session keys are derived from the x coordinates of ZP plus ZV. These are 2 points on the elliptic curve, and session keys are derived from the x coordinate of their sum. But computing this x coordinate in a binary circuit would involve very expensive operations because it works in a large finite field. So for a concrete estimation, we estimated that computing x directly in a binary circuit would need 900 k AND gates, which is the is the main complexity for MPC, which means the more AND gates you need, the more computation you need to perform in this 2PC computation. So we need to optimize a way, essentially, otherwise our computation will be very slow. So what we did is we essentially moved the arithmetic operation out of the circuit. And that allows us to work with a binary, single binary circuit that can be efficiently evaluated using garbled circuit-based approaches. So under the hood, what happens is a share conversion protocol, right, which takes in 2 shares on elliptic curves, and the output are shares, additive shares of the x coordinate of z, right? So doing so, the benefit of doing this is adding up 2 elliptic curve points in binary circuits takes about 900k AND gates, whereas adding up 2 numbers in finite field only takes a few hundreds of AND gates. This is how we achieve a great performance boost in the 3-party handshake protocol. And the construction of share conversion protocol is based on additively homomorphic encryption, such as PAHE crypto systems. So, zooming out from the technical details, so the outcome of all of this optimization is a very performant 3-party handshake, right? So in concrete term, it takes about 0.4 seconds to perform this 3-party handshake in a LAN setting, and it takes about 2.85 seconds to perform in a WAN setting. Compared to trusted hardware-based solutions such as Tancryer, this is indeed slower. It can be 20 times slower because it makes use of this sort of heavyweight cryptographic protocols, but DECO achieves cryptographic assurance, and it doesn't require trusted hardware. That is the main improvement. And just to quickly mention that so far we focused on CBCH-MAC, which is a popular cipher suite in TLS, and DECO supports the other very popular cipher suites, GCM as well. And by supporting GCM, DECO supports both TLS 1.2 and 1.3 because GCM is supported in both TLS versions. Okay, so coming back to the general big picture, DECO has 3 phases. What we just look at is the first phase. The second phase is more or less just the Euro TLS sessions, so I will skip that. I will then briefly talk about the third phase, proof generation. So now, after the 3-party handshake, right, the prover can essentially prove the provenance of TLS ciphertext. So once that is done, the ciphertext can be essentially treated as cryptographic commitments. And the prover then have multiple operations, multiple choices as to what to do with the commitment. Right? The first option is to simply open the entire commitment by simply revealing the decryption key. Doing so proves the provenance of the plaintext, but forgoes privacy. This could be useful for some applications. And alternatively, the prover can prove things about the plaintext in zero knowledge without revealing the decryption key. Right? And obviously, proving stuff in zero knowledge for large ciphertext would be impractical, but there are some operations we can do efficiently. Right? For example, in the paper, we proposed this scheme called selective opening, which allows the prover to decrypt a part of the ciphertext. Right? We support, DECO supports efficient record level or block level selective opening. And we can also combine selective opening with other Bell-set whistles, such as to prove a statement about the partially opened plaintext. And here the point is, even if the plaintext is large, selective opening allows us to prove zero-knowledge proof statements on only part of it, which gives us efficient proofs. For example, you can, following the same example, the prover can prove age greater than a threshold without revealing the exact date of birth. And the performance of proof generation is application-specific, and we implemented the 3 applications in our paper. And for the age proof example, actually, it takes about 4 seconds to generate the proof. And this application is to prove to a party that my age is over 18 according to some university register data about myself. DECO has lots of applications. I've talked about DID, and you will hear from Ari applications in decentralized finance. And it also has non-blockchain applications as well. The age verification can be useful for non-blockchain online age verification. Right? You can also think of other applications. In general, DECO allows the user to export their private data with integrity guarantee, and importantly, without the server's help, even without the server's awareness. To summarize here, DECO is a privacy-preserving Oracle protocol. It allows users to prove statements about TLS-protected data in a privacy-preserving fashion. It works with more than TLS versions. It requires no trusted hardware. It doesn't require any server-side modification. And if you want to learn more, I encourage you to go to our website, deco.works. We have a blog post, and we have also our technical paper. Okay, thank you. That is DECO. I'm happy to answer questions you might have.
Hi, my question is, in a real-world DApp, who will be the verifier? And because the verifier is able to audit a TLS session, how can you ensure his honesty?
Here, that's a great question. In a single sort of verifier setting, we need to trust the verifier for correctness, but not for privacy. That's the point. I mean, so a simple scheme, I do have some backup slides here, is to duplicate, distribute the trust across multiple verifiers, right? And who will be verifier depends on the application. I believe you will hear a little bit more from next talk. Yeah, I hope that answers the question.
I want to ask, what if the ECDHE, this ephemeral Diffie-Hellman, is not enabled in the server-side suites? Is this still going to work or not?
we focus on ECDHE because ECDHE is the recommended key exchange. I believe it should work with RSA as well, but since the ECDHE is the recommended key exchange, that's our focus. But I believe the protocol can be adapted to now RSA as well.
I have a question regarding the latency. You mentioned that your verification needs multi-seconds, whereas Ethereum block is 15 seconds, right? So basically, we need many, many blocks to just get one verification. Right.
Verification, you were talking about the verification is actually not the bottleneck. For example, since we use LeapSnark, verification is very, very fast.
Oh, okay, that's the
generation is more expensive, but usually generation for many applications it's not the bottleneck. You can generate the proofs off-chain.
Okay, so it is definitely possible, like for flash loans, right? Since that can be done within one block, they could potentially use your verification mechanisms, right? Could it?
Yeah, generating proofs within it depends on the specific application. As you can see, the bottleneck is the proof generation, which varies for different applications. So I guess that will be application specific.
Okay, thank you.
So very interesting work, very interesting idea of having other people vouch for your data. I wanted to understand a bit more about the security assumptions you made. It seems to me that because the protocol is online and you're relaying the MAC information to the verifier might be able to send information back to the website itself. Are you relying on a cookie or something else, or what's a secret assumption of what the verifier may or may not be able to do?
That's a great question. So verifier, we don't trust the verifier is trusted to be to have integrity but not privacy. The cookies are not revealed to the verifier, and even if the cookie is used, it's not revealed to the verifier.
Any more questions?
What would be the scheme for proving insertions?
Sorry, proof of what?
Like a post request or something to prove that something was updated in a database? You just check the response headers, or?
What is the scheme for proof of database update?
Well, as I understand, all the examples are basically on GET requests. You parse the response back, and you see the signatures.
Right?
So if you want to prove that, here's a login that went through, here's a database update or something.
I see. So you want to prove that some side effect of this query happened. Yeah. I think one way to do that is to sort of make a second query and compare the difference. It would be interesting future work to look into if we can support a post HTTP post or yeah.
Cool. Let's thank again.
Thank you.
So our next speaker is Ari Jules. He's going to talk about Mixicals, simple, private, decentralized finance.
Do we have a lavalier microphone? Yeah, I think that would be better, if possible. He's getting a lavalier, but is there a clicker?
Oh, I don't think so.
No, they didn't provide one. Okay.
Is he bringing a microphone?
He's bringing me, yeah, he's bringing a lavalier microphone. A clicker. Sorry, how do I do that?
Here, let me do it.
Yeah. He's going to give me a clicker. Yeah. Yeah, thanks. Okay. Great. Thank you. I'm Ari Jules. My main affiliations are with Cornell Tech and the Initiative for Cryptocurrencies and Contracts. But I want to mention that this work was done in my separate capacity as a technical advisor to Chainlink. I'm going to talk today about mixicles. The term mixicle is a portmanteau word. It's a combination of the words mixers and oracles. And you'll see momentarily the rationale for this term. As of a couple of weeks ago, DeFi passed the $1 billion mark. That's to say there's over $1 billion of cryptocurrency in DeFi smart contracts today. This is great, but wait just a minute. Should we know this? If DeFi transactions were private, we would only perhaps have a rough estimate of the amount of money in DeFi smart contracts today. But in fact, every single DeFi transaction is fully visible on-chain. There is no confidentiality. Additionally, DeFi smart contracts provide fairly esoteric, exotic, niche instruments. For instance, MakerDAO is basically an automated pawn shop for cryptocurrency, which you can use to achieve leveraged exposure and so on and so forth. And then there are flash loans that are used mainly just to weaponize idle cryptocurrency. Our goal with mixicles is to implement a fairly natural and common class of financial instruments, which includes things like simple binary options. A binary option is effectively a bet engaged in by two players, like our canonical Alice and Bob, who send money into a smart contract, for instance, and they are betting on an event with two different outcomes. So for example, they may bet on whether the value of a particular stock reaches a certain threshold, say XYZ reaches $300 at a particular time. And if the bet goes one way, for instance, if it turns out that this threshold is reached, then one player gets the money. And if it goes the other way, the other player gets the money. Right? Very simple and natural financial instrument. Our goals with mixicles in particular are four. The first is that we would like to achieve the type of confidentiality that, as I mentioned, isn't available in DeFi instruments today. And we're going to work in a particular model. We're going to assume that Alice and Bob are fine being recognized as trading partners. They might be financial institutions, in which case it's perfectly natural for them to work together, or they may have anonymized sufficiently the pseudonyms with which they're interacting or through which they're interacting with the DeFi instrument, so they're OK being recognized through these pseudonyms as trading partners. What we're interested in doing is concealing the type of trade they're engaging in and the payout amounts, how much money is involved to a certain extent. We want this thing to be auditable. It'd be very nice if there's an on-chain record available to third parties, auditors, regulators, and so on and so forth. We want compatibility with existing infrastructure. We would like to avoid having to build extra infrastructure specifically for our mixicles. I'll describe an alternative scheme that requires extra infrastructure. The main objective, though, in mixicles is simplicity. We're aiming for conceptual simplicity. As you'll see, mixicals are very simple from a conceptual standpoint. And conceptual simplicity often translates into simple implementation. And I'll give some evidence that the implementation itself was fairly simple to achieve. So in particular, we avoid heavyweight cryptography, zero-knowledge proofs, for instance. We avoid the need for watchtowers. And complexity is, of course, the enemy of security. Zcash, for example, had a bug in which, in principle, somebody could have minted an arbitrary amount of money without detection. And I would allege that that's in part because of the cryptographic complexity in Zcash's design. We avoid that in mixicals. I'm going to show you how to build a mixical incrementally in 4 steps. The first thing we're going to achieve is payee privacy, because we're going to conceal which of the 2 players, Alice or Bob, has won the bet. Then I'll show you how to achieve trigger privacy, the trigger being the basis for the bet. For instance, the particular stock that Alice and Bob are betting on. Then we'll proceed to payout privacy, concealing, at least partially, the amount of money that's being paid out to one of the players. And finally, I'll show you how we can use multiple rounds to completely conceal intermediate payouts in the case where Alice and Bob are engaging in multiple transactions with one another. The starting point for the construction is a mixer. Mixers are used to conceal the flow of money in a cryptocurrency system by directing money to 2 different pseudonyms corresponding to the 2 players that have engaged in the mixer, if 2 players are involved. These pseudonyms correspond to Alice and Bob, but their order is randomized. Let me be a little bit more concrete. To perform the action of mixing, what Alice and Bob can do is very simply flip a coin. If the coin comes up heads, then the first pseudonym, P0, is allocated to Alice, or Alice's pseudonym comes first when money is output by the mixer, and Bob comes second. And of course, if the coin flip goes the other way, then the first pseudonym corresponds to Bob and the second to Alice. With this very simple construction protocol, we get payee privacy, our first goal for a mixical. In particular, suppose that one of these 2 players sends money to some subversive organization. Right? Anyone looking at this process on-chain will be unable to tell whether it was Alice or Bob who sent the money. That's the sense in which we get payee privacy. You can build a mixer very straightforwardly using a smart contract. Right? Alice and Bob choose some pseudonyms off-chain. They flip a coin to determine how these pseudonyms get assigned to the players, in particular the ordering of the pseudonyms. The coin comes up heads, then the first pseudonym is Alice's, second pseudonym is Bob's. They commit their pseudonyms to the smart contract, then they send money into the smart contract, and the smart contract very simply forwards the money to the corresponding pseudonyms. Okay. We can take this basic construction and enhance it in various ways to achieve other goals. For example, suppose we want to do private payee gambling. Well, in that case, the mixer can take as additional input another coin flip, the result of flipping a public coin, or taking input generated by the blockchain into the smart contract. And then payment can be determined based on the coin flip. So if the coin comes up heads, the money goes to the first pseudonym, and if it comes up heads, goes to the second. You'll see we have payee privacy here. The identity of the winner is hidden on-chain, which is very nice. Now, of course, everyone's favorite place to gamble is the stock market. Right? We can transform this gambling smart contract into a financial instrument, one based on a stock ticker, for instance, fairly straightforwardly. Right? The smart contract simply takes as input an indication of whether the target stock, the stock that Alice and Bob are betting on in our binary option, has gone up or down. If it goes up, then of course first pseudonym gets the money, and if it goes down, then the money is allocated to the second pseudonym. Right, this is the goal. There's a little complication, though. And you heard about this complication in the previous talk if you were here. The complication is that blockchains in general, and therefore smart contracts, don't have internet connections. This is a function of their underlying consensus protocols. That's to say that a smart contract can't do what you or I would do if we wanted to know the price of Tesla stock, namely just go to some trustworthy website and look it up. The solution to this problem, as you also heard during the last talk, is a piece of middleware known as an oracle. The job of an oracle, and this is an off-chain entity, is to go fetch data from a trustworthy website and push it on-chain, deliver it to a smart contract. If a smart contract needs to know a particular piece of data, it can call the oracle on-chain. Oracle has an on-chain front end, and the oracle will go out and fetch it, and then relay it to the smart contract. So we can, in fact, realize the financial instrument I described before simply by engaging the services of an oracle to indicate whether or not the target stock price went up or down, very simply. Okay. This is all well and good, but we still have a confidentiality problem here, right? If the oracle is relaying the fact that a particular stock price moved in a particular direction, this is going to be visible on-chain. And that means that the basis of Alice and Bob's bet, the trigger, is world-readable, visible to everyone. And this we would like to avoid. We would like to achieve trigger privacy, as I described it earlier. How do we do this? Well, very simply, Alice and Bob can flip another secret coin, which they make visible to the oracle. The purpose of this coin is to designate what I'll call a secret trigger code. If the coin comes up heads, then the oracle, in the case that Tesla goes down, which means that Alice wins, is going to relay a 0 bit. And if the opposite occurs, it will relay a 1 bit. If the coin flip, on the other hand, is not heads but tails, then the code is inverted. Right? In that case, b equals 0 corresponds to Bob winning, Tesla up in this case, and vice versa. So now, all that the oracle is going to deliver to the smart contract is a single bit. And the meaning of the bit is randomized. Right? So now, it is not clear to somebody observing this process what it is that Alice and Bob bet on. In other words, we've concealed the trigger and achieved trigger privacy. So now we have both payee privacy and trigger privacy. This is great, but we're not quite there yet. We still have a confidentiality problem. Visible on-chain at this point is the amount of money paid to the winner. Everyone can see that the winner wins $1 in this particular case. And this, too, we would like, ideally, to conceal, at least partially. How do we do this? How do we achieve what I described earlier as payout privacy? It's easiest to explain payout privacy by example. Right? Rather than having Alice and Bob each pay in $1 and then sending all the money to the winner, what we can do instead is have them pay in $2 apiece and send $1 each to 4 different pseudonyms. In the case that the bit is 0, we'll send to pseudonyms P0 through P3. And in the case that the bit is a 1, we'll send the money to 4 different pseudonyms, P4 through P7. The key observation here is the following. Suppose that 3 of the pseudonyms correspond to Alice and 1 of them to Bob. Well, in this case, Alice wins $1. But if all of the pseudonyms belong to Alice, then Alice wins $2. And you'll notice there's no way for somebody just seeing dollars sent to 4 different pseudonyms to distinguish between these 2 cases. You can't tell if Alice is winning $1 or $2. And conversely, if 3 of the pseudonyms correspond to Bob and only 1 to Alice, then Alice loses $1. The upshot of all of this is that you can't tell by observing payment on chain whether Alice lost $2, lost $1, whether neither of them lost anything, neither of the players, or she gained $1 or $2. In other words, we can conceal 5 different possible payment amounts for each player with this setup. And so we get at least partial payout privacy. We can amplify the privacy we achieve with a simple trick. The trick is to express the payment amount in binary and to allocate payments according to each of the digits of the binary string indicating the total payout. So for example, we can have payout amounts of $1, $2, $4, and, well, there's a little rounding issue with the last digit, $7 instead of $8. And now there are 29 different possibilities for the payouts allocated to players. To put it another way, the number of possible payouts now can be exponential in the number of actual payouts, whereas previously we needed a number of payouts linear in the total payout amount. So we get this nice amplification with this simple trick. With this now, we've achieved payee privacy, trigger privacy, and payout privacy. The final evolution of the mixicle is use of multiple rounds, as I mentioned before. So in our initial setup, the players send some money into a smart contract, Oracle delivers its bit, and then one of the players gets paid, a payment is made to the pseudonyms, the payout occurs. But an alternative setup, and this is what we do if we have multiple rounds, is to keep the money in the smart contract and merely store in the smart contract a commitment to the balances of the players. As the players are not immediately receiving money, but their balances are recorded in a hidden way within the smart contract. And we can do this repeatedly. If Alice and Bob are going to engage in multiple interactions, we can continue to receive Oracle reports and update the secret state in the contract until the point at which the players decide that they want a payout to occur. And we can also make small modifications. Players can pay in money during intermediate rounds and can withdraw money during intermediate rounds as well, as you can imagine. What do we get from this arrangement? Well, we get an efficiency gain, which I'll describe a little later, but we also fully conceal intermediate payouts. The only payout that's visible on chain is the final one, in which the money is finally dispersed. And there we benefit from the payout privacy that I described previously. We can push the confidentiality of our mixicle construction even further. You may have noticed that there are still some confidentiality issues. And in particular, the Oracle must know the trigger on which the mixicle is based. It, after all, is responsible for implementing the secret trigger code. Ideally, Alice and Bob would like to be able to hide the trigger from even the Oracle itself. Now, this may seem hard to do, but you've actually already seen the solution to this problem in the previous talk. Alice and Bob can make use of deco. So as you recall, deco allows a user to prove things about a TLS session to an Oracle. So the setup here is that Alice and Bob commit in the smart contract to the trigger that they're going to use, and then the event occurs, the date on which they want to assess the movement of the stock, for instance, occurs, and then one of the 2 players queries a website, gets the stock price, and proves to the Oracle that the stock moved in a particular direction without revealing what the stock ticker was, just revealing, or just proving rather, that the stock that the player is querying from the target website is identical with the stock that was committed to in the smart contract. So all the Oracle knows is that Alice and Bob agreed that the trigger was XYZ, and that a player is using Deco to report on the movement of stock XYZ, but the Oracle has no idea what stock XYZ is. That's the idea. So now we're able to hide the trigger from the Oracle. I also mentioned that we'd like to achieve auditability in our mixical constructions. And the way to do this is very simple. The players commit ciphertexts on the secret terms of the contract, on all of the secret parameters of the contract to the smart contract itself. This serves two purposes. First, it allows selective disclosure of information about the trade in which Alice and Bob engaged to an auditor or a regulator. It also serves the purpose of holding the Oracle accountable. If the Oracle cheats and provides an incorrect input, well, there's a record on chain of what it was supposed to do. If the Oracle has agreed to the ciphertext terms here, it can then be called out by Alice and Bob, who can decrypt the trigger in the trigger code to show that the Oracle provided an incorrect report. The construction in the previous literature, most similar to mixicals, was a very nice idea from Taj Draya, proposed in 2017, called discrete logs. And discrete there is not misspelled, discrete in the sense of confidential. The idea is very simple. The players, Alice and Bob, for instance, partially pre-sign transactions corresponding to all the possible event outcomes in the financial instrument that they are parties to. By partially signed, what I mean is that a partially signed transaction needs some additional signature in order to be complete, in order to be valid as a transaction. Where does this partial signature come from to complete a transaction? Well, in the discrete log construction, Oracle broadcasts a signature on the actual event that has occurred, on the actual outcome, broadcasts a signature S sub j. So the winning player then can take the partial transaction that corresponds to the actual outcome, combine it with the Oracle signature, and get a fully valid transaction, which can then be processed on chain. This is quite nice. And in fact, discrete logs achieves potentially stronger confidentiality than mixicals. The Oracle's broadcasting this signature. It doesn't actually know that Alice and Bob are using the signature in a financial instrument. The transaction that gets processed on chain looks like an ordinary transaction. There's no evidence that it derived from a financial instrument. So you get very strong confidentiality in this sense. But there's a catch, or a few catches. One is that discrete logs are directed mainly at Bitcoin, and in particular Lightning Network. They assume Schnorr signatures, which haven't yet rolled out, and perhaps most seriously, they need this special purpose beacon infrastructure for all possible triggers of interest. For example, you can't achieve custom triggers. But they remain a nice point in the design space for decentralized financial instruments. You can add some other bells and whistles to mixicals. For instance, you can achieve even better payout privacy by combining mixicals with a system that conceals transaction amounts. Aztec and Zether are a couple of examples of such systems. They can be integrated fairly straightforwardly into mixicals at the cost, of course, of more expensive gas per transaction and additional complexity and trust assumptions, which are to some extent at odds with the design goals of mixicals. We can also create non-binary mixicals. We can have mixicals with multiple event outcomes, and we can even conceal the number of possible event outcomes. We can conceal the cardinality of the instrument. We can have multiple players. There's no reason to restrict ourselves to 2. And additionally, in an update to the paper we should be releasing 2, we explore a stealth version that's sort of like discrete logs for Ethereum. We actually have a couple of different variants, one that uses ECDSA and one that relies on Schnorr, should it be, or Schnorr signatures should they be implemented. Well, I mentioned that mixicals, because they're conceptually simple, lend themselves to fairly straightforward implementation. And in fact, we have a prototype of the multi-round version of mixicals that I showed you, something we call SIMI-PPS. You'll find it in the paper. This implementation required only 188 lines of code. It's really rather compact and fairly easy to audit, we hope. The gas costs for this transaction, this construction in Ethereum, are also fairly reasonable. The most important cost in a multi-round mixical is the new round, the cost of implementing a new round here. All the rest can be amortized across rounds. And so this is on the order of 170,000 gas. According to a back-of-the-envelope calculation I did this morning for a standard Ethereum transaction, standard speed Ethereum transaction, this would cost about 13 cents. And as I said, the rest can be amortized across transactions. More generally, though, mixicals are just one point in a large design space for DeFi instruments. And they may need some modification to address real-world needs. I see mixicals as most important in highlighting that oracles can do more than just deliver data, and that blockchain trust and resource boundaries can be flexible, a notion that we see, for instance, in layer 2 systems. To illustrate this, let me explain that when an oracle is invoked by a smart contract, what's called upon is generally not a single entity, but rather an oracle network, a decentralized oracle network. This means that the creators of the smart contract make use of some network, Chainlink would be an example, by selecting a subset of nodes that they particularly trust, a subset of nodes that they regard as reputable or trustworthy. And this subset of nodes effectively forms a permissioned committee, and therefore a high-trust committee. If you have a trustworthy committee, there's a lot you can do. This committee can achieve consensus on the value of some piece of data. That's the basic Oracle functionality that most people are familiar with. But it can do a lot more as well. For example, the committee can facilitate bidirectional communication. It can enable a smart contract to control, say, a cyber-physical system, an autonomous vehicle or a smart lock or what have you. It can do privacy-preserving computation, multi-party computation, for instance, or it can use trusted execution environments. And it can, in principle, even deliver persistent services, things like robust storage. In general, then, this type of committee, and therefore Oracle networks, can empower smart contracts to do a wide range of things that they can't do in an isolated environment. That's it for the talk. If you're interested in learning more, there's a paper online at the URL given here. Our prototype is also available on GitHub. And let me briefly take the opportunity to call out my co-authors here. You see their names, and particularly Lorenz Breidenbach, who contributed some of the key ideas in the paper and did the implementation for the most part, and so on and so forth. Thank you.
Any questions, Sari? I have a quick question. When do you expect this to be up so that people can start experimenting with mixicals?
Yeah, they can experiment with the prototype code.
Okay.
It's available.
So it's functioning.
Yeah.
A question. I know like this Oracle network can verify the truth of the data, but sometimes the truth may be manipulated. For example, a stable coin may be pushed to $2 price temporarily, right? So how would your Oracle network, make sure a stable coin has a stable price?
Well, Oracle attestations are only as good as the proofs that the Oracle nodes are relying on. So an Oracle network can't fix a buggy proof.
Hi, so are the gas cost estimates, is that for the version that does use DECO or without?
That's not using DECO, but DECO actually operates off-chain, so it's not going to have an impact on gas costs.
Oh, okay, because I thought somehow with DECO there's some snark verification in
yeah,
the contract.
that happens off-chain. So.
Oh, really?
Yeah.
Okay.
Yeah, right. So the prover is proving something to an Oracle node, which then relays an attestation to the blockchain. But the proof itself is happening off-chain.
Ah, okay, so you, all right, I see.
Yeah.
Do you have a sense of how the gas cost will scale with additional parties or additional conditions, more complex conditions? For the setup, at least.
Yeah, I don't actually know offhand. I'd have to think about it, or we would have to enhance the prototype. I can't give you an answer right off the cuff.
In case the oracle's available for that particular second for contact, and the available oracle is malicious, then how does the network respond? Is the network able to identify?
Yeah, so the concern about malicious oracles is the reason for using a committee rather than a single node. And the presumption is that a majority of the nodes in the committee are going to be honest if you've selected well. This is why you have redundancy. Nodes can fail, nodes can provide false reports.
Let's thank Ari again.
Okay, thank you.
And we are resuming tomorrow at 9.